Thank you, everybody, for joining us. Our first lecture for the Celestial Holography 2022 school is going to be by Andrea Puhm and introducing us to Celestial CFT. Take it away.
Hi, thanks, Sabrina. Thanks a lot for the invitation and for the honor to starting this week's workshop on Celestial Holography. And I was asked to give an introduction to Celestial CFT. And so let me start maybe with a disclaimer, because I saw a lot of experts in the audience. So this is supposed to be an introduction to this topic for the school, in particular geared to PhD students and newcomers to this field. So many of you who are working on Celestial Holography will already know what I'm gonna explain. And so consider yourself warned if you're stick around. Okay, so the outline of this lecture will be, I'm gonna start with some remarks about why we do what we do. Then there will be some basic comments about asymptotic flat space and S matrix, introducing some basic notions. Next, I will discuss soft theorems and asymptotic symmetries and their relation, which has fueled this new program that has become known as Celestial Holography. And then we're going to get to the main part, which is introducing Celestial CFT, which will start with motivating what you might call a holographic map. Then going to introduce the building blocks for Celestial CFT, which includes, in particular, the operator products expansion, which is a very important tool in CFT. And then we're going to discuss celestial symmetries and end with some outlook connecting to the lectures that are going to follow. And another thing that I want to sort of emphasize right at the beginning is to all the students and all the newcomers, please stop me at any time and ask a lot of questions. Okay, so let me start with some motivation. So this is a workshop on Celestial Holography, and what we're doing is we're recasting the S matrix in a different representation, which we call celestial amplitude. And the reason for this is that the S matrix is the basic observable for quantum gravity in asymptotic flat space, and we would like to understand better how to deal with that. And so one of the big questions is, what are all the symmetries of nature? And that's very challenging. And in a sense, one aim of a celestial holography that has become clear, in particular in hindsight, is that it aims to make a maximum numbers of symmetries manifest. And this will work in a way that we recast the S matrix, which is usually discussed in a momentum basis, into a new basis, which makes different kinds of symmetries manifest. And we'll see that there will be actually an infinity of symmetries that we can manifest. And what's more, in this new representation, the S matrix will take the form of a familiar object that we're used to in conformal field theory. And so this is where this is heading. And one of the motivations behind this is to uncover hidden structures and symmetries of amplitudes, which might be obscured in the representations that we are used to. The other motivation for this program is quantum gravity. So in the past 2 decades, the holographic principle has become a powerful tool in tackling quantum gravity, which is in general, of course, a very challenging question. And the basic statement is that there is a duality between quantum gravity on certain manifolds and a theory without gravity on the boundary of that manifold. And very powerful, of course, is the under de Sitter conformal field theory correspondence, which has given us a lot of insights into quantum gravity, such as, for example, the physics of highly charged or highly rotating black holes. And a lot has been done for this case of negative cosmological constant, but much less is known about other kinds of manifolds. In particular, of interest to us, of course, is positive cosmological constant for our universe. But then with approximation, many processes in our universe can also be described in asymptotic flat space. So we're interested if this holographic principle also applies to vanishing cosmological constant. So one question here is, how general is this principle? And then can we use it if such a picture holds also in asymptotic flat space to learn something about quantum gravity? Okay, so we're after quantum gravity in asymptotic flat space. And the first thing to mention is that in quantum gravity, the metric fluctuates, but fortunately, the causal structure of a space-time that is asymptotically flat is the same as that of Minkowski space. And so one of the first things is we look at how this works, how the causal structure works. So gearing this to students, let me start by drawing a Penrose diagram of flat space, which is drawn here in this diagram on the right, where past and future null infinity are at the bottom and the top of this diamond. Spatial infinity, denoted by I0, is out here. And then these diagonal lines denote past and future null infinity. And in this representation of our spacetime, of course, the two-dimensional sphere is suppressed. So at every point in this diagram, there will be a two-sphere. And so the past and the future null boundary of the spacetime are given by r times this two-sphere. And what I've drawn here in red and in yellow are lines of constant radius and constant time. And so I've picked a particular coordinate system here, r, theta, and phi, but there will be other coordinate systems that will show up in the course of this lecture. So let me set up upfront the notation that I'm going to use. So in many points during this lecture, we'll be using Cartesian coordinates, but we'll also be using coordinates that are more useful for discussing the physics near the boundaries out here. And the coordinates that are useful here are ones that parameterize the null boundary. So we're going to use retarded time u at the future boundary and advanced time v at the past boundary, which is out here when you take the radial coordinates to infinity. And the Minkowski line element written down here can be obtained from the usual Cartesian, from the one in Cartesian coordinates, by this coordinate transformation. So this introduces this null coordinate u, which is retarded time. We'll have a radial coordinate r, and then more useful for the purpose of going towards celestial CFT will be to replace the angles theta and phi by complex coordinates z and z bar on the sphere at the boundary. And then this gamma zz bar here denotes the metric on the unit 2 sphere. Okay, so this will be the coordinate system that we're going to use. And another point I should make here is that here I've drawn flat space at the diamond. So now the 2 sphere is denoted by a pair of points rather than just one point, one on the left and one on the right with respect to the origin. Okay, so much for setting up some notation. Now let's also briefly discuss the causal structure of the spacetime. So massive particles start out at past time like infinity and go up to future time like infinity. Spatial geodesic extends to spatial infinity. And then massless particles, which will be the main protagonists in this lecture, start out at past null infinity and go to future null infinity. And then another point that is important in the discussion as follows is the boundaries of the spacetime, namely the boundaries of the boundaries. So at the future null boundary of our spacetime, we have these corners here that connect to I plus and I0. And I will denote the future of this future boundary as scribe plus plus, and the past of this future null boundary as scribe plus minus. And as you can see already from this structure, if you're used to holography in anti-de Sitter space, flat space is much more complicated. Instead of just having a time-like boundary, as in anti-de Sitter space, we now have these null boundaries, which complicates the search for a holographic picture quite a lot. And then we also have these corners here where we have quite a lot of interesting physics, but also a lot of complications because of that. Okay. So now we've talked about flat space, and I've introduced some notation for the metric and how particles propagate. Now let's also start, talk about when we go away from exactly flat space and allow for some physics to happen inside our spacetime. So we want to allow the metric to fluctuate. And so in addition to the flat metric, we'll also get one of our R corrections. So a useful coordinate system to use will be one where we can discuss gravitational waves that propagate radially outward at constant retarded time as R goes to infinity. And such a convenient coordinate system is given by going to Bondi gauge. So this sets certain metric components to 0. And let's us neatly discuss the physics that goes on near the future and the past boundary. So in addition to the flat metric, which I've written out here, so the U squared, there is a du/dr piece, and then there's this angular piece here. There will also be corrections, which are denoted by the dots. And these corrections encode information about the mass, the angular momentum, and some information about gravitational waves. So in a bit more detail, so these metric functions that appear in the dots here at subleading in an R order in a large R expansion, they determine or define the radiative data at the future and the past null boundary. So written out here for the future boundary, where I have my metric written in retarded Bondi coordinates. I have these three functions. I have the Bondi mass aspect M, the angular momentum aspect NA, and what's called gravitational data or shear CAB, whose time derivatives gives us something that's called the Bondi muse, whose square tells us about the energy flux across null infinity. So this encodes some information about gravitational waves. And so while the gravitational data is free, the Bondi mass aspect and the angular momentum aspect are in general constrained by the Einstein equations. And so these quantities here are what determines the radiative data at the boundary of the spacetime. And so much of the discussion that follows next in terms of symmetries of the spacetime will involve these three quantities. Okay, so now we can ask, now that we've introduced flat space, the causal structure, and how to go away from exactly flat space to allow for fluctuations of the metric in the large R region, we can ask, does such a spacetime admit an underlying holographic structure? So first question is, if you want to study quantum gravity in the bulk of the spacetime, where would a dual boundary theory live? Well, the natural place to be would be here, out here, at the null boundary. One question or constraints that we have is that, of course, the symmetries would have to match. But then we can even ask, what are even all the symmetries that quantum gravity in asymptotic flat space obeys? Then we can ask, is the dual a CFT, similar to the one that we have in ADS CFT? And by now we know that this would be the dual theory to quantum gravity in asymptotic flat space would be of a more exotic kind, based on properties that we have uncovered in the past couple of years. And then you can ask, what's the spectrum? What's the organizing principle in this putative dual? Let's call it Celestial CFT. And then can we use powerful techniques from CFT, like the bootstrap, in order to gain insights into quantum gravity based on some fundamental axioms or principles? And maybe now is a good time to ask if there are any questions on this motivational part.
I have a question.
Yes.
So when you are talking about the bootstrap, you can also consider the bootstrap imposed by the BMS symmetries in the bulk, right? It's not necessary to consider the bootstrap as applicable to the CFT.
I mean, so here the purpose would be to have an intrinsic theory on the boundary that will tell us something about the bulk. You can also start from the bulk and start with the knowledge of what you know in the bulk to constrain the CFT. But usually when we want to understand quantum gravity in the bulk, we use the CFT as so in ADS CFT, we have a non-perturbative definition of quantum gravity in the bulk via the CFT at the boundary. And so this is why I'm asking, can we use CFT techniques to then constrain maybe scattering in the bulk and maybe even more non-perturbative processes in the bulk? But of course, using BMS symmetry, that will be an integral part of understanding what this CFT even is. And we'll discuss much more about that. We can view, for example, BMS symmetry, we can view it as being generated by objects that live in this two-dimensional, or let's say lower dimensional theory on the boundary.
Okay.
Mm-hmm. Other questions? Okay, there are already a lot of questions on the board, so let's get on and try to understand the answers to some of them, at least partially. Okay, so let me maybe take a step back before we dive into trying to understand if there's a holographic principle, and go back to the basic observable in quantum gravity that we have in flat space, which is the S matrix. So here in this diagram, I've drawn a massless scattering process, and for the whole lecture, I'm going to focus entirely on massless scattering. But of course, this is not, we are not limited to that, and it's very important to extend everything also to the massive case. And I'm just focusing on the massless case because of time constraints, and also because the program is not developed enough, at least not as much as for massless scattering. So that's why I'm focusing on that. So what we have here is we have particles coming in from the past, then going out to the future, and scattering happens in the middle. And so intrinsically, we already defined the S matrix by on-shell data, and so it already has some holographic flavor. So we have momenta of the particles, the on-shell momenta, which we, for massless particles, can parameterize in terms of an energy, omega, and direction. So remember, I replaced the usual theta phi angles by z and z bar, and I have chosen here a convenient parameterization. And then in addition to the energy and the direction, we also have a sign, epsilon, that indicates whether a particle is incoming or outgoing. And then we can act on the vacuum with the appropriate creation and annihilation operators, depending on this energy and the direction, to create single particle states. Now let's look at this a little bit in more detail and set it up in a way that we can use later when we go to Celestial CFT. So we want to talk about going from the bulk to the boundary or back as a first step in setting up a holographic dictionary. So we need three things in order to define a boundary operator. One, we start from a bulk spin S operator, which I have expanded here into an energy momentum basis, where I use plane wave functions, and then A and A dagger are the creation and annihilation operators, which for spinning particles are addressed with some polarization vectors and polarization tensors. And here I use a similar parameterization of the momenta as before, which is very convenient when because it embeds the celestial sphere into the light cone of Minkowski space. Okay, so we need a bulk spin S operator. Then we also need a wave function if the particles are spinning, and since I'm focusing on massless particles, they are labeled by helicity, which is plus or minus the what I call 4D spin S. These are functions of a bulk point X, and then these momenta, which I've parameterized in terms of the energy and then a direction towards on the celestial sphere towards which the particles are moving. Then we also need an inner product, and inner product we can obtain in general for spinning particles from the symplectic product. For scalars, the symplectic product would just be given by an integral over a Cauchy slice, which here I've chosen to be a constant time slice of this symplectic current here, which you can recognize up to a complex conjugation is exactly the Klein-Gordon norm. So for scalars, we just have the Klein-Gordon norm as the inner product. And then for spin 1, spin 2, and so on, we can obtain inner products by looking at what the respective symplectic products are, how they're constructed. But in general, it's some generalization of the Klein-Gordon norm. And now having these three ingredients, we can define in generality a boundary operator by taking the inner product between this bulk operator O hat for spin S and taking the inner product of it with the wave function. So if these wave functions are just the plane waves, then because plane waves are delta function normalizable, so if you compute the inner product of a plane wave with another plane wave, it gives a delta function. So if you compute the inner product of this operator with a plane wave, then as you can see from here, the operator that you get will just be a creation and annihilation operator, depending on what wave functions you plug in here. And so in this way, we can define operators that depend on this boundary point, on the energy, and on the helicity. And we will use this later in order to define operators that are living intrinsically in a theory on the boundary of asymptotic and flat space that are given in a representation that's very suitable to talking about celestial CFT. Okay, so bear this in mind. We have a bulk operator, wave function, and a product, and with that we can define a boundary operator. Okay, so now much of the discussion of how celestial holography and disputative celestial CFT at the boundary, what we have learned about it has come from understanding the symmetries of asymptotic flat space and the very low energy, the infrared behavior of gravity and of gauge theory. And so before moving on to discussing a holographic map that takes what I just said into a setting that we recognize in a more, that has a more holographic flavor and that connects to CFT, we'll take a little detour and discuss about soft theorems and asymptotic symmetries. So soft theorems are a universal behavior of gauge theory amplitudes when the energy of a gauge boson is taken to 0 or soft. And for the purpose of being explicit, let's look at this in gravity. So we have a process where we have, where we imagine n particles, and we add another particle, another graviton that's determined or defined by its momentum k, which I have parameterized here in terms of the energy omega and the null vector q that depends on this point w bar on the sphere. And the polarization tensor, and the plus minus here denotes the helicity of the graviton. So when we add such a graviton to an endpoint scattering process and then take the energy to 0, what happens is that the amplitude, this n+1 point amplitude, factorizes into an n-point amplitude without the soft particle, and then is multiplied by some expression. And what is this expression? So the leading contribution to such a process where the energy of this particle, of this graviton, is taken to 0 comes from diagrams where this soft graviton is attached to external lines. So either attached to incoming or to outgoing lines. And then what we have to do essentially is multiply this endpoint amplitude by the corresponding vertex and propagator. The propagator in this case, given here, I'm focusing on massless scattering, but this can be generalized to massive scattering. But focusing on massless scattering, we see that this is just given by 1 over the momentum of the ith hard particle dotted into the momentum of the graviton whose energy we want to take to 0. And because the momentum is proportional to the energy, we get a pole. And so this is the first term in this 0 energy expansion. And then this pole here is multiplied by a soft factor S0, which is just given in terms of the momenta of all the other hard particles in the process and the momentum and the polarization tensor of the soft graviton. Now we can go to one order to the next subleading order in this expansion. There's also a very nice universal term appearing. It is constant in the energy, and this factor S1 just depends on the angular momenta and the momenta of the hard particles in the process. So these are completely universal factors that don't depend on the species of the particles or the theory. And then the next terms in this expansion would come with positive powers of the energy. Okay, so this is a universal property of gauge theory amplitudes that I've illustrated here in the case of gravity. And we have these universal factors S0, S1, and then another one at order of the energy, which just depend on the momenta and angular momenta of the other particles in the process. And a similar result holds for gauge theory. For example, in QED, we would replace one of these momenta here by the charge of the particles, and then a similar statement of soft factorization holds. Okay, so that's one piece that we will need later on. Another piece that we will need in order to discuss celestial CFT is symmetries. But maybe let me also pause at this moment and ask if there are questions.
I have a question.
Yes.
So this O omega operator, does it correspond to the symmetries, the BMS symmetries, like the angular momentum corresponds to the S1 and the epsilon, the momentum corresponds to the S0?
So I'll get to that in 2 slides, if you can hold your question until then.
Okay. Okay,
so
fine.
we'll relate this factor here to BMS supertranslation symmetry, this one to BMS superrotation symmetry, and then there are the sub-subleading soft graviton here has also been argued to have symmetry interpretation, but what I will focus on in this lecture is mainly the first 2 terms. So if you have a question about this one, maybe ask again after the lecture, and then we can discuss about this.
Okay, thanks.
Other questions? Okay, so then let me get to the symmetries. So very quick slide about one-page summary about what an asymptotic symmetry is. So we are after the set of gauge symmetries or diffeomorphisms that preserve a specific set of boundary conditions and that act non-trivially on the physical data of the theory. So what we need to do is, if we want to say what the asymptotic symmetry group is we compute, or we look at what the allowed symmetries are and then mod out the trivial ones. What does it mean? So you could imagine a gauge transformation somewhere that has support inside your spacetime, but that goes to 0 at the boundary, and it doesn't do anything. But there are gauge symmetries which do not fall off too fast at the boundary, and these gauge transformations actually act on the physical data. And so this is what we're after. So in general, the question, what is the asymptotic symmetry of a given theory or on a given background? The analysis can be very subtle. It depends on your choice of asymptotic falloffs of the fields. It depends on gauge choices, and is in general an open problem for the full interacting theory. I will assume in the following that we have the existence of a set of asymptotic symmetries, in particular the ones related to BMS, which are generated by some charges. So we'll assume that we have constructed some charges. And then having such charges denoted by Q plus on the future boundary and Q plus on the past boundary, the statement of charge conservation is that Q plus equals Q minus. And this might seem like that's an obvious thing that should hold, but it's actually a rather non-trivial statement that involves a perhaps peculiar matching condition between scri minus and scri plus that Andy Strominger uncovered in several years ago. So this is a rather non-trivial statement. And then moreover, if you want to see if these charges are conserved also at the level of the S matrix, so if this symmetry is really a symmetry of the S matrix, well, then we have to show the following statement. When we wedge this charge conservation law between in and out states in an S matrix element, this has to be 0. If we can assume that the asymptotic data decays to 0 or fast enough at the future and the past boundary of future and past null infinity, then we can split these charges Q plus and Q minus into two pieces. One that contains fields, terms that are linear in the fields, which are called Q soft, and another term that contains quadratic contributions and matter fields, and this is called Q hard. And then this statement of a certain symmetry being also obeyed by the S matrix turns into this blue equation down here, where we have split the soft and the hard action in the S matrix element. And it's no coincidence that we have these universal low energy soft theorems, and we have, on the other hand, asymptotic symmetries of asymptotic flat space. The two are actually related. And what happens is that the action of these soft charges in these S matrix elements will be related to the insertion of soft modes of the field. So, for example, the soft graviton that we have seen in the previous slide. And then on the right-hand side, the action of the hard charges will become the soft factor in the expansion on the right-hand side of the soft factorization theorem. And well, maybe this was a bit abstract, so let's look at this as the example of gauge theory and gravity in a bit more detail. So let's just look at Maxwell theory in Minkowski space. So we just have the flat metric here. And then we have to impose some boundary conditions on the fields. So we take these boundary conditions to be that the angular part of the gauge field goes to a constant in R. So this is what this 0 here denotes. So this is the order R to the 0 term of the gauge field, of the angular part of the gauge field. And a gauge transformation that's non-trivial is one that also does not fall off at the boundary. So this gauge transformation dz of some function epsilon is also order R to the 0 at the boundary. Now, this gauge symmetry is generated by a charge, which is written here, as an integral over the 2-sphere. And this integral is taken at the past of the future null boundary. So if you remember, this is the future boundary, this is I0, this is the past boundary. So scri plus minus, scri plus minus is the past boundary of future null infinity. Okay. And so the charge is given in terms of this arbitrary function epsilon and the RU component of the gauge field. And the 2 here denotes again that this is order r to the minus 2 of the field strength FRU. Now, if we use the constraint equation, which is this here, we can replace this integral over the 2 sphere at the path boundary. We can extend it to all of future null infinity by just using this constraint equation. And then we can split this charge into a soft and a hard piece. And in particular, the current here goes into the hard piece. And now we can do what I've outlined on the previous slide. We can plug this into the conservation law, Q plus equals Q minus. And what the statement of this large gauge transformation then becomes is the leading soft photon theorem. So we have an analogous statement to what I've shown in gravity. There's some universal soft factor that multiplies the amplitude without the soft photon. And on the left, we have the insertion of the soft photon. This comes from the action of the soft charges, and this comes from the action of the hard charges. Okay, so we have a relation between the soft theorem in gauge theory and a large gauge transformation. We can do the same thing for gravity, where it's a bit more involved, because now we have to keep track of all these subleading terms in the metric. We are now working with an asymptotically flat metric, and we have to ask, what are the diffeomorphisms that preserve the fall of structure of these ... terms? So this boils down to finding the BMS supertranslation and superrotation vector field, xi mu, which I have written here just at the future boundary. So these are characterized by some function f and some vector field y. The charges that generate this symmetry, which preserves this fall of structure in this expansion of the metric, are given by the supertranslation charge and the superrotation charge. And they encode these metric functions that we discussed before, namely the Bondi mass aspect and the angular momentum aspect. So for example, if f is a constant, then this would be related to the ADM mass. But in general, f can be an arbitrary function, and then this is called the supertranslation charge. Now we can do what we just did before. We use the constraint equation of Einstein's equations to turn this integral over the sphere of an integral over the whole of the boundary, in this case, the future null boundary. And then we can do a similar story as before. We use the constraint equation to then split these charges into a soft and a hard piece, massage what we get. And what we will land on is the leading soft graviton theorem, which had this factor of S0, this universal factor that only depended on momenta. And then for superrotations, we'll land on the subleading soft graviton theorem with this universal factor S1, which depended on the momenta and the angular momenta. So now we have a relation between the BMS supertranslation symmetry, given in terms of this function f, and BMS superrotation symmetry, given by this vector field y, and the corresponding soft theorems. Okay, so let's say a little bit more maybe about BMS, also in particular since there were questions. So we have this diffeomorphism vector field that depends on this function f and this vector field y. A subgroup of the BMS group is the Poincaré group, which is what originally was expected to be the symmetry group of asymptotically flat space, but then to the big surprise, much more was found than Poincaré. But let's first look at how Poincaré is encoded here. So if we set to 0 this vector field y for the moment, then we just have this function f multiplying this retarded time derivative. And if this function f is just a constant, then this whole vector field boils down to a global time translation on the boundary. So this would be the usual translation in time. And then it turns out that if you form a function of these monomials, z bar, and z bar, you can also show that you get the other 3 spatial translations. So for particular choices of f, we get the usual translations. But in general, f can be an arbitrary function. And then instead of having global time translations that act in the same way at every point on the sphere, we get time translations that act differently at every point on the sphere. And those are the BMS supertranslations. So by allowing this function f to be arbitrary, we extend BMS, we extend the translations to supertranslations, and then we have the BMS group, which is given by the Lorentz group and supertranslations. Now you can ask, what about Lorentz transformations? Does something similar happen there too? You can start with the usual Lorentz transformations, which are given by taking these vector fields to be monomials of this form, which satisfy a global conformal killing equation, which is to say that the z bar derivative of the vector field yz is 0. And similarly for the other one, for the antilomorphic one. Now you can ask, well, if I extend the range of this yz, can I get an enhancement of the Lorentz group? And that is indeed the case. So if you relax this global conformal killing condition to a local one, then you can get holomorphic vector fields y, where which are proportional to z to some integer n. And this allows to enhance the Lorentz group to a Virasoro or a centerless Virasoro group. On the other hand, if you completely disregard this condition and allow for arbitrary functions or arbitrary vector fields of the angles, then you get the whole diffeomorphism group on the sphere. These two have a slightly different interpretation as far as preserving the boundary conditions of the metric are concerned. And we'll later see that they're also actually related from the point of view of Celestial CFT. I don't want to say too much more on that, but if there are any questions about this, maybe now is the time.
I have a question.
Mm-hmm.
So this this extra O omega operator that you had, which you said that it would correspond to other symmetries apart from the BMS symmetries,
mm-hmm.
Could it be that those symmetries are the further diffeomorphisms that are left apart from the BMS symmetries when you quotient out all diffeomorphisms by the small diffeomorphisms?
So these order these order omega terms, and then potentially even so order omega squared, and so on. So for the order omega squared, for the order omega terms, Miguel Cambilia and Alo Glada, who I don't know if they're in the audience, but they have proposed diffeomorphisms which would not fall into the class of the ordinary asymptotic symmetries that I've just discussed, but which are overleading in R. So they are interpreted as gauge transformations that diverge, that start linear, that are proportional to linear in R. And now you can ask, well, can I make an asymptotic symmetry interpretation for these and potentially for all the other terms with positive powers in omega in the expansion? And in a sense, you can, but it's a bit outside the this sort of more clear-cut asymptotic symmetry interpretation. Because what happens is that if you compute the charges associated to the symmetries, you will have divergences in R, and you have to renormalize, and so on and so forth. But these have been, an interpretation in terms of asymptotic symmetries has been proposed, yes.
Okay, thanks.
Yeah, I will not discuss them much more, but we can talk about that later. Okay. Any other questions on soft theorems and asymptotic symmetries before we go to Celestial CFT?
Sorry, I have a question.
Mm-hmm.
So for translations here, we have like a symmetric pattern, like when we have Z, we also have Z bar, and we have Z bar. But for the Lorentz, you have everything in terms of Z, which are 6 vectors. And my question is, what about Z bar here?
Yeah, so I actually only wrote YZ. You could also write YZ bar. So this notation A here denotes both Z and Z bar.
But you already have 6 vectors here.
Mm.
Yes, because I have complexified that. So I could have kept real and then have also YZ bar. Yeah.
Okay, thank you.
Maybe can I just say a remark about the subsubling? I know that's not the subject, but recently with Anna and Daniele, we have identified really what is the the asymptotic symmetry for that, and it's not it's a pseudo vector field, so it's kind of a non-local transformation at infinity. It's very clear, so it goes kind of outside the bound of the usual notion of asymptotic symmetry, but it's perfectly well identified now.
Yeah, I did not mean to say that it wasn't, just that it's slightly different from the other asymptotic symmetries, and I wasn't going to focus on on them here in this lecture, but there's a lot that one can say about those order omega, and then the whole infinite, semi-infinite tower of terms in the soft expansion, which we can try to associate to asymptotic symmetries and also interpret in terms of celestial CFT, which I will sort of end on in this lecture, but not go into much more detail. But thanks for the comment, Laura.
Could I comment?
Yeah, let Andy have a question.
Yes.
I'm confused. So is that, Laurent, are you saying that that what Campiglia and Lada said about the sub-subleading being an overleading diffeomorphism, that's not right, or it's a different formalism, or?
Maybe we can comment more on that on Anna's talk. I think we're.
Oh, okay. Sorry.
Right.
Yeah.
Yeah, my impression is that there's different ways of approaching or treating the problem, and actually.
Yeah, but ultimately, you know, Campiglia, we're not able to really identify the charge, you know, the charge and generator at infinity. So they had a guess, but we can, chat more about. There's a form of non-locality that appears for these, extra terms. That in fact is apparent that it's kind of a 1 over omega term. You know, if you think about omega as being a derivative, it includes inverse derivative in time. If you want to really understand that properly.
I think I'm so as moderator, I think this just indicates that the question that was asked was a very good question. And I actually applaud Andrea for the restraint that she had, because we're actually working on another take on this, which would be closer to the Campiglia one. But this just shows how excited we should be for the preparation we have now for Anna's talk, which will close out the conference. So we really will bookend this with this question. So keep it in mind. Take it away again, Andrea.
That's perfectly timed. It's beginning and the end of the conference. Okay, so I'm going to focus on the more standard, conventional symmetries for now, because I need to get to the actual what I've been asked to do, which is to talk about celestial CFT. And this whole detour to symmetries and soft theorems was to motivate for how we should recast the S matrix in order to make it more look like one that we would recognize as a CFT object. Okay, so let's maybe look at this this super rotation symmetry in a bit more detail, and the soft term that is associated to, which is the subleading soft graviton, which I've written out here again, where I've now picked a particular helicity for the insertion of the soft graviton. And what we can now do is we can massage this expression and smear it with a certain function on the sphere, and then use the parameterization of the momenta that I've already given before in terms of the energy, the assign, and these angle directions, Z and Z bar. And when we massage that, then the soft factor becomes this very nice expression on the right in terms of the angles. And then some object on the left, which I'll denote for now as TCZ. And if we look at the thing on the right, then we see that we have something that looks like a word identity for a stress tensor in a two-dimensional theory, but not quite, because we still have this operator that acts on the jth particles, the jth particle in the remaining endpoint amplitude. But the coefficient of this 1 over z square piece already looks very much like the weights the weights in a conformal field theory of an associated operator in this what looks like a word identity. But here at this point, it's still an operator. We still have this derivative acting on the jth particle energy. And so it would be very nice if we could find a basis where this really becomes a bona fide two-dimensional word identity for a stress tensor, and this would be a word identity for a stress tensor for 4D gravity. And this is now leading up to setting up the holographic map for celestial holography. We want to end up with something where the stress tensor insertion gives us this right-hand side here, where now this H is really a number instead of an operator. So we need to find a scattering basis that goes from the usual momentum one, where we have still this operator valued weights here, to another basis that diagonalizes the action of these operator valued weights. And might seem surprising that we may be able to achieve that, but actually what's behind the scenes here is that there's an isomorphism between Lorentz symmetry in 4D and global conformal transformations in 2D. So we have this isomorphism between SO1, 3. So this is the group of real 4x4 matrices with unit determinant, with SO2Z mod Z2, which is given by complex 2x2 matrices with determinant 1. And there is a relation between these matrices that doesn't care about the sign. So that's why the mod Z2 appears. And so we can relate our symmetry generators in 4D to symmetry generators in 2D. So we have the boosts and rotations of the Lorentz group, and we can relate them to the 2D global conformal generators. So dilations, translations, special conformal transformations, and rotations in 2D. Or equivalently, we can recast them in terms of L0, L plus minus 1, and the barred versions. And these satisfy a Witt algebra or a centerless Virasoro algebra. So we can trade the boosts and rotations for these global conformal generators in 2D. And now let's use this to make 2D global conformal symmetry manifest in the S matrix. So now we are at what you can call holographic map that tries to recast the S matrix in the usual momentum basis to a new basis that makes global conformal symmetry manifest. And what it tells us is that the usual S matrix can now be understood as a correlation function of operators that carry the quantum numbers of the global conformal group. And we have correlation functions on the sphere, which encode the information about the S matrix. So in one case, we have manifest translation symmetry and the momentum basis and plane waves. And on the other side, we now have made global conformal symmetry manifest. For massless scattering, this map is just given by an integral transform in the energy that sums over all the energies and introduces this delta here, which will turn out to be the conformal dimension under the global conformal group. Okay, so maybe is there a question at this point?
Yeah, I have a question.
Mm-hmm.
So this sphere actually it not only has a global conformal symmetry, it has a full Virasoro symmetry, right?
So
in general.
So in CFT, in 2D, we have the full Virasoro, yes. And
Yeah,
it's also a very good question because here what we have with the sublinks of graviton theorem is not just Lorentz symmetry, we have superrotation symmetry. And I said before the words Virasoro without explaining where they came from, but actually it's this symmetry, the superrotation symmetry, that enhances the global conformal symmetry to a local conformal one. And I'm going to talk about that too, but thanks for asking this question at this point. Here right now, I'm just focusing on using the properties of the global conformal group, under which we have these labels delta and J. And I'm going to later talk about how the local conformal group arises.
So you're going to use this global conformal group to bootstrap the amplitude, right? In some way?
We're going to use the global conformal group to recast all these momentum space statements into new statements that look like statements in a CFT. And then we'll ask, are there more symmetries in the CFT? And we will see that we also have local conformal symmetry. And that's a good thing because we would expect into the CFT to have the local conformal symmetry. If not,
Okay.
that would be weird and would maybe go against finding a holographic principle for asymptotic flat space.
Okay, thanks. And another question is, what would that correspond to on the bulk side? I mean, the Virasoro symmetry on the sphere.
Superrotation.
Superrotation. Okay.
BMS superrotations. Yeah, and you can write, so I've written down the vector field only at scribe, but you can write it down also going into the bulk with one of our corrections.
But then that begs the question that if you have the omega symmetries on the bulk, what would those correspond to on the sphere? Because apart from the Virasoro symmetries, you can't have anything else. Isn't that right?
So we have BMS super translations and BMS super rotations, and the super rotation enhances the Lorentz group, which is also the global conformal group, to the local conformal one. So this will give a Virasoro. And then you can ask, are there more symmetries which are related then to these subleading terms in the soft expansion for the soft theorem? So the ones that we just discussed, the order omega, omega squared, blah, 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 will then also arise as symmetries, at least at a tree level and up to some caveats.
And what would they correspond to on the sphere? That's the question.
Yeah, I'm going to get to that.
Okay.
Yeah. So right now we are just using that Lorentz symmetry is global conformal symmetry in 2D, and we are going to recast the S matrix via this integral transform as a correlation function of operators in this CFT. And now let me tell you what these operators are. So before we said we can define boundary operators via an inner product of a bulk operator with some wave function. And before we used plane waves. So this operator was labeled by the energy. But now we're not using plane waves, you're using different wave functions such that these operators are labeled by delta and j. And the plane waves that the wave functions that we should use should have definite weights or definite quantum numbers delta and j under the 2D global conformal group. So those are called conformal primary wave functions for this reason. And remember that they depend on a bulk point and a boundary point. So the bulk points will transform under Lorentz transformations with matrix lambda, and the boundary point will transform with 2D under the 2D global conformal transformations, which is given by these Möbius transformations here with this complex ABCDs. And then, so this is how these conformal primary wave functions transform. And then if they have spin, so if they have some indices, then there will also be a transformation property of that Lorentz index. And so these wave functions are now conformal primaries in 2D with conformal dimension delta and 2D spin j. And this 2D spin j is equal to the helicity of the wave functions in the momentum basis, and the delta we got by essentially doing this integral transform that integrates out the energy. So these are 2D conformal primaries, and they are still, because they depend on the bulk point, they are still 4-dimensional wave functions which transform as spin S fields under the Lorentz transformations. So this is what you plug in into this inner product here to then get an operator of dimension delta and j. And now let me say in a bit more detail how you construct these wave functions. So first, we start from this integral transform of a plane wave. That's the easiest case to consider. So a plane wave e to the plus minus I k dot x, where I denote again the k by an energy and the null vector q, and I use this parameterization. And then I've added here an I epsilon regulator in order to make this integral well-defined. So if you perform this integral, you then get a function that looks like 1 over minus q dot x, where this plus minus here is related to this, this I epsilon regulator. This thing is to the power delta, and then you also get a normalization factor that depends on this delta. And now this object that you get here transforms as a scalar conformal primary with dimension delta. Now, starting from this scalar conformal primary, I can construct spinning primaries. And for the rest of the talk, I will drop this normalization factor and just consider these more simple expressions. And then in order to construct wave functions of spin, say 1 and 2, or also spinors, we have to add the appropriate polarizations. So for spin 1 and for spin 2, I'm looking for polarization vectors and tensors, which transform with definite conformal dimension and spin. Because this scalar conformal primary already transforms with definite delta and j. And so now I just dress it with some polarization vectors that also do. The first thing that we could consider is we take derivatives with respect to this sphere coordinates, w and w bar of this null vector. And that gives natural polarization vectors for positive and negative helicity, or positive and negative spin. But these do not transform with definite delta and j. Instead, we can add to these vectors a space-time dependent piece that's given here. And then we get new polarization vectors that I call m and m bar. And those now have definite transformation properties under the 2D global conformal group. So they transform with 0 dimension and with spin +1 or -1. And now it's easy to see what to do. A spin 1 conformal primary wave function is obtained by taking this positive spin polarization vector and dressing with it the scalar conformal primary wave function. And then for spin 2, we just add another copy of this polarization vector. And then for the negative spins, we use the polarization vectors that have negative spin. Okay, so this is a constructive way of how to get wave functions that transform with definite conformal dimension and 2D spin. Okay, now,
wait,
yes?
Just a question, this M and M bar, they're uniquely determined by the property you have, or there's an ambiguity now?
They were constructed in such a way that they transform with definite weights, and also have, I didn't write this here, but they are normalized. The inner product is 1. And they are also part, you can construct the full null tetrad for Minkowski space by adding 2 other vectors. And then all of them, let's call them Ln, M, and M bar, have standard normalization properties. Does that uniquely define them? Maybe you can shift things around into the other vectors.
And
So
can I understand them in a twistorial way in some way, in some sense?
Presumably, yes. What you can do is you can take now these null vectors and then the other ones that are completed into a full null tetrad of Minkowski space. You can decompose them into a spin frame, and then the elements of this spin frame satisfy something that looks like the incidence relation in for twistors. So we discussed this or like at least comment on this in the paper with Sabrina from.
Yeah, we're coming full circle to the questions where we were bothering Lionel and Atul after Celestial Holography a year ago. So I love that it's now a lecture question.
Yeah, I can point you to the paper maybe after the lecture or in the Slack channel, and also probably in Atul's talk we'll come back to this question of relating it to twistors.
I'm not going to talk about this. This is actually related to twistors for ADS3, so this is like out of bounds. But okay, if people are interested, they can ask me at the end. Yeah. Yeah. Thanks for the question. Yeah, I'm dropping a lot of details because I mean, there's a lot of things that one can say about each point here. But yeah, I'm dropping a lot of details to finish in this 1.5 hour time frame.
Could you explain why exactly the Mellin transform is usually taken?
So one natural thing is for massless particles, they already hit the null boundary. So I said they are labeled by this energy and then a null vector. The null vector is already good. You're already on the sphere. And then you have this energy. And if you want to have something that transforms with definite weights rather than respect translation symmetry, then you have to do a transform that trades the energy for the conformal dimension. So that's what the Mellin transform naturally does. Yeah. So in hindsight, since this object transforms as a conformal primary, that's what you should have done. Yeah.
Okay.
Good. Okay. So now we have this map. We have the S matrix recast in a new basis such that it takes the form of a correlator of operators with definite dimension delta J and some plus minus label that says whether I should, this plus minus label epsilon here denotes whether this operator should act on the in or the out state. So it's related to the incoming or outcoming wave functions in terms of which I have defined them in this inner product. Okay, maybe a little exercise here. So if you take this scalar wave function, for example, and we look at the north pole, which is when W and W bar are 0, then this is a very simple expression, and we can explicitly check the action of the global conformal generators L0 and L0 bar. And previously, I have shown that the 4D Lorentz generators, the boosts and rotations, can be traded for these global conformal generators L0 and the L1 and L-1. So the two that are in the x3 direction are just given by the sum or the difference of L0 and L0 bar. And in terms of the Cartesian coordinates x, they're just given by these expressions here. And so we can explicitly check that when they act on this scalar wave function, that one combination gives us the weight, the boost weight, and the other one, which would relate to the spin, is 0 for the scalar wave function. So that is just a little exercise on the side. And now we have this nice map between the S matrix in momentum basis being mapped by the Mellin transform to a correlation function of operators in a two-dimensional theory. And now the question is, what is this theory? So let me make a few remarks before continuing about these conformal primary wave functions. So in the momentum basis, we had plane waves and they form the basis. So if you take the inner product of two plane waves, you got a delta function in the 3 momenta.
similarly here, when you take the conformal primary wave functions and you compute the inner product, you find that they also form a, let's say, delta function normalizable basis, but the conformal dimension now has to lie on the so-called principal continuous series of the Lorentz group. So the real part is 1, and then there is an arbitrary imaginary part. So if delta is of this form, then these wave functions form a complete basis. And there's another equally good basis that you can get by an operation in two-dimensional CFT. That's this is ubiquitous in 2D CFT. It's called a shadow transform. So this is a particular integral transform in the sphere coordinates, which produces a new wave function, where now the dimension is goes from delta to 2 minus delta, or in d dimensions it would be there would be d minus delta, and it flips the spin. And these new shadow wave functions form an equally good basis of delta normalizable wave functions, again when the conformal dimension is on the principal series. And the relation between these two wave functions, which give rise to 2D operators, is given by this shadow integral. So an integral over the sphere with some particular kernel, and then the operator gets mapped to another operator with shifted and flipped conformal dimension and spin. So we have this basis of wave functions, and we will see in the following that actually something interesting happens when we go away from this principal series. Okay, but before going there, let me maybe also mention some other very basic aspect of Celestial CFT. It's very important, which is that of the operator product expansion. So the operator product expansion tells us what happens when we take two operators close, and how does this arise from the 4D momentum space amplitudes? Where does it come from? It comes from taking the collinear limit between two particles in the usual momentum basis amplitude. So this extracts for us a sort of 4D momentum space amplitude, taking the collinear limit, extracts for us a two-dimensional operator product expansion for this periodic celestial CFT. And in using the parameterization that we had quoted before, the collinear limit of two particles I and j then translates to taking the location of these operators zi and zj close. And what I've done here is I've taken a sort of holomorphic limit where the BART coordinates z bar and I and z bar j are held fixed, and we look at the limit where this difference zi and zj goes to 0. So what happens in collinear limits of amplitudes is that there are divergences, and these divergences come from viewing the collinear limit of two particles as a massless virtual particle that splits into a collinear pair. So what we have to look at is a propagator for these two massless particles, which is given by 1 over pi dot pj. And when they become collinear, there is a pole. And from this nature of splitting, we can extract a tree level, a universal statement of how this amplitude behaves in the collinear limit. So you have this endpoint amplitude. You take this holomorphic collinear limit in these coordinates z. And then this can be expressed with a certain function here that's called the splitting factor, which depends on the momenta of the collinear pair. And then there's a remaining amplitude where the sum of the momenta of the collinear pair is given by new momentum, denoted by capital P, and similarly for the 0 components, the energies. So in this collinear limit, we can now try to extract a statement for the corresponding Mellin transformed amplitude, which gives us the celestial correlator. And in the celestial correlator, taking zi to zj should extract for us the operator product expansion. So maybe in view of time, let me just say quickly. So we Mellin transform the statement from the previous slide, then do some smart change of variables, and then identify a certain integral in this process, which we can evaluate in generality just based on the knowledge of the splitting factors. And the integral that appears there is this one, which you can recognize as the Euler beta function. As an example, if we consider gauge theory, where all the collinear particles, the collinear gauge bosons have positive helicity, so this is +1, +1, then there will be a collinear limit that ends up in a third particle, also with positive helicity. And the Mellin transform statement is extracting the operator product expansion here. So by Mellin transforming the equation from the previous slide, we can say what happens when two operators of dimension delta I and delta j and positive helicity, when they got close together, there will be a pole when zi goes to zj. And the coefficient of this, and then there's an operator, well, the operator that appears in the OPE. And then there is a coefficient here, which is given by this Euler beta function integral. And the arguments are just given by the delta j and the delta I and delta j, which come from the Mellin transform. And then because the splitting factor has also powers of the energy, there will be in general some shifts of, because the Mellin transform has omega to the delta, and then there are some shifts by some numbers depending on what the powers in the splitting factors are. And that's why this Euler beta function with these arguments appears here. And then a similar statement also goes for gravity, where we can write down the splitting factor and then extract the OPE of two. I've given here the OPE of two positive helicity gravitons. And I'm not going to say much more because there will also be talks about celestial OPEs by Tim and by Hong Yang in the course of this week. But I just wanted to mention this since this is an important aspect of celestial CFT. Okay, are there any questions on this before I move on to the symmetries?
I have a question.
Mm-hmm.
So when you do the Mellin transform, is your aim to get the sort of CFT that you are aiming for, or because if you didn't take the Mellin transform and just took some other transform or some simpler transform, then maybe these problematic beta functions wouldn't appear.
Why are they problematic?
They aren't problematic. I suppose they'll cause some problems later on. No?
There are some special things happen at integer values of delta, but I wouldn't call them problematic. It's just what's nice is that they universally appear, just because of the fact that in the splitting factors you have powers of energy, and that just shifts whether you have. That just shifts the definition of what x and what y is with respect to the deltas in the Mellin amplitude. And the
Do they have ordinary interpretations in terms of normal CFTs?
Well, first of all, we don't quite get the normal CFT. There's many exotic features, but there are much more exotic things maybe in celestial CFT than the appearance of these OPE coefficients. Because we already know that there's this celestial sphere, so it's a two-dimensional theory. There's no doubt about that. But isn't the Mellin transform kind of forcing the sort of theory to be the theory that you're getting? Because if you don't take the Mellin transform, take some other sort of transform, I don't know what. But if you take I don't know what other transforms you have in mind, but what we are after is to recast the S matrix as a correlator. The Mellin transform is just doing that. You can go to a different basis for scattering and then ask what are the properties there. But the point is here, the Mellin transform lands us on something where we have definite transformation properties under the global conformal group. So
okay.
Excuse me, Andrea, I have a question. There's work in the literature that claims that in gravity, in perturbative quantum gravity, that collinear divergences cancel when you sum up all the diagrams, and it's a consequence of gravitational ward identities. Mm-hmm. Do you agree with that? And what does that mean for these OPEs?
So yeah, good. So here, these are just the tree-level OPEs. Then there will be, we haven't discussed any loop corrections or corrections from higher derivative operators. We haven't discussed that even here. Maybe I shouldn't have shown the graviton OPE, but at tree level, this is what you get. You get the splitting factor, and then you can infer what the corresponding OPE will be, but just starting from this tree-level statement. Somebody who has worked on this maybe correct me, but I don't think this has been generalized to
include also loop corrections and so on.
So I would recommend, as far as just trying to like promote like different talks that are going to come up, that Kevin's talk and maybe also Francisco's, depending on what it ends up actually being on, like if I'm reading the title correctly, will hopefully address this, because at the end of, I think that the thing that you're going to see is like at the end of the paper by Nima and Andy and others, like the dressing modes for these gravitons will have like a correlation function where like the collinear limits, I think, somehow get canceled by the powers of like z minus w squared times the log. And then, so definitely like the leading conal behavior should be captured by the results at the end of that paper.
Okay. Thank you.
Can I add a small comment regarding this question?
Yes, the author of the paper.
So I think the thing is that you see, if you look at the gravity OPE, if you consider not a holomorphic or an anti-holomorphic limit, but the simultaneously taking z bar and z to 0, then you see that there is no collinear singularity. So I think actually the fact that gravity doesn't have any collinear divergences is related to this fact that you see there is an extra power of z bar in the numerator of the splitting function in gravity. So I don't think it's inconsistent with any of the previous statements about cancellation of collinear divergences.
So if there are any discrepancies that arise, then I think it would mainly come from not using the transform correctly. Like if you did the transform and there are some subtleties that you glossed over, then you can land on something that may be in contradiction. But here we are sort of Mellin transforming statements and then finding what, trying to interpret them in CFT language. And yeah, okay, these Euler beta functions might look weird from the perspective of Celestial CFT. But if you do the transform correctly, then no inconsistency should arise. And thanks a lot for the comment, Anna. That should resolve Tom's question. Let me know if it doesn't. Okay. Okay, so actually move away from OPs now and just for the remainder of the time talk about celestial symmetries, which will tie back to some questions that have been asked about the more subleading terms in the soft expansions, but also trying to extract from what I've just introduced about the building blocks of this putative celestial CFT, how the usual asymptotic symmetries arise. Okay, but first we need to find Poincaré here. So we've discussed that Lorentz transformations can be given in terms of these global conformal generators, how they act on the operators. And now we also have an OPE, so we can compute commutators. And if we do that, then we find that, and by the way, here I'm using the weights h and h bar, which are related to delta and j in this way. So we can now look at what the action of these symmetry generators are on our celestial operators. And that's written out here. Again, let's go to the North Pole as an exercise to see what happens. So the commutator with L0 just gives us the weights. That's what we expect. It's the eigenvalue of L0. L-1 gives a derivative. That's also what we expect. It takes a descendants of the operator. And then L+1 annihilates this one on the origin. So the North Pole on the sphere or the origin in the complex plane. And then we've said before that these generators obey the centerless Versor algebra, and these labels M and N are within ±1 and 0. And now the celestial amplitude, the one that we got from Mellin transform the original amplitude, what are the constraints that Lorentz symmetry puts on them? Well, this is just amounts to the global conformal word identities in a 2D CFT. We have to see how Lorentz symmetry constrains them, and that's just the usual thing in CFT. So far, so good. So now a bit more strange is the way the translations act in the CFT. Remember before in the momentum basis, we had manifest translation symmetry, we had the plane waves as a basis. Now we have conformal primary wave functions, and we have Lorentz symmetry manifest as 2D global conformal symmetry. And now the action of translation symmetry gets a bit obscured, and it gets obscured in the way that now the momentum generator is a weight shifting operator. So under the labels under the quantum numbers of the global conformal group, translations act by shifting the conformal dimension via this derivative operator. So we can form from these 4 components, we can form 4 translation generators, which denote by PKL, with KL being plus or minus a half. And then we can look at what the commutator with our celestial operators is, and it's given by this expression. The simplest one, the one that's obtained by taking the combination P0 plus P3, is the one where KL is minus a half, and then this goes away, and we just have that the commutator with our celestial operator just gives us back the celestial operator, but now the weights are shifted. Each H and H bar are shifted by 1/2, or delta is shifted by 1. And then these translation generators, they compute. And now translation invariance, what this means for celestial amplitudes is that it gives us a relation, and this relation now involves amplitudes with shifted weights, just because of the way that these operators act. And so this is a more exotic constraint on amplitudes that we get in this basis. So we have the Poincaré group. So already showed these 2 commutators, the centerless Versoro and the commutator of translations. And then we can also form the remaining one between Lorentz generators and translations. And then we have the Poincaré group. And these are constrained to a certain range of these labels. But if we extend them to the full integers or half integers, then we get an enhancement of the Poincaré group to BMS group. So this then encodes BMS super translations and super rotations, and I will not say more because there will be a whole lecture about charge algebras that starts in a couple of minutes. So we'll defer to Romain for more on this. So what I'm now going to, for the remaining minutes, talk about is where the asymptotic symmetries arise from the point of view of these wave functions and the celestial operators that we have discussed. So I mentioned that these operators are obtained from an inner product of a bulk operator and this conformal primary wave function. And I also said that inner products can be obtained from symplectic products. In symplectic products, if one of the entries here is pure gauge, then these give rise to canonical charges of the gauge symmetry that these wave functions are associated to. So let's look at the conformal primary wave functions that I've introduced for spin 1 and spin 2, and let's look at which ones become pure gauge, or when do they become pure gauge. So the spin 1 wave functions become pure gauge when delta equals 1. And then we have this total derivative of some function, and this function turns out in the large R expansion at the boundary is related to the large gauge parameter of large gauge symmetry that we had before. So these are called epsilon before. For the spin 2 conformal primary wave function when delta equals 1, this becomes a diffeomorphism. But what's more is we can also write it as derivatives of a potential. And then this potential near the boundary becomes the super translation parameter f, or is related to the super translation parameter f that we had before. Now we can ask, are there more symmetries in this conformal basis? And there are. So for the spin 2 wave functions, there are 2 more diffeomorphisms. One when we take delta to 0, and another one when we look at the wave function that's related to that one by a shadow. So that will have a conformal dimension that's 2 minus 0, so 2. And these 2 wave functions are associated to diffeomorphisms that are related to diffus 2 or Virasoro symmetry. And if we expand them again near the boundary, then they will be related to the superrotation vector field YA that we had before. So we can find in the spaces of wave functions all the symmetries that I've discussed in the first part of the talk. And let me just list them in a table. So when we go away from this finite energy wave functional principal series and allow the conformal dimension to take certain integer, or for fermions, it would be half integer values, then we can recover the symmetry parameters for the asymptotic gauge and gravitational symmetries that we've discussed. So here I've listed the spin. We just discussed the spin 1 and the spin 2 cases where at dimension 1 and 0 or 2, we have our large gauge and BMS symmetries. And these can be associated to a symmetry current, which in the case of a gauge theory would be the soft photon current, and in the case of gravity would be the super translation current or the 2D stress tensor that we have discussed before, or its shadow. And as we discussed before, these symmetries are associated to soft theorems. In the case of gauge theory and gravity, at the leading order, we have this pole in the energy. And then for gravity, we also had this order 1 piece that the stress tensor was associated to. And we could also look at supersymmetric theories. We have an extension of supersymmetry to large supersymmetry. And there we have a supercurrent, which arises at certain half-integer values of the conformal dimension. And it's associated to large supersymmetry and supergravity. So we now know at which values of delta we have pure gauge wave functions, the operators that they give rise to become asymptotic symmetry generators. They are related to these celestial currents. So if we understand how the usual asymptotic symmetries work in this way and can be understood purely from the 2D celestial CFT perspective. Okay, the last few things that I want to sort of end on is we have now at special values of delta asymptotic symmetries, but we also discussed before that we have further subleading terms in the soft expansion. And there were questions about whether they also have a symmetry interpretation. And the question is, how do we know where to look for celestial symmetries in general? So let's start again with our celestial operator that we obtained from an operator of energy omega and helicity L by the Mellin transform. And now let's ask, is there something, how would we pick out these terms in the soft expansion that start with a pole and then a constant and omega to positive powers? So this is picked out by taking a limit of these operators, where we multiply it by delta plus n, and then take delta to minus n. To see that this is the way to pick out the terms in the soft expansion, we take this operator here, and we do an expansion at energies that are below some cutoff energy. So we expand in some powers of the energy, and then there will be some coefficient. And now if you take this limit where delta goes to minus n of this expression, and we do the Mellin transform of this expanded operator, then we see that this limit picks out the nth power in energy in an expansion around omega equals 0. So this is where we would look for something special to happen in a celestial amplitude when delta goes to these integer values that start at 1 and then go to 0, -1, -2, and so on and so forth. Okay, so let's look at this again for the cases that are well understood. For the leading soft photon, we had the story that in the momentum space amplitude, if you take the energy to 0, you get a soft pole multiplying the amplitude without the soft photon. And now the corresponding statement in the conformal basis would be, you take the corresponding Mellin amplitude, the corresponding celestial correlator. You want to pick out the this behavior, which in a momentum basis was a pole in energy, and here becomes a pole in delta. So this amplitude will have a pole at delta equals to -1. So you multiply it by that factor to pick out something finite. And what you will find is, of course, the corresponding statement from the momentum basis, namely that there is this soft factor. This would be the S0 factor, which are written in terms of this momentum parameterization in terms of the direction of the sphere, and then the remaining endpoint amplitude. And now you can interpret this whole Mellin amplitude, this celestial correlator, as a correlation function of operators. So this endpoint celestial amplitude becomes a correlator of n celestial operators. They're multiplied by this soft factor. And then on the left-hand side, we interpret the soft photon theorem as an insertion of a current inside the correlator. And this is the corresponding conformally soft factorization theorem, where you started with the correlator, you took the conformal weight to have a special value, and then you get the remaining correlator without this insertion and a conformally soft factor attached to that. And so we started from some momentum space, 4D momentum space soft theorem, and we landed on a 2-dimensional word identity. What is J is the 2-dimensional soft photon current. Same thing can be done for gravity. Let me just be very brief because I'm out of time. In gravity, the complication is that there are extra powers of the energy floating around, and the soft graviton theorem and the fact that translations act as weight shifting operators have as a consequence that if you take the conformally soft limit of a Mellin celestial graviton amplitude, you get a soft factor as before, but the remaining amplitude will have shifted conformal dimensions for each term in the sum here. And also here, this is not a holomorphic soft factor, but we can take a derivative and then turn it into something holomorphic. And this now corresponds to the insertion of the super translation current into a celestial correlator. And then the sublinks of graviton translated into the spaces we have already seen. This is just the OPE, not the OPE, the celestial correlator with the insertion of the stress tensor. All right. So now let me try to conclude. I talked to myself.
Sorry about that. This one thing is there's no good way to pin, like really like ring at somebody. Like, you know what I mean? You can kick people off, but you can't just be like, you know.
Did I talk to myself for the last half hour or?
No, just one slide. Obviously. No, but now that you can hear us, like we want to thank you for very engaging talk. That was lovely how many questions we had. And okay, so we had a very engaging first talk for this Celestial Holography school. And basically Andrea really presented what's the core like Celestial CFT canon in preparation for a lot of the talks that are going to be following. So for the remainder of the school, we have the pleasure of having 3 different speakers who have like 1 foot solidly in the Celestial Holography program, and then also another foot in a canon that's been like their different respective, like whether it's charge algebras or CFT or Twistor amplitudes, etc. Background knowledge, and they'll present that for us from the perspective of people who want to know about what they're doing as a celestial holographer. So we're very fortunate to start that section of the school off with Romain Ruzziconi, who's going to tell us about charge algebras from null infinity to the celestial sphere. Please take it away.
Okay, so thank you. So hello, everybody. And first, I would like to thank Sabrina for setting up this very nice event, and also for giving me the opportunity to give these lectures about charge algebra. The main topic of this workshop is celestial holography, which is basically a holographic correspondence between gravity in asymptotically flat spacetime here on the left, and a 2-dimensional celestial CFT here on the right. Very few things are known about this 2-dimensional celestial CFT, and the tools that we have to kind of constrain this theory are the symmetries coming from the bulk analysis of gravity. So basically, the main objective of these lectures will be to construct the charge algebra and to actually constrain the celestial CFT and deduce some OPE relations, and also make the link with word identities to know a bit more about this 2-dimensional celestial CFT. So here are the plan, is the plan of the lectures. So in the second point, I will review the analysis of asymptotically flat spacetime in 4-dimensional gravity. And to do so, I will work in the Bondi gate. In the third point, I will derive the charge algebra associated with the BMS symmetries. And I will also introduce this notion of BMS momentum fluxes. And after that, I will make the link between these notions of coming from the bulk analysis with the celestial CFT perspective. And we will see that in this context, the BMS flux algebra will play an important role. And finally, I will finish this presentation with some comments about the big picture that I am presenting here, and also about future directions of research. Sabrina, you have a question, or is it? Okay, so let me start by reviewing the analysis of asymptotically flat spacetime in 4D gravity. To do so, I will work in the so-called Bondi gauge, which allows to study null infinity around scribe plus here, which is depicted on this conformal diagram. And the Bondi coordinates are given by this U coordinates here, which is basically a retarded time coordinate, the space-time. You also have this r coordinate, which is just the radial coordinate in the space-time, and xa are z and z bar, which correspond to the stereographic coordinates on the celestial sphere. Then the Bondi line element takes the following form, where the various functions appearing here, so beta, UA, GAB, and V over R, are functions of the coordinates. Now, to complete the gauge fixing, you also have to impose the so-called determinant conditions, which tells you that the determinant of this transverse two-dimensional metric is r to the power of 4 times the determinant of the unit sphere metric. And so Q dot here is just the metric on the sphere. Now, to define asymptotically flat spacetime, you can impose some follow-ups on the functions appearing here in the line element. And these follow-ups have the properties that when you take r going to infinity in the Bondi line element, you just recover basically the Minkowski metric. But of course, for a generic gravitational solution, you will get some corrections in 1 over r to this Minkowski spacetime. But you can get global Minkowski metric by just taking the following values for the functions appearing here in the line element. Now the next step is to solve the Einstein's equation in the Bondi gauge with the asymptotically flat spacetime boundary conditions. And the follow-up expansions take the following form. So let me just say a few words about the functions that appear in here. You have here this Q dot, which is the metric on the celestial sphere. dA will denote the covariant derivative with respect to this metric. Now here at subleading order, you have the so-called asymptotic shear. And it's a two-dimensional symmetric tensor. And if you take one derivative of it with respect to the retarded time, you get what is called the Bondi news tensor. And as I will explain later, it contains information about the outgoing radiation in the spacetime. Furthermore, you have this Bondi mass aspect that appear here in this metric, and that basically contains information about the gravitational mass in your solution. And you have the angular momentum aspect that appear here at this order. Furthermore, you can show that Einstein's equation will also impose some, you can either see them as time evolution or constraint equations on the Bondi mass aspect and the angular momentum aspect. And what will appear here in the right-hand side is this Bondi news function. In particular, if you take the Bondi mass here, and that you integrate it on a two-sphere at infinity, and if you take the time derivative of it, then you get a quantity which is negative. And this formula is called the Bondi mass loss formula. And it tells you that the mass of the system decreases in time due to the emission of gravitational waves here going through scribe plus. So it really gives you some important information about the dynamics of the system. So you see that the advantage to work at scribe plus is that it provides some interesting information about the dynamics of asymptotically flat spacetime. And it will be a bit different if you were working at I naught, where you will have information about the state of the system rather than these dynamics.
I have a question.
Yes.
I have a question. So when you are saying that because of the gravitational radiation, the mass will decrease, the Bondi mass will decrease.
Yes.
Why is that? I mean, because gravitational radiation would increase the energy, it would carry some energy, right?
So basically the Bondi mass, you can see it as being measured at finite u, so at a finite point on scribe plus. And when you let u progress, basically you will have some gravitational wave reaching the space-time boundary. And so you are going to lose some mass in the system, just because you are losing some gravitational wave at infinity.
Okay.
This is a very important notion, so let me know if it's not clear.
Sorry, Romain.
Yes.
Is there a similar notion for angular momentum? For example, we expect that a rotating body spins down by emitting gravitational waves and not to spin up, for example, just
Yes.
intuitively. But do you see from these equations such a result?
I'm not aware of a so clear result like the Bondi mass loss, but yeah, probably if you integrate it on the two sphere, you can deduce some characteristic about the evolution of the angular momentum. But I don't think that there is a precise sign or something like this associated with that. I'm not aware of it actually.
Thanks.
Okay, so now if you are interested by the symmetries that preserve the fall-off conditions that I gave you at the beginning to define asymptotically flat spacetime, you will find that these diffeomorphisms are generated by vector fields here, xi, that takes the following form here at leading order in R. And so these vector fields are parameterized by two types of functions. You have these T functions here, which involve Z and Z bar, and these are called the super translations parameters. And you have the Y and Y bar functions, which are called the super rotations parameters, and they satisfy this conformal Killing equation. Now, if you are interested by the algebra, which is satisfied by these vector fields in the spacetime, you have to use this so-called modified Lie bracket, which is given by the standard Lie bracket of vector fields on spacetime, plus some terms here that takes into account that the vector fields here depend on the metric at subleading order. So they will involve some dependence in the solution space. And if you want to have a bracket that closes for these vectors, you have to take these terms into account. So by using this modified Lie bracket, you can derive an algebra for these vector fields here, and you find the following commutation relations that are expressed in terms of the parameters, so the super translations and the super rotations. And this defines what we called the BMS4 algebra. Let me make a technical remark at this stage, is that this modified Lie bracket here induces a structure of Lie algebroid. So if you are familiar with this notion, the role of the base space in this context will be played by the solution space of gravity. And the algebra at each point of the base space will be the set of vector fields that preserve your symmetry and that are generically state dependent. And you can endow them with this modified bracket that I just introduced, so that they form an algebra at each point. And finally, the anchor map that is necessary to have this structure of Lie algebroid is just the statement that the action of the symmetry form a representation of the BMS symmetries. So actually, the fact that you have this structure of Lie algebroid that arises is a general feature of gauge symmetries. But as you can see here, at the boundary, you don't have any field dependence in the structure constant of BMS. So you can just talk about a BMS algebra and forget about the bulk considerations where this Lie algebroid structure arises. So here I will just refer to this as the BMS algebra. Okay, so let me make a kind of summary of the BMS algebra and its various extensions that have recently appeared in the literature. So the historical proposal for BMS algebra is now called the global BMS algebra. And this is given by the semi-direct sum between the Lorentz algebra and the super translations. And actually, it corresponds to an infinite dimensional enhancement of the Poincaré algebra with the so-called super translations. And this was a bit a surprise historically that you find this infinite dimensional symmetry algebra at infinity. But the super translations are actually absolutely necessary to consider in the analysis if you want to include the radiation, so radiative spacetimes. And indeed, later, the super translations were related to the so-called displacement memory effect, which is believed to be an observable phenomenon. And they've also been shown to be symmetries of the gravitational S matrix. So more precisely, the word identities associated with the super translations have been shown to be equivalent to the leading sub-theorem. Now, the first extension of BMS that was proposed in the literature is called the extended BMS algebra. And it involves a semi-direct sum between the double copy of the width algebra, which are called the super rotations, and which correspond to the infinite dimensional algebra of conformal transformations in 2 dimensions, and again, these super translations. So notice here that since you are working on the celestial sphere, these super rotations will be singular, so they will involve some singularities at the poles of the celestial sphere. And consistently, the super translations will also have to be singular for consistency of the extended BMS algebra. And again, this super rotation extension is very important because it has also been related to the subleading sub-theorem and also to some memory effects in the same way than the super translations, in a similar way. Now, a second extension that was proposed in the literature is this generalized BMS algebra, where in this case, the super rotations are given by the isomorphism on the celestial sphere. And technically, you can allow for these transformations by just allowing here the leading order in the metric to fluctuate. So you don't require that it's just the metric, the unit sphere metric, but you allow any metric on the 2 sphere, but still you want to preserve the volume form on the celestial sphere. And I like this extension very much because if you are interested by BMS symmetries in ADS, you can find these, the so-called lambda BMS symmetries. And if you take the flat limit of them, then you will precisely end up on these generalized BMS algebra and not on any other extension. And now finally, in the literature, there was recently a proposal of Weil BMS algebra, which is basically this generalized BMS algebra for which you add the virus scaling at infinity. So these virus scaling were already considered in the 2010 paper, but the full analysis of the phase space and the arbitrary fluctuation of the metric were discussed in this very recent paper. And this extension is nice because it naturally arises from the extended corner algebra that is discussed in this reference. Now, since I'm interested by making the link with, to make the link with celestial holography and in particular the celestial CFT, I think the extended BMS algebra is the most convenient to work with because you readily have some conformal symmetries in the asymptotic symmetries, and you have this holomorphic and anti-holomorphic structure appearing directly from a bulk analysis, which is not the case if you are working with the other extension. It's a bit less transparent. And also the expressions for the charges simplify drastically for this extension. So now I will focus on extended BMS.
I have a question.
Yes.
So in the last talk, we saw that these order omega symmetries, or the order omega terms in the expression, they corresponded to some extra diffeomorphism symmetries that were apart from the BMS symmetries. So what would those symmetries correspond to in the celestial sphere in this case? Because in the BMS 4 extended algebra, what would those sorts of symmetries correspond to?
So I think that these symmetries are not visible by this asymptotic symmetry analysis. You have to allow some kind of, as Laurent commented before, some exotic types of vector fields, maybe on the space-time, and then maybe you can exhibit these, let's say, subleading symmetries, but they will not be visible in the standard asymptotic symmetry analysis. I will comment a bit on that at the end of this presentation.
Okay.
Do you have any comments on how you can go from your lambda BMS down to the extended BMS, like how you would try to break something?
Yes, yes. So the problem is that when we try to go from these lambda BMS symmetries, we have to allow the fluctuation of the transverse to sphere at infinity of the boundary metric, and so you end up naturally on this generalized BMS algebra. But if you want to find extended BMS algebra, you have to fix this transverse boundary metric. And the problem is that if you do that, you end up with the conformal symmetries on the boundary. So you end up with a finite dimensional algebra. You don't find the full extended algebra in the limit.
Thanks. More questions, I guess, from, I don't know who was first, if it was Andrea or Andy. Okay, Andy first then.
Is there any argument that if the generalized BMS is bigger than the extended BMS, is there any argument that if you take the quotient of generalized by extended, that there are any non-trivial elements in that quotient?
I would say that, so if I look at the charges that I can compute with for this generalized BMS algebra, there are some part of the superrotation, so which are part of the dFS2, and which are not conformal killing vectors, and that will provide me some non-trivial charges. So I will say that in this sense, this algebra contains more symmetries, because you have non-trivial charges that that you cannot quotient freely. But I don't know if it answered the question.
We can go on to Andrea's question, but yeah, because I guess I'm curious about how this gels with what Kevin's going to talk about, or just more generally like giving an action to like the vector fields that are not actually holomorphic. So maybe that's another advertisement for a future talk. And then Andrea.
So these lambda BMS symmetries, do you have only smooth? Are you considering only smooth vector fields and supertranslation parameters there, or?
So in the first analysis, you can consider only the smooth dFS2, but as you know very well, it doesn't cost a lot to like extend to some meromorphic function on the celestial sphere, and it's useful for the derivation of the subleading soft theorem, for example. So you can actually allow for some singularities.
So even from the lambda BMS that you started with.
From the lambda BMS analysis,
yeah.
Probably you can also do that, but in the analysis that we did, we restricted to the smooth transformations.
I'm asking because the extended BMS, so the singular super rotations are related by a shadow transform to singular dFS2. So now you have non-meromorphic ones, and if what you land on from lambda BMS, if you started from including also singular vector fields, and you would land on dFS2 that also has meromorphic vector fields, then by the shadow transform you can get extended BMS.
Okay, then maybe there is a relation when you allow some singularity for dFS2 that will be yes, interesting to investigate.
And I think this leans us nicely to what Bahar might say, because I know you're dealing with these shadows and effective actions. I'm curious basically about like whether you can have it a boundary term or something that gives an action for this. So maybe Bahar, do you want to ask your question?
I just wanted to ask something off of what Andy was talking about. Will the diff S2 give any other non-trivial constraints beyond the extended BMS?
You mean about the flux balance laws? I would say So my comment was about the fact that you have some charges that are non-vanishing for some superrotation that are in part of DFS2, but that are not in this extended BMS algebra. But
Yes.
I am not sure that they will give some more constraints about the flux balance law, for example. That's
Right.
for sure. But I will comment a bit on the flux balance law and the constraint on the dynamics that you can actually derive from it a bit later.
Okay, thank you.
Kevin?
Yeah, so I think there is a question related to whether generalized BMS or extended, well, whether generalized BMS is a good symmetry group, which is whether the metric on the two sphere should be considered a dynamical entity or not. And from the point of view of the Bondi-Sachs formalism at non-infinity, it's not very clear. Because you don't have, for example, an action principle with well-posed variational principles. So it's not, usually you know what kind of boundary conditions you have to put on your theory by looking at the action principle, but at non-infinity we don't have that. So to me it's still unclear whether the metric on the two sphere can be fully dynamical or not.
Yeah, I guess I'm really curious how, eventually to understand how to get to your effective actions from Romain's lambda BMS or not, what's happening in that flat limit. But maybe this is more of an advertisement for your talk, Kevin, later, and also lovely paper by Romain and Laura I should advertise. So.
Okay, so thank you for your comments. Just to say that here also the advantage of generalized BMS is that you can have the super rotations, but which are smooth on the celestial sphere. Of course, you can extend it with singularities, but still there is a. If you are interested by smooth symmetries, this is, I think, a nice extension. Okay, so now what you can do is to compute the variation of the solution space under the action of the BMS symmetries in the bulk. So you obtain that by just acting with a Lie derivative on the metric. And you will get the following variations. So here is the variation for the asymptotic shear, here for the Bondi news, the mass, and the angular momentum aspect. And something that you can notice here is that the Bondi news does not transform homogeneously under super rotations. So there is the appearance here of a Schwarzschild derivative, which means that the condition that the Bondi news vanishes is not invariant under super rotations. Now the question that I'm going to address is how to define non-radiative spacetime in presence of super rotations. And as I'm going to argue, you need some refinement for the definition of the news to encode these super rotations, the consistency with them. So the proposal is here to define this physical news, which is given by the Bondi news, from which you subtract the value of the news in the vacuum, which is given here. And this NAB vac is expressed in terms of this field, phi, which is called the superboost field. And this field is important because it can be shown to encode the refraction and the velocity kick memory effects. And why do you call it superboost? Because if you start with a solution where phi is set to 0, then this field will be turned on by boost. So and their super rotation generalizations, which are called superboost, namely the super rotation for which YA is not divergence free. Now this NAB vac can also be interpreted nicely as the trace-free part of the stress tensor of a Liouville theory living on the celestial Riemann sphere, and which is given explicitly here. And another interpretation of it is that it can be seen as the trace-free part of the Gurock tensor that was introduced in his 77 review. Now, when you take this definition for the physical news and you take this variation of the superboost field into account, you can show that the physical news will transform homogeneously under the action of BMS symmetries. And so this means that this is a good definition of physical news in presence of superrotations. And in particular, the condition NAB hat equal to 0 is invariant under superrotations and will define for us non-radiative spacetime in the following. Now, in addition to the follow-up in R that I provided at the beginning of the talk, you can also impose some follow-ups in U that will be important. And so these follow-ups are imposed at the corner of scribe, so at scribe ++ and scribe ±. And basically, you require that NAB and CAB takes their value in the vacuum around the corner of scribe. So NAB, the Bondi news, is just the value of the news in the vacuum, and CAB takes this value, which involves these fields, C+ and C-, which correspond to the values of the supertranslation field at scribe plus and scribe ++ and scribe ±. And you can show that it encodes the information about the displacement memory effect. So these follow-up conditions in U are compatible with the action of the superrotations on the phase space. And as I will also argue later, they are necessary if you want to have some BMS fluxes that are finite in U. And these objects will be important to make the link with the Celestial CFT. So just these boundary conditions in U basically tells you that you don't have radiation at the corner of scribe. So NAB vac is equal to 0. And it also tells you that CAB is electric. So it satisfies these conditions, which is the generalization of the electricity conditions, but in presence of superrotations.
Sorry, Romain.
Yes.
Why do you exclude a term like 1/U in the shear?
Yes. So basically, this is to have some finite BMS fluxes, because then at some point I will make an integration over U from -infinity to +infinity. And if I want to have a well-defined expression, then I have to impose these follow-ups, which are a bit stronger than some follow-ups that were previously considered in the literature. So it's essentially to fill in this criteria.
But you can show that this excludes actually very important solutions.
Yes, precisely. So these follow-ups a bit stronger actually were discussed in this paper. So you are like excluding some tail memory effects. But still, this is the follow-ups that I need to introduce the BMS fluxes that I will talk about later. So it depends on what you want to do, but if you want to define the fluxes and have some finite expressions, then I have to impose these a bit stronger follow-ups in U.
How much flexibility do you have in the definition of the fluxes in the case of like basically with the soft theorems, we would normally like integrate by parts or some add like in a way to basically shuffle around boundary terms so every integral over U is well defined. Do you have like an intrinsic definition of the BMS flux for U, or just the fact that it's like this U integral?
Yes. So exactly. So I will go into much details in the following. So I will provide all the possible ambiguities and so on.
Sorry, just one comment here. So if you have a total mass in the system, in the bulk, then if you have any kind of radiation, the interaction between the radiation and the total mass generates a tail term, which goes like 1/U. So as soon as you have radiation and a total mass, then you will have solution, which goes like 1/U. So excluding this 1/U term means either excluding total mass in the system or radiation. So this is kind of tricky to do. So
I'm not sure I agree with, but so these follow-up conditions were considered in this paper, and there they are actually like providing which restriction you impose on this on your phase space. And but for what we are doing, I don't have choice. If you want to include super rotations and define some fluxes, and I don't see any obstruction to define some mass in this case, but maybe we can discuss a bit more about that later.
Yeah.
But I don't see any.
Yeah, it's explicitly written in our paper about, I mean, harmonic gauge to BMS gauge. You can check that, but
Sure, but in principle, if he's able to capture the mass loss flux law, like for the leading soft
Yes.
theorems, I would have thought that would be exactly where you're saying there's an issue.
No, I mean, if you solve Einstein equations, which you can do in the bulk, assuming you have some source, and it's typically done in harmonic gauge. And when you transform it to Bondi gauge, you see that tail terms go like 1 over u. And that's
but like the tail that you're getting should be literally like in what he's going to show is like the algebra that corresponds to the leading soft theorem, for instance, like as far as like bonding mass changes from the initial and final scattering states are captured by some sort of zero mode of part of the news, and he should be able to reproduce that. So I would have thought that would have been giving you your tail that you have an issue with.
Yeah, maybe we can discuss it later. Thank you.
Okay, so this ends my review about the solution space of asymptotically flat spacetime in 4D gravity. Now I would like to discuss a bit how to construct the charges from this solution space, which are associated with the BMS symmetries that I've introduced. And to do so, you have to consider this symplectic structure at Scribe plus, which is a 2 form on the solution space because it involves 2 variations of the metric. And it involves the Bondi news and the asymptotic shear. The problem is that, again, in presence of super rotations, you have some issues because there will be some divergence in R if you compute the symplectic structure from covariant phase space formalism. And so you need a renormalization procedure to remove these divergences. So let me say a bit more about it. If you start with your bulk Lagrangian, say the Einstein-Hilbert action, and that you take a variation of it, then you obtain a term which is proportional to the variation of the metric times the Euler-Lagrange equations, which correspond in this case to the Einstein's equation. And to make this term appear, you have to integrate by part. And this defines you what you called the presymplectic potential here. But of course, this object is defined up to an ambiguity here that is called sometimes the corner ambiguity. So this is an exact form on the spacetime. And the key of this renormalization procedure is to play with this ambiguity to remove the R divergence. So basically, the symplectic structure is obtained by taking one more variation of the potential. And then this symplectic structure is defined up to the ambiguity as follows. And you can show that you can remove the R divergence using this Y. And you get finally this result. Let me also mention that there is another way to get this finite result for the symplectic structure at Scribe plus is to go in ADS and then to use the holographic renormalization procedure to remove the divergence in the symplectic structure there. And then you can take consistently the flat limits to recover the symplectic structure in asymptotically flat spacetime, which means that this whole renormalization procedure here is reliable. Now to write this symplectic structure here, I threw away some terms which are proportional to the variation of the boundary metric. So basically these terms will be singular on the celestial sphere. So they will vanish everywhere on the celestial sphere, except at the poles where you have these singularities associated with super rotations. And therefore, in principle, you should have to keep track of these terms in the derivation of the symplectic structure at null infinity. And the full expressions reads as follows. However, in the following, I will just discard these terms proportional to the variation of the boundary metric. And you can make sense of that rigorously. Either you can work locally out of the poles of the celestial sphere, And so you don't really care about these singularities at the poles. The other way to proceed is to change the topology of the celestial sphere. And for example, work on this two-punctured Riemann sphere where you remove the problematic points where the singularity arises. And in this case, you can make sense, for example, of integration on this celestial Riemann surface. Okay, so now the way to derive the BMS charges is just to contract the symplectic structure at infinity with the BMS symmetry. And there is a very general result in the covariant phase space formalism that tells you that this is an exact form on the space-time. So this is just a statement basically that the charge in gravity will be surface charges and not volume charge. And now the gravitational charges are just obtained by integrating this codimension 2 form, which is a 2 form in 4 dimensions, on a cut of scribeless, so which is at finite value of u. And then the result that you get is a non-integrable expressions, which is given here. And so here, this object is still a 1 form on the solution space because it involves a variation of the metric. And non-integrable means that you cannot write this expression as a delta exact term. So here is the explicit expression for the integrable piece and the non-integrable part. But of course, you have an ambiguity in the splits that you choose between integrable and non-integrable piece. So you can always shift your integral part by some quantity and then subtract it in the non-integrable part by the same quantity, so that the full object here, which is the object that really makes sense, is not affected. So later I will provide additional criteria to isolate a meaningful integrable part in the charge. But for the moment, I will stay with this non-integrable expression at finite value of u. And indeed,
I have a question.
Yes, yes, sure.
So what symmetries actually do these charges generate, the BMS symmetries?
Yes, yes. These are just the BMS symmetries, so the extended BMS symmetries that I introduced before.
Oh.
And so basically you can explain this non-integrability because you have some gravitational radiation going through null infinity, and you see that it appears in this non-integrable part. So the point of keeping the whole non-integrable expression is that it allows you to write some charge algebra at finite value of the retarded time u, and from which you can derive some flux balance laws that are very important for describing the dynamics of the system. And so you have to use to write this BMS algebra the so-called Barnish-Troussard bracket, which is defined as the standard bracket for the charges. It's also called the Peirce bracket, plus a modification that takes into account the non-integrability of the charges. And if you use this modified bracket for the charge, you can show that the BMS charges will form a representation of your symmetries up to a cocycle that appear in the right-hand side. So this cocycle, you can show that it is field dependent because it depends explicitly on this asymptotic shear that I introduced before. And it satisfies what is called the generalized two cocycle conditions here, which allows you to make sense of these brackets. So you can show that this implies that this bracket satisfy a kind of Jacobi identity. Now the interest of this technical results, this charge algebra, is that you can derive from it some flux balance laws. So if you take in this algebra Xi2 to be just a time translation, which is part of your asymptotic symmetries, and Xi1 to be a generic BMS transformation, then you can show that this algebra implies the following flux balance law, which tells you how much the BMS charges is not conserved due to the gravitational radiation that goes through the null boundary of the spacetime. And in particular, if you specify this flux balance law to the time translation, then you precisely recover the Bondi mass loss formula that I presented at the beginning of the talk, which means that these flux balance laws contain some very important information about the dynamics of the system. Now let me comment a bit more about this result of charge algebra. First, you can show that this Barnish-Trussard bracket, the fact that it closes does not depend on the particular splits that you make between the integrable and the non-integrable piece that I mentioned here. So of course, if you make a different choice, it will affect the value of the cocycle here, but it will not change the fact that the bracket will close up to a field-dependent cocycle satisfying this condition. The second comment that I want to make is that this cocycle is it vanishes when in absence of superrotations. So you have this cocycle only because you are considering superrotations, but it will not be there if you restrict to Lorentz transformations. The third point is that this cocycle cannot be reabsorbed by playing with this ambiguity in defining the integrable part and non-integrable part, which means that it really plays an important role in the physics that we are describing. And finally, let me mention that if you don't like this story about field-dependent cocycle appearing on the right-hand side, you can actually refine this definition of modified brackets. So that was done in this reference. And using covariant phase space formalism and particular splits between integrable and non-integrable p's that correspond to the Noetherian splits, then you can actually reabsorb this cocycle in the definition of the bracket and having an algebra that represents your symmetries. Okay, so now let me address the question if there exists a preferred integrable part, how to isolate it. That's the question. So there is a long story to find what are the right BMS charges that has appeared in the literature. So first, in the derivation of the soft theorems, it was shown that it was necessary to consider particular prescriptions that generates canonically the transformations on the phase space. And then later, this prescription was refined a bit by including the consistency with the action of superrotations on the phase space. And finally, we end up with this result here, which is, up to my knowledge, the most up-to-date prescription of charges that we have for the BMS symmetries. So here, these are the super translation charges, and these are the superrotation charges. And the explicit expressions are provided here in terms of the solution space that I introduced before. So the interest of these charges is that they have some nice properties that I'm now going to discuss. First, they vanish for vacuum solutions, namely solutions that are in the orbit of Minkowski space by acting with BMS transformations. The second interesting criteria is that the flux associated with these charges vanishes if you turn off the physical news. So it's just a statement that the BMS charges will be conserved if you don't have any radiation going through Scribeless. So this is a reasonable physical requirement.
I have a question.
Yes.
So here, you're working on the celestial sphere, but you're not doing any sort of Mellin transform or things of that kind, right?
I am not yet really working on what is called the celestial sphere, in the sense that I'm working on a cut of scribe plus at finite value of u. To get some objects that will be defined on the celestial CFT, you will have to make an integral over u, actually, which in a sense is a bit the equivalent to make a Mellin transform. So I will define these objects a bit later in the analysis. But for the moment, I'm at a cut of scribe plus at finite value of u.
Okay.
Excuse me, sorry, I have a question.
Yes.
I'm sorry if this is a naive question. I just want, so this is regarding point 1, the charges that vanish for vacuum solution. So if I'm not wrong, so the Compier-Long paper as well as yours paper in 2018, so there are some transformation of NAB, the CAB vac. So the vacuum shear transforms under super translation. So the Goldstone boson mode C, so it transforms under the super translation vector field. So suppose if the charge vanishes for them, so what are the what is it that generating those transformation? I wanted to know that, like, there has to be some charge so that you get some symmetry transformation, right, on your fields. So how are you getting those symmetry transformation on suppose your Goldstone boson mode C?
Yeah,
Or
that's
CAB
yes,
vac.
yes. I see, understand your question. So to precisely answer to that, I think you would have to know a bit more about the phase space in presence of these vacuum contribution in the charge. So you need to have the commutation relations between NAB vac and the super translation field to actually know how to generate the transformation on the phase space. But I agree, in this case, then it is difficult to see how they will actually generate the transformation on vacuum solutions.
Isn't it the point that to generate transformations, you need the off-shell charges and the off-shell brackets, which are not zero? I mean, these are operators.
What do you mean by off-shell charges? Because here everything is on shell.
You're not evaluating it on a specific solution, but you keep all the fields like arbitrary.
Ah, yes. So yeah, it's a good point. So the fact that you can start with a vanishing charge and then generating something non-vanishing, this is what you...
Well, it's the opposite. You to generate the transformation, you need the off-shell charge, which never vanishes because it's just an operator. But then when you evaluate it on some solution, it can be zero.
Yeah, no, probably that's what's happening for the vacuum. So you have to consider like the full charges, and then it will generate like the orbit of Minkowski because they are non-vanishing for generic solution. They vanish on vacuum, but probably not on yes. They are non-zero on other solutions. So yes, that could be the explanation. So okay, so let me come back to the criteria of these charges. Let me just mention the fourth point that will be interesting for us is that this charge actually, and this is a very important property, that they will form a representation of the BMS symmetries at the corner of scribe. So at scribe plus plus and scribe plus minus. So you will not have any field-dependent cocycle here on the right-hand side. And furthermore, you just need the standard brackets to have this representation. You don't have to use the Barnish-Troussard bracket. So you see that the things simplify drastically when you are looking at the corner of scribe. So now I will define some objects that will be very important for us for the Celestial CFT analysis, which are called the BMS momentum fluxes. And so first you defined the super momentum flux by integrating the flux of mass on U from minus infinity to plus infinity. So this is here that I need this this fall-off in U to have finite charges. And so it will be defined as the difference of charges between square plus plus and square plus minus. And similarly, you can define the so-called superangular momentum flux as the difference of angular momentum between square plus plus and square plus minus. The total BMS fluxes are obtained by integrating these expressions on the celestial sphere and by contracting them with the symmetry parameters, so the BMS parameters. And so here there is a factor 2i pi because basically to make sense of these integrals over the celestial Riemann surface, you will need some residues into the definitions. And so the 2i pi factor will appear naturally in this context. So this F here, so the BMS flux, is physically very important because it encodes the total flux, which is radiated through square plus for the whole story of the universe. And as a consequence of the closure of the algebra that I presented here, you can show that these fluxes will also form a representation of the BMS symmetries. So without any central extension, and you just use the standard definition of the bracket. You don't need to modify it. Stated differently, you can write this result in terms of the BMS momentum fluxes that I introduced before and that enter in the expression of the flux. This means that they will transform in the following way here. So the transformation of the supermomentum flux tells you that this is a Virasoro primary under the action of super rotations, which has weights 3/2, 3/2. And the super angular momentum flux will transform in the following way under super rotations, which means that this is a Virasoro primary of weights 1, 2. And there will also be a contribution in the transformation that comes with the super translations. The way to understand this part is that when you have the angular momentum for a solution and that you perform a translation in the space-time, then basically this angular momentum will transform with the cross product between the translations and the linear momentum. So this term is just like the generalization of this transformation, but for the full BMS symmetries and super translations. So these terms have to be there. Now, let me just mention that this transformation actually corresponds to what is called the quadrant representation of the extended BMS algebra, which was derived recently in this paper, which means that you have a natural momentum map between the dual of the BMS Lie algebra and the solution space of 4D gravity in asymptotically flat spacetime. And this momentum map involves these momentum fluxes that I introduced here and that have a clear interpretation in terms of the dual of BMS algebra, which means that they are the right objects to look at. They have nice properties transformations. And they will be important for CFT. Yes?
I have a naive question. So once you have these BMS generators, can't you kind of define a theory which will whose fields will have representations in terms of, I mean, which can be represented in terms of, which will carry representations of these algebras or these operators or these charges, so that the resultant theory of those fields will correspond to the dual theory that you need for the holography to work.
Yes, probably these objects will play a role in the construction of the representation. They might play a role. That's an interesting thing to study. For example, by classifying the quadrant orbits could be a good question to ask, because it could be related to like the unitary representation of the BMS symmetries, and this representation might play a role in the context of celestial holography. That's for sure.
Yeah. Yeah. Okay.
Okay, so now this result about the closure of the flux algebra can be stated in terms of these BMS momentum fluxes through these commutation relations. So you can already see these commutators as algebra in the Celestial CFT, because these objects here that I've introduced, the BMS fluxes, are really objects living on the Celestial CFT. They are not any more objects at finite value of u. You have integrated over the u coordinate. So they are objects living in CCFT. And these commutation relations will be important later for us because they will allow us to derive the operator product expansion that will constrain the CCFT. Now, in this paper, in collaboration with Laura Donnet, we studied if there was a good split between hard and soft parts of the fluxes that I've just introduced. So basically, the hard part of the flux involves a quadratic term in the news, the physical news, and the asymptotic shear, and the soft part involves linear terms. But there is still an ambiguity here because you have some vacuum contributions in the fluxes, and so there is a kind of freedom to split between hard and soft part in the flux. And the way that so we propose these prescriptions, and the motivation is that with these particular prescriptions of the split, both the hard and the soft part transform separately in the quadrant representation. So they will, if you split the flux like this, they will transform separately in this representation that I've introduced here, which tells you again that these are the right objects to consider from the point of view of the symmetry, the action of BMS symmetries in the bulk.
Is that guaranteed once you write all of those like combinations in terms of well covariant derivatives of like right, there's like two descendants and then etc.
Yes, actually, I will just go to that to my in my next slide. Yes, just to make a comment that this split is consistent with the one that was proposed in the literature to study the soft theorems. There are just some vacuum contributions that are different. So when you set NAB vac to 0 and the super translation field to 0, you recover precisely the expression. So in this sense, yes, you recover all the results that you are used to. But indeed, you can introduce a derivative operator in this context, which involves this superboost field, and which allows to rewrite these a bit complicated expressions of the fluxes in a more compact way, and which makes this structure of descendant a bit more transparent. So this operator is curly D here, is defined as the covariant derivative plus some shift here related to the superboost field that I introduced before. And this operator was first introduced in this paper, and it was called the superrotation covariant derivative. And it was also considered in this paper from different considerations, where it was seen as a Weil covariant derivative on the celestial sphere. But in this context, these operators coincide, and they take the following form. And they have the nice property that when you act on Virasoro primary with them, you recover Virasoro primary, where the weights are just shifted by 1 unit. Now, using this derivative operator, you can rewrite the soft part of the fluxes in a very compact way. And for example, the supermomentum flux is just two action of this derivative operator on the so-called leading soft mode of the news, which was important in the derivation of the leading soft theorem, And similarly, the super angular momentum flux is can be written in terms of the subleading soft mode of the new tensor, which was again important in the derivation of the subleading soft theorem. And there are also some contributions coming from this super translation field, and they allow to have the nice property transformations that I mentioned here.
By subleading, do you mean the order omega terms? No.
But by subleading, I mean subleading soft theorem. So yes,
order omega
expansion of omega that Andrea
Omega
told
to the 0.
Yes.
Okay.
Okay, so now I would like to make the link with celestial holography and the celestial CFT considerations that we are used to. And in this context, you can actually write some CCFT word identities that encode information about the bulk soft theorems. And to do so, you need to introduce some currents in the analysis. So for example, you need this super translation currents, P, which has weight 3/2, 1/2, and which is necessary to write the word identities for super translations. And basically, when you plug this super translation current in a correlator, it will produce a pole in 1/z, as Andrea explained, and it will also shift the weight in the conformal field on the celestial sphere. So it's just a way to recast the leading soft theorem on the celestial CFT. Similarly, you can write the word identities associated with the super rotations in CCFT by introducing this 2D stress tensor. And so this is holomorphic and it has conformal weights 2, 0. And when you plug it into, you insert it into a correlator, it will produce this word identity, which is just the word identities of a 2D CFT. And it encodes the information about the subleading soft theorem in the bulk. So now the question that I would like to address is, what is the relation between the celestial CFT currents that you are using here to write these word identities and the BMS momentum fluxes that I have introduced before and that have nice property transformations under the actions of BMS symmetries in the bulk? And how to deduce some constraint on the celestial CFT from the BMS flux algebra that I presented before. So the first stage is to relate these BMS momentum fluxes with the celestial CFT currents. And you can define this super translation current P here in terms of the super momentum flux by using the covariant derivative operator that I introduced before. And similarly, you can define the 2D stress tensor using a contour integral on the celestial sphere. And you can define it from this super angular momentum flux that I introduced before. Let me mention that these definitions of CCFT currents differ from those that were used originally in the literature, again, by some vacuum contributions. So when you set them to 0, you recover the standard definitions, but you need to include them, again, to have the right properties transformations of the objects under the actions of BMS symmetries in the bulk of the spacetime. So now, besides these nice properties transformations, there was a conjecture that was made recently in the literature that it could actually have an impact on soft theorems to consider these refined definitions of the CCFT currents. And in particular, it may appear that this stress tensor defined from the superangular momentum flux that I derived could reproduce the subleading soft theorem at one loop. So usually when you are just considering the the standard definition for this stress tensor, you get the, let's say, the 3-level subleading soft theorem, but when you start from the word identities, but this theorem gets a one-loop correction. And the hope is that by using this covariant definition, you could reproduce the one-loop correction. So this was a conjecture made by Sabrina, and I also, Kevin made a remark about that. So I think that would be very nice to derive this result, if it's true.
Yeah, I think it's really beautiful because basically, like, think about the work that like Prahar and et al. And Andy had to do to get the, sorry, I guess I shouldn't comment like that, to get the one-loop correction to show the algebra was still there. And basically you're seeing that from your covariant derivative point of view. And like, yeah, if you can match the coefficients with what I was doing with Herman, it'd be lovely. So yeah, sorry.
Yeah, that would be a really nice story because this will justify all this technology of introducing these corrections to the covariance. And I would really like it.
I love it, yeah.
Okay, so now from the BMS flux algebra that I discussed before, which I wrote here in these commutation relations, you can deduce the OPE on the Celestial CFT. So here are the OPE of the BMS fluxes, and you can also derive from it using the definition that I introduced here of the CCFT currents, the OPE of these objects. And these OPEs were obtained from different roads by using, in this paper, some scattering amplitude methods. And so it's very nice to see that by taking this road coming from the BMS flux algebra and the bulk analysis of the phase space, you can recover these constraints on the Celestial CFT. Furthermore, you can also write some OPE with conformal fields on the celestial sphere with these BMS fluxes, and you find these OPE here. And in terms of the Celestial CFT currents, these OPEs we read as follows. And they contained information about the word identities that I wrote before, because basically with this OPE, if you insert these super translation current and this stress tensor into some correlators, then you reproduce exactly the word identities of the Celestial CFT that I discussed before. So the whole story is completely consistent. So now let me maybe conclude with some general comments about what I've said, and also I would like to draw the general picture of this presentation. And I think that it can be summarized by presenting the two complementary visions that you can have on Scri+. So you have two pictures. Either you see Scri+ as a boundary along which there is a time evolution with respect to the retarded time. And in this picture, it is particularly well adapted to describe the dynamics of the system through some flux balance law, such as the Bondi mass loss formula that I described before. And in particular, you can interpret the Einstein's equation that constrain the evolution of the mass and the angular momentum that I introduced before in the solution space of gravity, really has time evolution equations along Scri+. In the second picture, you can see Scri+ as a portion of Cauchy slice in the space-time that you push to infinity. And this picture is particularly interesting to describe the state of the system rather than the dynamics. And in particular, it is well adapted for the scattering problem. So basically, you provide the state of the system at Scri-, then you let the system evolve and the scattering process happening in the bulk, and that you get the out state or the finite state at Scri+, and this defines the scattering process in asymptotically flat spacetime. And this was this picture that was taken, for example, to derive the soft theorems from the word identities. And in this case, you can see the constraint on the mass and the angular momentum as constraint equations rather than time evolution equations. Furthermore, in the first picture now, you are interested by non-integrable expressions because you are interested at what's happening at finite value of the retarded time. You want to write some flux balance laws, and you have to deal with this Barnish-Troussard brackets that I introduced, and that allows you to write this BMS algebra from which you can derive the flux balance laws describing the dynamics of the system. In the second picture, as I showed here, the relevant objects are the fluxes. So you have to take the integral over u. You don't really care about what's happening at a finite value of u. Or you can also talk about the charges at the corner of scry. And in this case, you don't need this notion of modified bracket. You can just use the standard Lie bracket, Dirac bracket for the charges to write your flux algebra. And so this first picture here suggests a 4D bulk, 3D boundary flat space holography duality, where the dual theory would live on scry plus and will be a BMS field theory. So this is a bit reminiscent of what's happening in ADS CFT, for example, where the dual theory is living at the boundary of ADS, which is codimension 1. And you also have a time evolution along this boundary. So you have a similar picture here. And let me just say that in the second picture, this is more natural to suggest a 4D bulk, 2D boundary celestial holography, which is the subject of this workshop. And in this case, as I've tried to argue, the dual theory will be a 2D celestial CFT. Yes, I see there is a question.
Yeah, I'm wondering why we should expect a 3D field theory. I mean, it's different than ADS because in ADS, things don't go through the boundary, they bounce out. So we kind of know that there can't be an evolution. I mean, we couldn't have a state. It would be a field theory. It wouldn't be a quantum mechanical field theory, right? There couldn't be a Schrodinger equation. We can't have a state that evolves along scry. So if it is a field theory, it would be one with a random source, or I don't know why. Yeah.
So maybe I can just comment, in ADS, we can actually impose some boundary conditions that allow some fluxes going through the boundary. And indeed, in this case, this flux is there because you allow the sources to fluctuate in the phase space. And I think there is something very analogous happening here in asymptotically flat spacetime. And it's true that this theory will probably not be unitary, but it should be maybe thought about as a theory coupled to some external sources where the charge are not conserved and you have a non-unitary evolution. So the things will be a bit more complicated, but I think that there might be a way to make sense of this duality. But it will not be like the standard ADS CFT, where you are selecting some, let's say, bouncing boundary conditions, where the gravitational waves are not allowed to leave the spacetime. Yes. So since I'm talking about symmetries in Celestial CFT and about algebra of currents, let me mention that very recently, there was this proposal of W infinity symmetries that are symmetries of the gravitational scattering and that have been uncovered in this Celestial CFT picture. And probably as Atul will tell us more about that, they naturally arise in the Twistor space as symmetries of self-dual gravity. And the nice thing is that this symmetry survive beyond the tree level, which means that they should be taken seriously to constrain the Celestial CFT. And the question, of course, that I am interested in is where are these symmetries in the gravitational phase space? I think this is a legitimate question to ask. And there was this recent proposal by these authors here that proposed that these symmetries might be encoded in the subleading order expansion of the solution space. So basically in the psi0 component of the Weil tensor. So probably Anna Maria will tell us more about that in her talk. So I would like to say that these symmetries might be crucial to find the right candidate for the CCFT, and I'm looking forward to hearing more about that in this workshop. Okay, so this is all what I wanted to say. So thank you very much for your attention.
Let's thank Romain. I really found that very interesting, and I'm sure we all did. If there's any more questions, I'll leave the recording on until they're answered. Otherwise, I'll break for lunch. Okay, well, welcome back to the afternoon session of the Celestial Holography School for Celestial Holography 2022. We're very happy to continue our foray into different subfield expertises, or whatever the right word is for that, coming into Celestial CFT. And so the first session for this afternoon is going to be Emilio Trevisani, who I've had the pleasure of working with, telling us about CFT for CCFT. Take it away.
Thank you very much for this opportunity and also for the organization of this beautiful event. And also it's a pleasure to give a talk after these beautiful lectures that we already had. And I think I will use a bit of that. So it will be also based on the 2 lectures that we had before. So as Sabrina said, this is based on CFTs for Celestial CFT, this lecture. The plan is going to be very basic. So the first half of the lecture will be on just CFTs. And I want to define them like axiomatically and get to this bootstrap philosophy. And so I want to introduce in practice this idea of the bootstrap. And then I want to go to the Celestial CFT side and see what the bootstrap, or how this fits into this bootstrap language. So let's say how to define some axioms for the Celestial CFTs, and this will give rise to some questions, and I hope that it will be interesting. So this is a plan. If we want to do something axiomatically about conformal field theory, the first thing that you should do is analyzing the symmetries. So in this context, I'm actually working mostly in CFT in D dimensions for a couple of reasons. Well, one of the reasons is because the bootstrap is actually typically defined in generic dimensions. And the other reason is because I think also most of this story will work also for Celestial CFTs, but in different dimensions. So that's just the reason, but then I will have some comments on 2-dimensional cases. So let me start by the generators of the symmetry. Well, you have translations and rotations, well, or some, depending on the signature of your CFT, if you are in Euclidean or in Minkowski, you could have Lorentz. So these 2 are the usual, form the usual Poincare algebra. And of course, translations are, as usual, just derivatives, and okay, rotation are also the usual generators. What you have extra when you consider conformal symmetry is scaling symmetry, which is generated by this dilation operator, and this other weirder generator that is a special conformal transformation generator, which can be thought as an inversion and a translation and another inversion. So the idea of this transformation is like, this is doing something similar to translations, but while translations are moving all points, in particular the origin, and it's fixing instead infinity, this special conformal transformation is doing the opposite. So it's fixing infinity and is moving the origin. And here also, well, I didn't say it, but all these indices, these Latin indices are just indices from 1 to D. And you can then write the algebra for these generators I didn't want to write everything down, but you can find it in books. But the important part that I think I may use later is just these two commutation relations of the dilation with translation and with special conformal transformation, where you see that they form some sort of ladder algebra in the sense that D gives the commutator with of D with P gives you back P, but with a plus sign. Well, the one with K, it gives a minus sign. And so this is gonna play a role. Okay, so symmetries, the way I presented here, the symmetries, they look a bit cumbersome. There are many generators and many commutation relations, but there's a trick that is very useful, and it's also very useful in the story of Celestial CFT. That is the fact that actually the symmetry of the conformal field theory in the dimension is actually a Lorentz symmetry in D+2 dimension. So in other words, the symmetry of a CFTD is just SOD plus 1, 1. Well, this is in Euclidean. And how do you see it? Well, there's a simple trick to do it. You just repackage all the generator in a single matrix that is antisymmetric. So it's this one. And this matrix, so it's just a single set of generator J mu nu, where now these indices run from 0 to D+1. So there are two extra directions. And these generators satisfy the algebra indeed of just Lorentz algebra. And so this is going to be really important because we are going to consider quantum field theory in D+2 dimensions, and they just have Lorentz symmetry. And we want to interpret that Lorentz symmetry as a conformal symmetry in 2 less dimensions. Okay, so now we define the symmetry, and the next step is to study the operator content of your theory. And so you want to have some local operators, and you want to classify them in order to have some nice operators that transform well under the conformal symmetries. In particular, you care about operators with definite scaling dimensions. So this is the relation where the dilation just measure delta, that is the scaling dimension of the operator, and with some definite spin. That in general in SOD is, well, it's an SOD spin, but for this talk, we can think just about some tensor that are symmetric and traceless with J indices. And we will call these as spin J operators. Then beside these, it's also important to get back to this algebra that of K and P with D, and noticing again this ladder structure that tells you that in practice, if you start by some operator here, I'm writing this axis that measure the dimension of the operator, and you see that by acting with P, you're increasing the dimension of the operator, while by acting with K, you're decreasing. So it's natural to assume that this should end somewhere. Otherwise, you would have infinitely many. I mean, let's say that your spectrum will not be bounded from below, and so you typically assume that you have some primary operators that are just killed by K. And so this would be the case where this is your primary, and if you act again with K, you just go to 0. And then there are the descendants that would be all these other points that there are infinitely many, and you can write them in this way. And it's also important to notice that this structure is nice because descendants are really simple, are just derivatives acting on primaries. So if you know the primaries, it's very easy to know all the descendants. So we call the spectrum of the theory the full set of primary operators, and so these are classified by indeed they're just a dimension and spin. So now, since we define the operators, we can go back to this idea of symmetries and revisit this idea. So it's important to notice that axiomatically in CFTs, there's a different way to approach symmetries with respect to what you do in quantum field theories. So in quantum field theory, you start by the Noether theorem. And so you have your action that is actually the input of well, at the starting point, and you just study the symmetries of the action. And you know that if you have a continuous symmetry, you should have some conserved currents. And in this axiomatic language, instead, we start by a different point of view where you don't actually have the action. You have this set of operators, so you have a spectrum. So why symmetries should be there? Well, symmetries are actually imposed in a different ways because you impose the existence of some currents. And so these and the conserved currents will give you these, well, continuous symmetries. And there are, well, two examples that are quite important. For example, in dimension bigger than 2, we say that it exists one operator that is called the stress tensor that has 2 indices. So it's a spin 2, and it has dimension d. And it has some word identities, or if you want, if you drop contact terms, I mean, you have this conservation equation for the stress tensor. And so through this definition, you can actually build all the generators that I was defining before by just integrating the stress tensor against, okay, you have some vectors that are just, okay, the conformal killing vectors. And here there's some surface. So it's just an integral of the stress tensor. So in the end, we don't have to impose the existence of these generators. We can actually just impose the existence of the stress tensor and they come for free. And okay, here there's the basic example that is in any quantum field theory book, that is the just translation, that is the integral of the stress tensor with this free index. And there's the same case in 2 dimension, which is a bit more rich, as you well know, probably, where the stress tensor now, I write it as T of Z because I use complex coordinates. Also here, the indices M and N would be in direction 1 and 2, but we can consider direction 1 plus I2. So some direction that I would call Z, Z, or Z bar, Z bar, and they give you some holomorphic and anti-holomorphic components for the stress tensor. And and this that would be the holomorphic one has some spin equal to 2, and it would satisfy this conservation equation. And from that, you can build all the generators. But once you do that, okay, there are some differences between this case and this case. So in particular, well, the simplest thing is that, okay, this surface now it's in 2D, so it's just a circle. So this will be a contour integral. And the other thing is that there's actually an infinite basis for this vector. And this is parameterized by this Z to some power. And so you have a generator for each power of Z. And these are called LK and are the Virasoro generators. So if you take L-1, L0, and L1, they are actually, and their anti-holomorphic counterpart, you just build back the same generators that were in there also in D bigger than 2, but you now have an infinite enhancement. And okay, this is the full algebra, the Virasoro algebra that they satisfy. And so this slide was just to say that it's the role of symmetry in CFTs is a bit the opposite. So we start by imposing the existence of some currents. So that's our starting point to define symmetries. Now, observables. Which are the observables of a conformal field theory? So the the most, well, I would say the most important ones are the ones of local operators, correlation function of local operators. And these ones are strongly constrained by conformal symmetry. In particular, if you write one-point functions, they are just completely fixed by conformal symmetry to be 0, unless you have the identity operator, and in that case, you just get 1. Then the 2-point functions are also fixed by symmetry in this way. So you have this power of delta, that is the dimension of this operator, and the 2 operator must have the same dimension. Also, I'm writing from now on this x12 or xij is just a difference of the 2 points. Now, when you go to 3 points, you see that again, this is fixed in terms of the dimension of the operators with these powers, but now you have a new ingredient that is this overall constant, is a normalization, if you want, for this 3-point function. And this coefficient, you call it OPE coefficient or 3-point function coefficient. And then you can go on and study higher point functions, and they will not be completely fixed by symmetry. In particular, if you study a 4-point function and consider 4 equal operators, well, scalar operators, you'll see that conformal symmetry tells you that you have an overall factor that is fixed to have this form times a function of u and v that are this cross ratio. So which are conformal invariant. And you can also write them in terms of z and z bar. This is just a different parameterization.
Can you make one comment for the sake of when people are, I think there's going to be some talks later on in the workshop where people are going to address like shadows versus Mellin transform amplitudes, where basically there would be singular terms that still satisfy the same constraints from conformal invariance. Could you say something to the extent that normally you just completely would exclude it in the yellow book, for instance? Like, for instance,
you mean delta
contact
functions?
Exactly.
Yeah. So
the phrasing for why you don't normally consider them would be lovely to just add here so that we can.
Well, I was thinking to get back to that question later when I go to Celestial CFT, but in general, let's say that well, no, it's better to talk about that later.
Sorry,
yeah.
Great.
And okay. So now there's another important, well, really important axiom, if you want, is the presence of an OP, operator product expansion. That is just this statement that if you have a product of 2 operators, you can actually replace it as an infinite sum, well, or a sum of single operators. So this sum runs over all the operators in the spectrum. And you see that you have some OPE coefficients here. So these indeed were the ones that we saw here. So they are the same coefficient that you find in the 3-point functions. And then there's some differential operator that depends on the difference of x12, and it has derivatives on the x2. So in practice, it's kind of creating descendants. And so the important thing is that this object is completely fixed by symmetry. So it's just kinematical. So here, the only information that is dynamical is the spectrum in this sum and these OPE coefficients. Now, why the OPE is so important is because you can apply it to endpoint functions. So once you apply it to endpoint function, of course, you get a sum over n-1 point functions. And then you can iterate this many times, and you get, for example, many sums of some either 3-point functions or 2-point functions or 1-point functions, but some correlation functions that you know. So one of these 3 that are known, and you can get 2 sums of those ones. And so you see that in the end, in this story, you just use the knowledge of the spectrum and the OPE coefficient, and you manage to rewrite an endpoint functions in terms of something known. And so this motivates the definition of the so-called CFT data, that is the set, well, is the spectrum and the OPE coefficient. And the idea of this CFT data is that if this is known, then you can build all endpoint functions of your theory. then it's very, well, it's very natural to ask a question. So since I have this set of numbers, this is just an infinite set of numbers, and from those numbers I can define a CFT in practice. And so the question could be, but are those numbers special? I mean, can I just take some random numbers or my favorite numbers and they define a good CFT? And well, the answer, okay, here there's a spoiler alert, but it's no. And so this is the idea of the bootstrap. And to see that indeed it's not the case, it's important to introduce this concept of conformal block decomposition, which is in practice just done in this way. So we take one 4-point function. Here for simplicity, I take a 4 equal field that I call phi, and I do the OPE of 1 and 2 and 3 and 4. Once you do the OPE, so I wrote it before, you just plug this formula, and you get that you get some differential operator that will act on this operator OK at the point 2, and another differential operator that acts on the operator at the point 4. And this is a 2-point function. But you see that these, everything in this parenthesis is just fully kinematical. So it's something just fixed by symmetry. So you know these and you know these differential operators. So again, the only part that is not known are the OPE coefficients and the sum in the spectrum. You can further rewrite this in terms of a function of the cross ratio, because in the end, this was just a function of 4 points. So you can fix it by conformal symmetry as any 4-point function. And it will be a kinematical function that depends on U and V. So this function is what is called a conformal block. So this, you can represent it pictorially in this way, where this is the OPE of operator 1 and 2 and operator 3 and 4, and you're exchanging some operator O. In this case, it would be OK. And it's important to make some points about this, function. So the first point that I will continue to stress is that it's completely kinematical, so it's fixed by symmetry. But moreover, it's also sometimes just known in closed form. So for example, also in 1D, 2D, 4D, also in general, in even D, there are some known formula. And you can write, for example, in 2D, this is the simplest case, where you write this conformal block as a product of 2 functions, that depends on Z and Z bar, which are the cross ratios. And you see that these functions are defined here, and they are just simple hypergeometric functions, 2F1. The other point is that, okay, in other dimensions, for example, in odd dimensions beside 1, they are not known in a closed form, but still there are techniques to compute them at arbitrary precision. So it's possible to compute them. And okay, so this was my, now we defined the conformal block decomposition, and now it's very natural to ask a question, but what happens if I do a conformal block decomposition in a different channel? So instead of doing this channel, the OPE in this channel, I do an OPE in the channel 1,3 and in the channel 2,4. And so this is what it's written in this schematic formula, which can be actually written in this way, which is not schematic. And this is it's an equation that surprisingly is not satisfied automatically, but by a generic spectrum. So and it's more than just one equation actually, because you see that this equation depends on the U and V variable, which are 2 continuous variables. So you actually have 2 continuous infinities of equations. And this can be thought in our setup, where we think as of the OPE coefficient and the spectrum as the unknown. So these are equations, infinitely many equations that constrain the CFT data. And then it comes this numerical bootstrap oracle. So this, I don't want to go to enter in the details of how to do this, but let's say that in this bootstrap community, it was actually, it was found a way to actually extract information from these infinitely many constraints. And in practice, the algorithm, there's an algorithm that works like this, that you input your favorite set of numbers, so your CFT data, and then let me think of a black box that is this numerical bootstrap oracle. And this black box tells you if your CFT data is actually not allowed, so it tells you no, so you cannot use that, or it tells you maybe it's fine. And so this black box contains information from crossing, so this equation, and some extra assumptions that you can add, and I will discuss in a couple of minutes. So what can you do with this algorithm? So I write here an example. This is, well, the most famous one, but there are actually many, many more in the literature. But you can see that there is this example that is very famous, is the critical Ising model in 3 dimensions. This is famous because this model is actually not solved analytically by any technique. And so typically you compute observables in this theory just through Monte Carlo simulations, or sometimes also epsilon expansion, but that is very hard to get with some accurate precision. And so what does this algorithm give in this case? Well, it gives you some quite nice plot. So here I plot the dimension of 2 operators. So this is part of your CFT data. This is an operator that is called sigma, is the spin operator of the Ising model. And this is the energy operator, epsilon, of the Ising model. And so what it gives this algorithm is that there's a huge, a huge no region, and there's a tiny maybe region that is just there. And you see that it's actually very, very precise, the size and very tiny, the size of this island, that is the maybe region. And actually, it's really centered at the position where also Monte Carlo simulation find the dimension of these 2 operators. So it's quite remarkable. And why I went through all this story is just to say that in practice, this is telling you some very important lesson. It's teaching you that axioms, in particular, this would be crossing plus this extra assumption, can be thought as like defining the CFT. So you can really define the CFT through some axiomatic approach. Now, since I talked enough about these extra assumptions, maybe I should also say which kind of assumptions you can use in general and which one were used in this sort of plot. So the typical assumption, let's say level 0 assumption, is the discreteness of the spectrum. So this it means, in other words, you say that the CFT is compact. This is a really important assumption because you see here we have sums over this over the spectrum. But if you don't have a compact spectrum, you would have integrals. So it would be a completely different kind of equation. It would be much harder to study. So this is the level 0, and any kind of bootstrap, at least, the recent bootstrap is done with a discrete spectrum. Then there's another assumption that is very often used, almost always, but not really always, that is, unitarity. Or if you want, in terms of the CFT data, you can call this just by this assumption. So the assumption is that the dimension of the operators are as follows, are bigger than something that depends on their spin and the dimension of the spacetime. In particular, you see that this is the dimension of a free scalar. And so it's telling you that any scalar operator has dimension bigger or equal than a free scalar. And this is the dimension of a conserved tensor of spin J. And so any operator with the spin J will have dimension bigger or equal than the one of a conserved tensor. And the other assumption is that these OP are actually real numbers. Another assumption that is used in most of the works, but not in all of them, is the existence of the stress energy tensor, so locality. And okay, that was also used of course in this plot. And then you can also input the existence of extra symmetries. For example, for this easy model, there was a discrete symmetry, Z2, that is just the symmetry that flips the spin. In the easy model, you have a spin plus or minus 1. You can flip the spin and you have a symmetry. And so this symmetry enters in the equations as a selection rule. So you know that your correlation function sometimes cannot be non-zero because of selection rules. But in the case of continuous symmetries, you actually can also impose the presence of a symmetry just by saying that there is a current. And well, this was not the case for Ising beside the stress tensor. And okay, then you can add extra assumptions. And this, you can add anything you want to add. And in the case of the Ising model, there's actually something that you know from physics, that is the number of relevant singlets in the Ising model, because it's telling you, so you know that because once you do Monte Carlo simulation, you know that to reach the critical point, you have to tune one parameter, you have to tune the temperature. And so this tells you, in the sense of the RG, that there is just one relevant singlet perturbation in your model. And this tells you in practice that in this axis, so you see it here, I have delta epsilon, that is the dimension of the force operator that is a singlet, so it's Z2 even. And the next one will have dimension bigger than D, so in that case, bigger than 3. And okay, so I finished the part about the bootstrap, and now the idea was like to see where we stand with these celestial CFTs in terms of these axioms and how much we can of this philosophy we can use. By the way, if you have any question, you can ask. So let me, if there are no questions, I'll go to this celestial CFT, to the celestial CFT part. So let me start by the basic axioms of the celestial CFT. So this is really the level 0 part, which any CFT must have. And so you want these axioms to be there in celestial CFTs. The first part is symmetry. But symmetry, again, it's a conformal symmetry in the dimension in a celestial in a CFT. And so what do we have in the celestial CFT? Well, I told you before, we have a quantum field theory in 2 higher dimensions that has Lorentz symmetry. And so we are fine. Lorentz symmetry in two extra dimension, it gives you in practice the conformal group. So you are done with symmetries. Now, the operators. It's important to have a set of primary operators. How do you build them? And this was introduced by Andrea. And so I'm just telling you that if you have some field in your Lagrangian, let's call it phi, that will depend on some point in your 2 extra dimension space. So in your Minkowski space in 2 extra dimensions, and what you do is this convolution of this operator with some primary wave functions that integrate out the x dependence here, and gives you back a dependence on X and on delta. And so it gives you exactly an operator of this kind, which transforms indeed as a primary. So we have a set of primary operators. Now, correlation functions. Well, the correlation function, in this case, it was also introduced, and it's in practice just you take your... Yes?
Can I ask a question?
Sure.
I was just confused. I should have asked this to Andrea. So this way of defining the operator, are you saying that we should think of these bulk operators as the dual operators as well? Are you identifying them? Or are you saying that this is the source for the dual operator in the dual CFT?
So no, I'm saying that, well, I'm saying that given any operator, you can build something that transforms like a primary. I mean, it's not really a dual operator. I don't know, because you have just a single operator, and this gives you the full set of possible operator of the CFT. So it's slightly different. I wouldn't know if to call it exactly a dual operator.
So, I mean, I would kind of argue that it's like basically an extrapolate style dictionary. Now, there's a sense in which you might likely think of it as a source in the following sense. Like F will normally be like the canonically conjugate mode to the one that you're creating in some sense. So
okay, yeah, sure.
The way I think of this is that this is in practice giving you a creation or annihilation operator that creates some state that transforms like a primary. So that's the way I think of it.
Yeah, but I'm just confused which Hilbert space this lives on, because this is an operator in the bulk Hilbert space. So
yeah,
it'll act on the bulk vacuum and create
indeed.
A bulk state.
That's
so
indeed.
Exactly, that's the point where, yeah.
Oh, we're saying that the two Hilbert spaces are identical. That's the conjecture.
Well,
and so
well, it depends on how you think of it. But yeah, that's a different question if you want. But for sure, there's a way to define it in this way, in such a way that it's the same idea of doing the Mellin transform of the S matrix. If you do the Mellin transform of the X matrix, you find something that transforms like a correlation function, which was my next point. And indeed, it's exactly in that sense. So yeah, I think, so you get something like a correlation function, which is not a state. So for example, if you do it for a 2-point function, you get a 2-point function. You don't get, so this part, the part of the S matrix, you would start with, well, that's a bit trivial, the one-to-one scattering. But let's say that in that case, you would have, you would get some states, but on the other hand, you get a correlation function, a 2-point function in the CFT.
But I think you can also say that you can look at a correlation function in either 2D or 4D. So maybe that's another way that looks a little bit more similar. Like in the same way that I would say that the thing on the right-hand side is basically, instead of doing LSZ, you are like trying to write massless S matrix elements as like correlation functions in the bulk of like operators pushed to the boundary. So
you're saying that this convolution with F kills the external propagators.
So basically what F is doing is basically getting rid of all the polarization tensors so that you really do extract out A. But in practice, it's pretty trivial to do that for like the spin 1 and 2 fields. It's a little trickier for spin 1/2 because basically it's just like every polarization tensor turns into a factor of 1 plus ZZ bar to some power. So you're just like, oh, look, it's just a free factor, but like, no, you should be careful. You're like projecting it out. So.
Thanks.
Okay, anyways, well, I'll assume that this gives you your set of operators. And so...
Maybe just to add a slight comment that combines what Sabrina and Emilio both said. In the case of the plane wave, if F is just a plane wave, then you can just, and you mode expand phi into plane waves with the creation annihilation operators, then you just use that the plane waves are delta function normalizable. And what Sabrina said was that the plane wave that's inside the phi mode expansion is the one that survives, that gives you the creation or annihilation operator, whichever one is in front of the
canonical partner of the wave function f that you plug in, you use the delta function inner product of that, and then you land on the creation and annihilation operators. And here we just plug in a different wave function f, and you can still, if you want, use the mode expansion of phi into plane waves, or you can use the mode expansion of phi into conformal primary wave functions. And then whichever you do, you will always pick out the operator that comes with the canonically conjugate wave function to the one that you plug in for f here. I don't know if this clarified things or had the opposite effect, but
no, I think it's fun. Yeah. This is very fun.
To confirm, so if you take the bulk correlation function of these operators, it does the LSC reduction for you.
Yes, like LSC is almost like if you look at the first step of LSC, it is this. So instead of going all the way to the Cauchy slice, basically if you look back at like the first soft theorem equals like word identity papers, and they have the saddle point, like you can reinterpret that as basically an extrapolate dictionary for the U basis. So this is why I'm sympathetic to people saying that, oh, maybe it's on a 3-manifold, because you can just Fourier transform back and literally think of like the news at the boundary as a local operator is basically like giving you something that's Fourier transform related to the S matrix elements in the plane wave basis, or Mellin transform related to the ones in this one. So all fun.
Thanks.
Okay, and now I'll go to the last basic axiom, that is the OPE. So this was also reviewed by Andrea, so I'll be quick. And the idea is just that in the S matrix, if you take two particles to have collinear momenta, you get this, the fact that you get a sum over amplitude with one less leg. And so you really get something that looks like the OP, and in particular, after you Mellin transform this, you get an OP of these correlation functions. And so the basic axioms are there. Now the question is, what about these extra assumptions? So that indeed that they are really important, because in the case of the Ising model, the way one defines the theory is by the basic axioms plus all the extra assumptions. There's a question, I think.
Yeah, can I ask a question about the existence of the OPE?
Sure.
Do you know that OPE is well defined in the Celestial CFT? For example, the OPE, when you have holomorphic, anti-holomorphic fields like positive helicity and negative helicity fields, those OPEs are ill-defined because sort of don't you have to relate, you have to choose a prescription to make them well-defined, which the prescription that is often chosen is that you take the plus helicities first, and then you take the negative helicity limits first, some holographic limit that was described in the previous talk.
So can I ask you, when you say that, is the issue with taking the soft limit or taking like literally the OP collinear limit? I just want to understand that better.
I think they're both related.
Okay.
Maybe I'm saying something wrong. That's what I want to ask.
I'm sorry, because I'm asking this too.
In 4 dimensions, there is this issue with, with different helicities, and you have to worry about there's some prescription that you have to do. So, and that's fixed by using some prescription. What goes on if you're assuming the existence of an OP in higher dimensions, are we assuming it with some prescription, or is there no other information that needs to be provided there?
Well, indeed, that's a good question, and I would add to that also the fact that actually these there are 2 ways to define the OPE. One is through this Mellin transforming the collinear limit, and one is through symmetries. And yes, if you both ways anyway have a subtlety that so they are based still on some so they have quantum corrections, so they may have one loop corrections, and so one should actually be a bit careful in this definition. And one should have everything under control, because this is such a basic axiom that you want to have it completely under control. So I think that it's very important. And I also agree on your comment that there's a question about the prescription. So yeah, I think probably this must be cleaned up a bit. I don't know, Andy has maybe as a comment on that.
Yeah, I do. I was going to say something about this tomorrow, but the fact that that Prahar was referring to about the double soft limit, that has nothing to do with celestial conformal field theory, and it has a fact. It's already a problem in momentum space. So it's already true that if you scatter if you scatter two soft gluons or two soft gravitons, the usual story, it's not well defined. And as Prahar well knows, because he and Temple and I talked about this problem in a paper about 5 or 6 years ago, that simply means that the standard textbooks do not define the momentum space S matrix, because they don't tell you what to do if you're scattering two soft particles. And this is kind of a common thing in mathematics, where you have some manifold and there's some, say, in algebraic geometry or some moduli space, and there's some singularities, and you need to give some prescription to compactify compactify the manifold or compactify the moduli space, or how you deal with that extra, what the structure of the manifold is at the boundary. So there isn't in the literature a proposal for what you do when there's two soft particles. So the S matrix in momentum space is not defined. It's not about conformal field theory, and that problem persists when you go to the conformal basis. Yeah, now, Prahar and Temple and I made a proposal in how you should deal with that, and our proposal was that you choose one helicity, and you always take that one soft first. And we kind of put that out there. And what I've realized only recently, well, this came out very clearly in the recent paper by Costello and Paquette, that this is exactly what the Twistor people have been doing for 50 years, and it's what's done in the amplitude story. Is you expand around the positive helicity sector, or you expand around the negative helicity sector, and that gives you different descriptions of the S matrix. So I think that so the problem with the OPE, just to summarize, the problem with the OPE, it's not a problem with celestial conformal field theory, it's a problem with quantum field theory. And there is a proposed way, which I think is not fully understood, but there is a proposed way of understanding it. And in that proposal, the OPEs are perfectly well defined.
And one thing,
that's the proposal in 4 dimensions, right? So that works for 4 dimensions. Is there a generalization of that, do you know, to higher dimensions?
Well, I don't know why the same thing wouldn't work, but I haven't really thought about it.
So you don't have positive, negative helicity.
Yeah.
You now have like 4 different helicities.
So
and you don't really have
this isn't, and it was our proposal, but I think it's been implicit in the Twistor program and whatever.
They're the reason. What helps us is that you have this self-dual and anti-self-dual. You can restrict yourself to the self-dual sector and the anti-self-dual sector.
No, but it works for perturbation theory about that, in which you recover the complete theory. So that was, so you start with the self-dual sector. So, in this recent paper I think this is all stuff that is known, been discussed in different languages in many places, but you start with the self-dual sector, and then you reconstruct it. Atul's the expert on this. You reconstruct the whole theory, adding perturbatively, finite numbers of anti-self-dual excitations. And in that expansion, the correct thing to do is to adopt it. Essentially is equivalent to the prescription that you and I and Demple put out, whatever, 6 years ago. So we couldn't think of anything else to do at the time, but it now seems like that probably was right.
So can I add one question or comment along those lines to see, like, so do you guys think that it would still be okay if you were not at strictly zero frequency in the following sense? Because if you look at like the derivations that you guys are starting from is normally using like the saddle point approximation. And there's something funny about the saddle point approximation commuting with the soft limit or not, where like maybe like if we said that the OPEs are like for finite frequencies or finite delta before we continue to soft, like makes sense. And then you can understand any problems as like an order of limits issue, or I don't know, just throwing that out there for like food for thought and or like background. Because that's there, that saddle point thing is there in momentum, I mean, in either of these extrapolate pictures, like in the, yeah, before going to Millen. So
I just wanted to say that what Andy said will not work in higher dimensions because in higher dimensions, the twistor correspondence only works for the hyperkähler sector. So there are like many, many more negative helicity modes than the one single positive helicity mode. In higher dimension, well, in 4K dimensions at least, there's always one positive helicity mode, which comes from the hyperkähler sector, hyperkähler perturbations of the flat metric. But all the other are negative helicity modes, and there's no symmetry. So there's no Penrose transform for all the negative helicity ones. So it's not clear how you'd order them.
Prahar and Temple and I didn't use any of that structure in our description of it. I would say we describe something which is more general, which reduces to what the Twistor people are doing in the special case of self-dual. We weren't even in a conformal basis. The conformal basis wasn't known then.
Yeah.
Right.
I do think this just shows it's an interesting question.
I think the operator product, if you've defined the quantum field theory, I mean, the operator product expansion is the collinear expansion of the quantum field theory. So if you've fully defined the quantum field theory, the operator product expansion better be, you know.
Yeah, I think the issue is when you intersect the soft and the collinear limits. It's like, so that soft limit is where a lot of the constructions that we have kind of become like things you have to double take at. So. Oh, Lee has a question, or is it just me?
If I may, I mean, many of us see the same phenomenon, say the same words with a different motivation. So I wonder if these things are known to you. The way that we think about it, going to self-dual gravity, gives us a theory whose action is cubic, is purely cubic. So the equations of motion are purely quadratic. And both classically and quantum mechanically, you never have to do anything but to find one operator product, because you only have to construct solutions to quadratic equations. And then once you do that, you can do the perturbation theory in the opposite helicity, and it's systematic.
That sounds like the same, yeah.
So do you all talk about Klavansky with the same awe that we do?
I think we're starting to.
That's what Kevin and Natalie's paper did, essentially. Mm-hmm. They used the H tilde H twistor action that I talked about, reduces to Klavansky. Yeah.
Yeah.
Good.
This is a googly problem. It's just everywhere.
Yeah, and I'm just because Atul might be too humble to like. He has a really cool paper, a solo paper on this stuff. So check it out.
Thanks.
So one trick we learned about early was going to the self-dual sector with no cosmological constant, and then setting the self-dual connection equal to 0. So you got a simple equation in basically you had 3 vector fields, and the time derivative of one was the commutator of the other 2, and that was the entire of how you could write down the dynamics of the self-dual sector.
Yeah, I don't know if we have much more to add on that in this context, but I'm sure that, especially with Atul joining the Harvard group, like there'll be a strong.
Feel free to sort of talk over me in my talk.
Yeah, I guess there's a talk coming up where we can debate this further. Let Emilio go back to.
Good. Okay, thank you.
Anyway, I agree on the fact that it's really important to have a very solid definition in Celestial CFT, since this is such an important axiom. So if it's not there, everything collapses. So it's really important to have it on the most solid ground as possible. So and so this was the end of the basic axioms, that they must be there. And so let's assume that there's no problem with the OPE, since, I mean, a lot of evidences seems to go in the direction that, I mean, there's a well-defined OPE. So let's assume that. And now let's consider the extra assumptions. So extra assumptions in practice were always assumptions on the spectrum in practice, or on the CFT data. And so the first question is, what even is the spectrum of Celestial CFT? So I want to understand what is delta. And so, of course, you get this definition for the celestial amplitude from a Mellin transform, where you trade this omega for some parameter delta. So at the first sight, it looks like a free parameter. So this would be the first sight point of view. And this would look like quite crazy, because we saw before that in the bootstrap, we say that there are these consistency conditions that are so strong that tells you exactly, I don't know, 10 decimal places, the number exact for some dimension. And here, the fact that you can have a free parameter, it would look like something completely weird. But then there's the second point of view that is a bit more restrictive, and at least it sounds a bit better, that the dimension should actually lie on the principal series. And so it's d/2 plus any imaginary number. And you actually need the full principal series. It's not like it belongs to, it's really, you need the full principal series. And why you need it? Because indeed you want this delta function normalizable set of wave functions. In order to have it, there's this sort, in practice, it's just a completeness relation. And this sets the dimension to be in this principal series. But beside these ones, we also saw that there are some dimensions that are in the integer. And so it's quite unclear. And also there may be more dimension that we still didn't understand. So I would say that it's still a question, what is the actual spectrum of this Celestial CFT? Which, okay, in some sense is normal. For example, if you knew already the spectrum of the Ising model, then you would have solved the theory. So in some sense, it's fine that we have some questions about what is a spectrum. But here, I think we are at a level that we still don't understand, let's say, more basic question, like, let's say, what is even the field? Is it actually a complex number, a real? Do we actually need the principal series? Is there a formulation that gets rid of the principal series? I mean, I think there are some questions that, I mean, are still not completely answered. But typically, we assume that the principal series should be there. And so I assume that it's there. And so if the spectrum contains the principal series, we get a definition for the CFT that has quite weird properties. It's non-unitary, it's non-compact, because so we need this spectrum to be continuous. You need the full principal series, and it's complex. And so this is like the worst case scenario. I mean, it never happened in any known case that you have an actual spectrum with these features. And I see many raised hands, but let me just say one last thing. I think that this is indeed related to this fact that Sabrina mentioned, that is that indeed this function f of u and v, the function of the cross ratio that we find in the 4-point function, is not even a function in this case. It must be a distribution for momentum conservation. So this means that, so you see here we had, if you have that this 4-point function is just a sum of functions, for sure the space of function that you can get as an infinite sum of functions is it's probably much smaller than the space that you can get by an integral. That is what you would get with a continuous spectrum. And so this is the reason why you may get these delta functions. And so it's a related problem. We have these functions that are actually distribution in this case, and also we have this very complicated spectrum. But now please ask or make comments or questions.
Andy was first, I think. Or...
Let Prahar go first.
Oh, sorry.
I just want to ask, why are you saying the principal series is non-unitary? Principal series is a unitary representation.
It's a unitary representation of the Euclidean.
But we are in Euclidean CFT. This is the CFT.
I mean, what I mean is that unitarity, what I call unitarity here is unitarity in Lorentzian. But otherwise, it has a different name. It's reflection positivity in Euclidean. I mean, the condition, let's say that you don't call it unitarity, you call it this.
Yeah, but this condition is not relevant for us, I think, because the CCFT is inherently Euclidean, right? It's not like we are obtaining the CCFT from some quick rotation.
That's not clear.
Well,
that
actually,
is not
it's not even true. At least,
think,
and is working in a different signature.
And to do like the light transform stuff that Atul and like and like Scott and I, like you need, and Anna and lots of people, you need to know how to kind of like at least having one foot into two.
I want to make anyway an important comment on this. So once you consider typical CFTs, for example, this Ising model is in 3 dimensions. It's in Euclidean 3 dimension, and so it's a Euclidean CFT. And the relevant unitarity is not unitarity, it's called reflection positivity, but is this one. So this condition should hold for Euclidean CFTs too. So this is, I mean, it's not something that you must have in Euclidean. Indeed, there are some CFTs that are non-reflection positive that you find as a critical point of some. I mean, once you study phase transition in some statistical physics model, you may find some non-unitary CFT in the sense of non-reflection positive, so that it doesn't satisfy this constraint. So it's not needed but that, I mean, it's a property that most of the known, well, that it's not true most, many of the known CFT have, and the one that we are studying doesn't have it. But I would argue that this is not at all the main problem. So the main problem is that it's complex. Complex CFTs are really almost never studied in the literature. There are some cases where you can do some analytic continuations of known CFTs where you have some parameter and you make it complex. And so you can study those ones, but those ones are, even in those cases, you have a discrete spectrum. So there's no case with such a complicated spectrum that is continuous and complex.
I mean, if hints from de Sitter holography, to the extent that that exists, suggests that you should also have principal series, right? There's also showing up there with a different notion of unitarity.
Sure. You can have. I mean, I'm not saying that you cannot have it. I'm not saying that is that is inconsistent. I'm just saying that it's very complicated.
Okay.
Maybe Andy might have some fun thoughts about this.
Yeah,
like restricting
yeah.
control.
So I don't think it, well, first of all, I'd like to say it's an awful lot like Liouville theory, right? If you have a Lagrangian for 2D Liouville theory, you can, a priori, you can write down an operator with any dimension by just writing e to the alpha phi. And that gives you continuous dimension. And as you know, the Zamolodchikovs, after sort of decades of work, used the conformal bootstrap to show exactly what the spectrum was for Liouville. And it's not, those operators are not all independent. The values in the complex plane aren't all independent. So I don't think I guess I don't agree with the statement that that a complete basis has to include the principal series. So it's a little bit like if you have a.
I didn't say that.
I thought you said we agree that isn't there what is written here? Principal series is.
Well,
here's an if.
There's an if, but I say that is a typical assumption that we consider, or at least I think it may well be just a tool that we are using that, for example.
Right. So I think, it's a little bit like if you want to describe a Gaussian wave packet, you can write it as Fourier transform of plane waves. That's like the principal series modes. Or you can just do a Taylor expansion in powers of X.
I agree.
That's like the integer modes. And so, my hunch, and it's only that a hunch, is that the integer modes are a complete basis, and that should make you happy because it's both discrete and real. And I also think it's implicit in what the Twistor people have been doing for 50 years.
I want to make a comment on that. At this point, I wanted to hide these comments, but since this is coming out, why not? So indeed, even in usual CFTs that have this discrete spectrum, you always have a way to actually recast it in this principal series, because you have indeed also the basis that is provided by the Euclidean representations, the unitary, the unitary Euclidean representation that would be the principal series. And so this is actually a different representation, and typically what you do in conformal field theory is that you have an integral over the principal series, and then you can deform it and pick poles, and these poles would be actually discrete at discrete real values. And so hopefully this will be the case also in this story. But yeah, at this point, yeah, I would say that it's still not fully understood what is the spectrum. Hopefully it's just the integers, but I don't know.
Yeah.
So, okay, but beside that, even the worst case scenario where we have this very nasty spectrum, however, we have a good thing that are symmetries. So we said that in order to specify a theory, we need a lot of extra assumptions. And in particular, some of these extra assumptions are related to the presence of symmetries. And here we have many, one for each soft theorem. So I have this table that is in practice just what you already discussed in the previous talk, but let me go through that. It's just a review. So we have, I'm now focusing on the Celestial CFT 2 and also on gravity. So we are considering some amplitude and we are doing the soft expansion, so in powers of omega. And so once we do the Mellin transform, we know that powers are mapped to poles. And so we get the poles at some value that are integers. And that in practice, at these poles, you can say that you can define some operators with the definite conformal dimension equal to some integer. So let's call them H. And so you see that the leading soft theorem would be mapped to an operator H1, which has dimension 1, and is the one related to supertranslations. But then you have a subleading omega to the 0 that is related to this operator H0. And if you take its shadow, you define the stress tensor, and this was the superrotation generator. And then you would have this next power that is sometimes called the most subleading. And this most subleading in the sense that it has, it's the most subleading soft theorem because it has some universal piece. But in principle, we can take any other power. And they are just some operators that we can call H minus K. And these altogether form like this W1 plus infinity extension that is now studied a lot, and it will be discussed in the next days. So what I wanted to say now is that there's a way to classify some sense of bootstrapping principle for classifying these symmetries. So we have many of these currents, but there's a question. So you see that these currents have some special dimension and some spin, and so they are really some special operators, and we want to understand if they are even compatible with conformal, the conformal structure. And this is possible. It's a question that has an answer because in CFT it's possible to classify the conserved operators. So they are in practice just related to the primary descendants. Let me give you an example. So if you have a stress tensor Tmn, so you know that it will have a conservation equation that will set this to 0. And so you want this to be a primary. 0 is a primary. And once you ask that this is a primary, you actually get a condition for the dimension of the stress tensor that it must be equal to D. So this tells you that you cannot have any operator with this property. That operator must have a specific dimension. And here we have operator with some dimensions and some spin. And so we want to understand if they can actually be present in this CFT picture. The picture in general looks like that. We start by a primary, and then we consider a descendant that is just built by taking some derivative of the primary, and we ask that it's a primary itself, so it's annihilated by K. And this condition is enough to fix the dimension delta and J and delta prime and J prime of the primary and the primary descendant. And it's also important to notice that these are actually all, these numbers are classified and they are known for any CFT in any dimension. And it's just representation theory. Instead, this form for differential operator is not yet known in any dimension, but as we see now, in 2-dimension, it's actually a trivial question, this one. It's a one-line computation to find it. Indeed, in 2D, okay, the generators, we saw them are these ones. And it's also important to introduce the definition of H and H bar instead of delta and J. And we see that given a primary, we write a generic descendant in this way, where these L-1 are just the derivative in direction Z or in direction Z bar. And this would be the most generic descendant. And we ask that this is a primary by requiring this. And it's just a one-line equation, just doing some commutation relation of L1 with L-1 to some power. And we see that this must be 0. And so this gives a condition for H. And you can do it for H and for H bar. So you have a primary descendant when this is satisfied and also when this is satisfied. But it could happen that both of them are satisfied. So you have this more interesting structure where you have your primary here and it has a primary descendant there, but it also has a new primary descendant here, and they both have a primary descendant at the bottom. And this structure is called, well, now is called the diamond. And okay, we can then rephrase it also in terms of dimensions and speed and spin. It's useful for the next. And in terms of the dimension and spin, you see that your primary operator will have primary descendants of 3 types. Type 1 is the case where the primary descendant has spin that is greater in modulus than the one of the primary. The type 2 is smaller, and the type 3 is equal in modulus. Well, it's equal to minus, so it flips the spin. So there are these 3 types. And the first type, it actually has two realizations, type 1a and type 1b. And they are just a bunch of derivatives, either anti-holomorphic or holomorphic. And they both arise when the dimension of the primary, so this dimension, are 1 minus j minus n. And you see that n can take any value from 1 to infinity. But then you have this type 2 case where instead, this is the definition, and you have it for these dimensions, but you see also here there's this parameter n that takes just a finite number of values. And the third type that has just one value. So there's just one type 3 primary descendant. And you can make some nice pictures. They all can be represented as some reflections in this plane with delta and j. And okay, so now another important story is that there are some shadow relation between this primary descendant. In particular, given a primary, you have that the primary descendant of type 1a and type 1b are related by shadow. Also, given 2 primaries that are related by shadow that have a descendant of type 2, primary descendant of type 2, you see that they both go to the same primary descendant. And the third type is the primary and its primary descendant are related by shadow. And so this is these pictures that just representation theory for the conformal group. And we can apply it to the story that we just saw. So here I wrote the spin 2 and minus 2. So there are the 2 copies, the holomorphic and anti-holomorphic. And you see that there were dimensions 2, 1, 0. There were many dimensions that I mentioned for these special currents. And now we see that they are actually captured by this representation theory. So they are consistent. And in particular, you see that the asymptotic symmetries are all of this type 2. And they are also related, they have this relation by shadow that relate like this point to this point. And while this most subleading theorem is of this type 3, and then there's this infinite tower of primaries that have some primary descendant there at the bottom, that is this W infinity completion. And so we see that indeed at least everything is compatible with this symmetry that one, with some the conservations that one can have in conformal field theories. So so this is just I wanted to end here this talk. And so here I just introduced the CFT language, the bootstrap language, and I applied to Celestial CFTs, where we find that there are some basic properties that seem to be under control. And this special property of the spectrum and on the special symmetries are also under control and can actually be lifted to find a unique picture that will actually define these theories. So thank you very much.
Thank you, Emilio. Were there any further questions before I terminate the recording? If not, thank you again, Emilio. It's really fun how we can have these lectures that nominally are on rather like basic things, but then it like instigate really interesting discussions with this. So thank you.
Sorry, I had a question. I just remembered.
Yes.
Did we have an interpretation for the positive conformal weight modes as well? Delta greater than 1. Delta equals 2, delta equals 3, delta equals 4, and all those.
They appear as like the shadows, I think, or like the,
Oh, they're not independent. Okay, I see.
I mean, there are, but the ones that are,
let's say that typically when you do the representation theory, let's say what you study are operators that are either at this unitarity bound that I showed or below. These are, let's say, what give some representation that have something weird. Typically, they may have some null state inside.
Yeah.
So this degenerate representation appear typically at negative dimension. But if you think of the shadow of one of these, then yeah, you can get anything.
And so the kind of pretty thing about it too, though, is I think that there's something that we've appreciated since where like we draw these diamonds that like basically terminate for, if you just keep everything to order delta, you would find that that infinite tower basically gives 0 when you descend. But if you go to the subleading order and an infinitesimal deformation of the delta, you can keep a term that's like the light transform and then go back down again to the shadow. So you can really get modes with like the positive delta. So. Okay, Andy.
Yeah, just, I'm not sure if somebody said it, but I think the positive integers also, they're symplectically paired, as Sabrina showed in some paper, with the negative ones. And so that means we can understand them as or their shadows as Goldstone bosons.
I see, yeah.
Of this symmetry that they're paired with. But I had a question for Amelia. So, you know, in the Ising model, we had some idea in the D=3 Ising model, we had some idea of what the spectrum should be, as you said. But now suppose we want to talk about celestial conformal field theory, and in particular, we want to talk about the one that describes the real world. And there we don't really know what the spectrum is going to be, right? We know gravity, there would be gravity and all the conformal primaries you could make out of that, and all the ones you could make out of the photons. But there's lots of massive stuff that we assume that, you know, that the standard model is not the end of all particles. Sure. Maybe there's string theory and a lot more stuff. And so is there any use for conformal bootstrap? And is it within would you be willing to speculate about some kind of application of the conformal bootstrap to the real world, where somehow we start with things that we know and assume celestial conformal field theory and the conformal bootstrap and deduce that there's something else?
Okay, so yeah, I would say that at this point, at least the typical techniques that are used in the bootstrap are, let's say, I don't want to say completely useless, but let's say at least the numerical bootstrap is useless because, I mean, well, it depends. At least depends if you impose a discrete spectrum or not. But what I was hoping is that imagine that we understand this infinite tower of symmetry. I mean, if there is actually this infinite tower of symmetries, and so we can impose the existence of infinitely many conserved operators, and yes. And we have some idea of the spectrum, maybe even the usual conformal bootstrap or some versions of that can help. Or in general, to me, it's not even, the bootstrap is not really just the techniques that are available now that were used to find the easy model. It's really just a way, let's say a philosophy, a way to instead of looking at examples, let's say, to just try to lift the symmetries and what we know to get some mileage for, let's say, some non-perturbative definition for the theory. So I was hoping, yeah, that something like that, I hope that something like that at some point could be done. But yeah, it's not, I mean, I don't have any clear idea of how to do it. yeah, it may be very different from what is found in the easy model. So but for example, yeah, what is studied, I mean, all the theories that were studied with this numerical bootstrap had like discrete spectrum are typically unitary theories. Already for non-unitary theories is much more complicated. And so, for example, this method is not always perfect, but it has all other incarnations. For example, there are some analytic bootstrap results that are useful sometimes to do some perturbation theory. And so, I mean, and depending on the theory that you have at hand, you can find some new bootstrap questions, maybe some modular invariants, I don't know, or some different kind of some different kind of algorithm, let's say.
Hey, Scott.
Hey.
Hey. Related to the comment about analytic bootstrap, is the vacuum a normalizable state in CCFT? Like, is there an identity operator that participates in any, like that's exchanged in any channel, in any CCFT observable?
I would think so, but I think that there's a little bit of a subtlety of understanding that like the state operator correspondence like Andy has in his paper. I think once you understood that, then the identity operator should really be the fact that we have to be careful to not look at like disconnected parts of the S matrix, but the full S matrix. And then there should be like, they probably will have the same type of like generalized free field type of.
Yeah, right. Like one of the lessons of the analytic bootstrap in recent years is that the presence of at least in the presence of a gap above it, if you have the identity operator in one channel, that leads to universal asymptotics of CFT data in the other channel. And this is what led to the sort of perturbation theory that Emilio was referring to.
And that's using just normal like global parts of the bootstrap, or is using Virasoro symmetry?
Both.
Yeah.
Don't you need for that the delta equal to 0 operator is the lowest dimension operator?
You do, yeah, you do.
Which is not the case here, because we know there exist all negative integer modes. Those are the W1 plus infinity. So I don't know if the identity contribution will be dominant.
But even in this case, we are not, I think we're still not quite sure about the spectrum, because maybe you can map all these operators, take a shadow of all of them, and actually get just everything.
Yep. Because if you took Andy's tower and then you shadowed, you'd have one integer, and you'd have that full tower, and maybe the identity then would actually be lower. But it's interesting to think about. I think these are good questions. Andy?
Yeah, just to make things more confusing, I mean, it's worth mentioning that there's a lot of different stress tensors, right? So, and when, you know, there was this funny thing that when you, well, the W algebra, it looks like it's a unitary representation, but we start out with, but it's not the unitary representation with the same stress tensors. It's a stress tensor that you would get from the Sugawara construction from the, you know, so even that is not something we can be certain about. Which stress, there might be another stress tensor that's better to use.
I agree with that sentiment. I think I'm not sure which of the stress tensors we're all referring to, but there are definitely, yeah, freedom with your stress tensor. So
what is the other stress tensor? I don't.
Well, I mean that. So the whole negative tower of soft modes were mapped to a bunch of W generators, all of which had positive conformal weights with respect to the usual stress tensor that you would have in the W symmetry. And that I think that usual stress tensor is something that lies in the enveloping algebra, the W algebra, and is basically the thing that it's like the Sugawara construction of the W algebra. So all of a sudden the negative weights become positive. Now it's very hard to see a situation in which we have only positive weights, but things that we thought were negative did become positive. So, you know, I don't.
Can you remind me where the stress tensor is coming in your, because normally if you're in the plasticity sector, you include a mode that would shadow to the T-bar stress tensor there. So, but you can also, I imagine that you're saying that there's another stress tensor just from that construction that is not, is that the one at the bottom that's like the theta term, or maybe I have to look at
Well, there's a W algebra, right? So the W algebra, there's an SL2R current algebra, and you can make Sugawara SL2R stress tensor, and that when people write down the W generators, they don't say those have negative weights. They say they have weights. What are their weights? Their weights are all 1. They're all currents. So everything, this infinite tower of negative stuff all got mapped to dimension one stuff, obviously with a different stress tensor. And that stress tensor, I think, is the Sugawara stress tensor of the SL2R subalgebra of the W algebra.
Because the delta equals 1 is like a wild reflection of these guys, or what? I just want to make sure that, or maybe, because there's definitely also 2 types of stress tensors you can get without thinking about the W infinity, which is like the super rotation Goldstone mode, and then the standard CFT stress tensor, where then you have to worry about combinations. But I don't know if maybe this one lands somewhere in between those 2, or what, if it's like a third thing.
But can we ever restrict to just simply posit? Don't we have the translation generators which shift delta? So
no, the translation generators are W3 halves, right? Those are the they're in the W algebra.
Yes, but they act on operators and shift, right? Isn't that correct?
At some point you can terminate, right? Because you can have a BMS primary.
They shift the weight defined by the old stress tensor, but not this other one. I'm not advocating for this other stress tensor. I'm just saying we you know, that's another thing. Thing to think about.
More things to play with, which is great. So. Okay, if there's no further questions, I'll stop the recording now. Okay, so I am happy to be introducing the final lecture for the school. So Atul is going to talk to us about Twistors and Celestial CFT. And just to like presage, I guess, some of like the talks coming up, Tim is going to be talking tomorrow. And then in a fun, I guess, twist of things, our IAS friends are hosting Kevin Costello on the Monday after the conference. So just like advertising that for those who want more when this is over, it'll be on Zoom. So yes, thank you. Take it away, Atul.
Thanks for the invitation. Of course, most of you are already experts in Celestial CFT stuff, but the Twistor stuff can probably tend to be very new, even though technically speaking, it's 50 years old. So I'm not going to be able to convey a lot of applications of Celestial CFT, but I'm just going to try to be super pedagogical for the sake of Tim and Alfredo's talks. So, of course, the end hope is that there's some neat way of patching the 3 descriptions together so that we can have more influx of students from one university to another. No, sorry. Oh, okay. Here are some of my favorite references. So there is a very nice set of lecture notes, quite recent, by Tim on twistors as well as twisted strings. So that's quite a broad set of notes. And then there are some notes which are closer to the twisted string revolution. So they're more focused on the topological B model type introduction by Freddie and Swartchek. Sorry if I butchered that name. I'll share my notes on Slack so you can copy that in time. So let me just start by imparting some motivations, because I understand that the farther you go away from Oxford, the harder it becomes for you to motivate yourself to study this, even at Oxford now. But so there are sort of 2 main slogans that historically have been the motivating principles for working with twistors. So the first slogan, which sort of is Penrose's big slogan, is that they make all symmetries manifest. And the classic example of this is that Twistor variables are variables that make the 4D conformal group of Yang-Mills manifest. And some more modern amplitudes applications have been in making dual superconformal invariants of n equals 4 manifest, as well as the W1 plus infinity application that we've all been discussing and probably will discuss tomorrow as well. So if people are interested, I have some bonus section on the W infinity bit, but no pressure. The second slogan is that of integrability, which is more the Michael Atiyah type of slogan, where you work in Riemannian signature rather than Lorentzian signature, and you try to solve nonlinear equations, nonlinear four-dimensional integrable field theories like self-dual Yang-Mills and self-dual GR. And in particular, that also leads to neat solutions of the corresponding linearized field equations. But the real power here lies in the self-dual nonlinear bit. And I think there'll be some mention of this in Alfredo's talk. So look forward to that. Of course, for our purposes, the most interesting reason why we should study Twistor theory is because they have a very deep connection to scattering amplitudes. This was uncovered quite late, well, in 2003 by Ed Witten in a paper that he introduced what are called Twistor strings, which are basically some sort of topological strings that describe the scattering amplitudes, the tree-level scattering amplitudes of super Yang-Mills theory. And there have been many generalizations to supergravity and to something called ambitwistor strings. And Tim will be discussing the four-dimensional ambitwistor string formalism. So hopefully my lecture will set up some of the notation for that. Okay, so now that hopefully you're slightly motivated and not fully, completely sleep deprived, let's start with the basic ideas. So before I get to Twistors, let me try to remind you of Spinor helicity variables for scattering amplitudes of massless particles. Twistors will simply be a generalization of the Spinor helicity machinery. So recall, hopefully you've seen these before, but feel free to ask me questions if you haven't. Recall that whenever you have a null momentum, say starting in Minkowski's space, it satisfies such a nullity constraint. And this is a nice quadratic constraint, which by now we know very well how to solve in terms of spinors. The idea, in 4 dimensions at least, is to construct a 2x2 matrix. You can recognize, if you stare at this for a while, that this is constructed out of P0 times the identity matrix, plus P1 times the first Pauli matrix, plus P2 times the second Pauli matrix, and so on. This particular matrix is constructed in a particularly nice way so that it has the following property. Its determinant vanishes if and only if the nullity constraint is satisfied. This means here alpha alpha dot are 2 component spinor indices, which in my conventions run from 0 to 1, but you might have seen them in supersymmetry literature. There are no plus minuses and things like that. So I'm going to deal with the same kind of spinors that you might have seen in other literature, but my spinors are just going to be bosonic 2-component objects rather than some fermionic fields. Super simple. So when you construct this P alpha alpha dot, this is a rank 1 matrix, a rank 1 2x2 matrix, and hence it can be split into a pair of 2 spinors, which you can write as the standard notation is lambda alpha and lambda tilde alpha dot. You distinguish them by the indices so that at least in Minkowski space, they are complex conjugates of each other. But we don't need to restrict ourselves to Minkowski space. We can just work with generic momenta, complex momenta, and at the end of the day, we can restrict them to be real. In general, complex solutions of the nullity constraint will have such a decomposition. And just to show you an example that these things do exist, here's a simple example of such a decomposition. You can take lambda alpha to be 1, z, which is the stereographic coordinate on the celestial sphere in Minkowski in Lorentzian signature. And the other one you can decompose as 1 times z bar, 1 comma z bar times an overall scaling, which you can further decompose as we do in celestial holography into a positive energy omega and a sign epsilon. Of course, any such decomposition, as you might have heard, is only valid up to little group redundancy. So there's a redundancy in this description, according to which if you scale lambda up and lambda tilde down simultaneously by the same amount, then this product doesn't change. So the momentum stays the same. So here I made some choice of real group scaling by fixing the first component V1, but I'm not gonna, in the rest of the talk, I'm just gonna work generally with some 2 component objects, lambda and lambda tilde. The scaling can be fixed tomorrow. Okay, so alpha dot are spinor indices. Just to quickly review, these spinor indices are 2 component indices. They can be raised or lowered by the symplectic form, this Levi-Civita type object, where in my conventions, all of these are the same. But you might see other conventions where epsilon with the upstairs indices are inverses of the ones with the lower indices. So just be careful depending on which speaker is using which convention. This is the Penrosian conventions we have. This is the correct convention. Okay, so here's some example. I defined lambda with an upstairs index previously, so the one with the downstairs index will just be contracted rightwards. Yeah, okay. Similarly, just a matter of notation that we in amplitudes use a lot. The spinor products of spinor helicity brackets are defined as contractions using this Levi-Civita symbol, but I've just represented it as a contraction between 1 upstairs and 1 downstairs index. Angle brackets are contractions between undotted spinors, and square brackets are contraction between dotted spinors. Any questions about the spinor helicity bit? Just this bit before I move on to defining twistors. Oh, everyone knows about this. Awesome. You can, of course, ask me later. You can stop me and ask me. This is the last talk, so it's fine. Okay, so the idea of twistors is very simple. It's the most obvious next generalization of the spinor helicity variables. The spinor, if you consider any massless particle moving in a flat space-time, there are 2 conserved quantities associated with the massless particle. One is momentum, the other is angular momentum. So you would expect that if there's such a nice spinorial decomposition for momentum, then there would be some nice spinorial decomposition for angular momentum as well. And that's what the twistor gives you. Well, that's what I'm going to write is a twistor will be something whose first component will give you a spinor helicity variable for angular momentum, and the second component will give you a spinor helicity variable lambda, which I discussed previously. To discuss this, let's begin with some of the basic technology, setting up spinor coordinates on space-time. So recall that you can start in Minkowski space with the standard Minkowski metric, dx0 squared minus dx1 squared minus. And you can write some nice coordinate system called double null coordinates, but I'm just going to call them spinor coordinates, which basically make the metric look like this du dv minus dw dw bar, like 2 different 2-dimensional metrics. And just because we're going to also discuss R22, let me just discuss the difference. In Minkowski space, U and V will be, oh yeah, here I've written, I sort of put down the expressions at the end of writing my talk. So I put them in a corner, but these are standard expressions that you would know in Minkowski signature. U and V are x0 plus minus x3, they're real and independent. And W and W bar are x1 plus minus I, x2, so they are complex conjugates of each other. And you can plug these expressions in this metric and get Minkowski metric. In R22, you can obtain the R22 metric by the most convenient choice is to Wick rotate x2, so that dx2 squared goes to minus dx2 squared. And when you do that Wick rotation, this I turns into x1 plus x2 and x1 minus x2. So you just get W and W bar to being independent and real as well. I'll continue, I'll not really use this notation much, so I'm just going to continue denoting this as W bar. So the takeaway is that in R13, WW bar complex conjugates, in R22, this matrix, all components of this matrix are completely real. Keep that in mind. That will be helpful. So, okay, now let's discuss how we define the conserved quantities associated to a massless momentum eigenstate. The momentum, as I discussed above, can be split into these spin helicity variables. Very nice. We use them every day. We like our Park-Taylor formula with our tea in the morning. So this decomposes into lambda and lambda Taylor. The decomposition of angular momentum, you might not think that this decomposes in any nice way a priori, but just plug P alpha alpha dot into that and you'll see that there's some nice structure that you can still have. And this nice structure, so to write this nice structure, you take M alpha alpha dot beta beta dot. So this is angular momentum in the basis of two forms generated by dx alpha alpha dot. So these are just spinor components, tensor components replaced by spinor components, composite spinor indices, sorry. But basically, it's defined like this, x times p minus x times p the other way. But what you can do is, once you write like this, you can decompose using the antisymmetry of alpha alpha dot and beta beta dot as composite indices. You can decompose this into SU2 irreps. So just because you're in 4 dimensions, the only way you can have such a composite index, alpha alpha dot being antisymmetric with another composite index, is if the thing is symmetric in alpha beta and antisymmetric in alpha dot beta dot, or the other way around. These are the only 2 possibilities you sort of get in 4 dimensions. So this is very nice. You can actually decompose this into SU2 irreps, and that gives you a pair of things. So the full angular momentum has 6 degrees of freedom, but now we decompose it into 2 objects of with 3 degrees of freedom each. Because now my M tilde alpha dot beta dot and M alpha beta are going to be symmetric 2 by 2 matrices. They're going to be symmetric in their spinor indices, while these Levi-Civita symbols are going to take care of the overall antisymmetry of the angular momentum. And if you convert this into 2 forms by just adjoining this with dx alpha alpha dot wedge dx beta beta dot, then you can show that this comes with the self-dual. This becomes a linear combination of self-dual 2 forms, and this becomes a linear combination of anti-self-dual 2 forms. So in that sense, these are associated to positive and negative helicity states. So for a positive helicity state, one of the angular momentum is going to be to annihilate that state, and the other one is going to be non-trivial, and the other way around. Now, to define twistors, you simply take each of these components and write down their spinorial decomposition. So this is fairly simple. Firstly, you extract, say, M tilde alpha dot beta dot by contracting both sides with epsilon alpha beta. Since M alpha beta, as I said, is symmetric in alpha beta, its contraction with epsilon alpha beta vanishes. And in my conventions, the contraction of epsilon alpha beta with epsilon alpha beta is just trace of epsilon. It's just the trace of the minus the identity matrix. So it just gives you a 2. So 2 comes the other side, becomes half of the full angular momentum, as you sort of intuitively want it to be. These are standard calculations in amplitudes, and you can, you should be able to find them in any old textbook. So now, just compute epsilon alpha beta, just plug in this expression for M, where I plugged in the spinor helicity decompositions of the momenta, and then note that, say, epsilon alpha beta contracts with this lambda beta up to a minus sign, it lowers the index alpha and contracts this factor of lambda alpha into the x alpha alpha dot. And similarly, here it lowers this index alpha, contracts into x, and it gives you a fairly beautiful spinorial decomposition of this self-dual bit of the angular momentum, where this mu alpha dot variable is now going to be my spinor helicity variable for angular momentum, as defined in terms of the position about which you're taking the angular momentum as x alpha alpha dot lambda alpha. Okay, and similarly, you can take the other one, and that gives you a similar symmetrized spinorial decomposition, where my convention is that you put a minus in front here because of some reason that I'll mention later on. Any questions about this calculation? This is probably the only explicit calculation I'm going to do in the talk anyway. Okay. So once you have these are what I'll call incidence. These are what are called incidence relations in the literature. But in the end, they're just a means of saying this is the data for angular momentum, like half of the data for angular momentum, chiral half. And this is the data for the other half of the angular momentum. Yeah, okay. So a twistor is basically just a chiral half of the angular momentum and a chiral half of momentum put together into a 4-component object. It's just mu alpha dot and lambda alpha. And a dual twistor is going to be these dual variables. So lambda tilde is the other chiral half of momentum, and mu tilde is the Spinor helicity variable that determines the anti-self-dual part of the angular momentum. So Tim is going to talk tomorrow about ambitwistors, which is going to be a sort of combination of twistors and dual twistors. But otherwise, today we'll just focus on twistors.
Andy had a question?
Yeah.
So if we were in 2-2 signature, then mu alpha dot lambda alpha would be real and twistor space would be 4-dimensional. Is that a fair way to say it?
It will be 3-dimensional because I will talk in a bit about little group scalings. So there will be an overall little group scaling which you'll have to quotient by. It acts on lambda as a Spinor helicity variable, but it will also act on mu. So it will be RP3 in the end. But I'll mention this.
Can I ask a silly question too? Like, for some reason, I guess maybe by limited exposure to twistor theory, but like the emphasis of mu as being an angular momentum is something I hadn't, I guess, seen emphasized as hard so much before. So is there a reason that you want to particularly phrase it that way? I like it.
Oh, I'm giving this talk to physicists. Sorry, I don't want to say it. Well, it's just the nicest way to introduce it.
It seems nice. I just like the, I mean, yeah, nice. Okay.
Sorry, I'm not Witten. I can't explain complicated concepts in a very nice way.
No, I was just like, are you going to do something like spin memory or something soon? Like,
I will let you know that
vibration is this like.
This is how Roger first came up with this, I think, because I revisited his first paper and that's where I found this interpretation. So it's fairly nice. If you, it's a fairly readable paper. It's just the notation is slightly different, but it's fairly readable. I will come to R22 specifically in a bit. At the moment, I'm just discussing it in general. Because that'll be helpful probably for Alfredo's talk. Okay, so this chiral half gives you a twistor and the other chiral half, which we can forget for the rest of my talk, gives you a dual twistor. Incidence relations are just these definitions of the mu and mu tildes in terms of the pieces, chiral halves of angular momenta. Okay. And lambda alpha, as I said, are homogeneous. Yeah, the better explanation is here. So there's a little group scaling that acts on these variables. As you saw earlier, it acts on, you can, recall that you can scale lambda up and lambda tilde down. So just consider the scaling of lambda for now. In angular, so since mu goes like x alpha alpha dot lambda alpha, mu scales the same way as lambda. And you can also check that the angular momentum, m tilde alpha dot beta dot, is mu alpha dot times lambda tilde, so that if you scale mu up and lambda tilde down, then the angular momentum is also in little group invariant. So the data for a twistor is only defined up to a scaling up for mu alpha dot as well as lambda alpha. So this turns into an overall scaling of Z. That's why it's meaningful to put these 2-component pair of spinors together, because they scale like a total 4-component object. And similarly, the dual twistors, Ws, scale down. because they look like mu tilde and lambda tilde alpha dot. So what is Twistor space? Recall that the celestial sphere, in Minkowski space at least, is a space of null momenta, so the space of lambdas. In Minkowski signature, at least, lambda bar is determined in terms of lambda, so you can just think of momenta as being encoded in lambdas. So the celestial sphere is just the space of all the lambda spinors. And the lambda alphas give you homogeneous coordinates on it. Twistor space is a simple extension of the celestial sphere to also include the data of angular momenta. In Minkowski's signature, mu tilde is also going to be the complex conjugate of mu. So it's determined by mu. So you can just think of lambda and mu, the space of lambdas and mu's. But in general, you can think of twistors and dual twistors separately if you like. One plays nicely with the self-dual sector, as I showed you, with m tilde alpha dot beta dot. The other plays nicely with the anti-self-dual sector. So Twistor space is just an extension of the celestial sphere. You're familiar with another extension of the celestial sphere. Null infinity itself is some sort of a geometric extension of the celestial sphere. Twistor space is very similar. It's an extension by 2 dimensions rather than 1 conical dimension. So it's celestial sphere plus the space of at least the chiral halves of angular momenta. And more explicitly, it's this set. It's the set of all z's, 4 component objects that can be divided into a mu alpha dot and a lambda alpha in C4 at the moment, such that lambda alphas are some 2 component spinors, and there exists some x, some point in space-time for which mu is given, mu gives the angular momentum data for a massless particle. Of course, you can consider the space of all such random mu's, but not all mu's will come from such x's and lambdas. But for those mu's that do come from such x's and lambdas, it gives you the data for, yeah, Andy.
The space of angular, self-dual angular momentum, that's 3-dimensional, right? 3 real dimensions?
Yeah.
So celestial
That's
sphere
3 real
dimensional. So then we get to 5 dimensions. Well, isn't it supposed to be 6-dimensional?
Well, that's actually correct, because that's the dimension of the space, the Twistor space of Minkowski space is indeed 5 real dimensional. That's a bit of an issue. This is exactly why we never discussed Twistor space of Minkowski space. But if you work with R4 then or R22, then you will get different dimensionalities. For R4, you get 6 real dimensions. And for R22, you get 3 real dimensions, so RP3.
Wait, but down here you're writing PT as CP3. That's 6-dimensional.
It's a subset of CP3 in general, depending on which
subset of C. Oh,
yeah, it's a patch of CP3.
C4 is 8-dimensional, and so you're doing 3 rescalings.
I'm doing an overall rescaling by the little group in C star, so that brings down C4 down by 1 complex dimension.
To 6, and then how do we get to 5?
We get to 5 by imposing the condition that these come from some real points x alpha alpha dot in Minkowski space, x alpha alpha dot. If the x alpha alpha dots are arbitrary complex numbers, then you get a top dimensional patch of CP3. But if the x alpha alpha dots come from, so if W, W bar are complex conjugates of each other, as I said earlier, then there are some algebraic constraints imposed on the twistor. It turns out that the twistor has to be real in some SU2, 2 sense. So it reduces down to 5 real dimensions. It's a bit of an issue. That's why we sort of never actually managed to make Lorentzian signature twistor theory go very far in terms of things like twistor strings or twistor actions. So we just work with the general stuff in CP3, and then we calculate something, say fully complex or in Euclidean signature, then we analytically continue to Lorentzian signature, at least at tree level. But that's a very good question. I was hoping to avoid that, but you brought it up, so thank you. So The basic idea, let me just repeat, that the space of twistors for completely general x alpha alpha dot will be given by those z's for which the first two components can be written as x alpha alpha dot times lambda alpha for some point in space-time, say some complex point in space-time, some point in C4 in general. Up to these overall scalings that came from little group scalings. And these scalings, again, can be arbitrary complex numbers before you fix your life in Lorentzian signature or 2-2 signature. And so this overall scaling basically makes PT a subset of CP3. Originally, it's a subset of C4, but you quotient it out. And since lambda alpha are always homogeneous coordinates on the sphere, there's always one lambda alpha which is non-zero. So there's always one component of the twistor which is non-zero. So it's always in C4 minus 0. And the quotient by scaling brings you down to CP3. Any more questions about this construction? Okay, cool. I'm assuming that that's because people are following, not because. So let's go to the first sort of non-trivial dynamical bit of twistor theory. Up till now, I just discussed the kinematics, so to speak, the momentum and angular momentum, the symmetries, how to transcribe the symmetries in twistor language. But now let's ask, is this good for something? Now, we are sort of accustomed already to asking such questions in Celestial CFT, because in CCFT, we ask whether we can find some theory living on the celestial sphere, which can describe four-dimensional physics holographically. There's a similar question here. Can we find, so twistor space, as I said, is an extension of the celestial sphere by angular momentum data. Can we find a theory that lives on this space, on twistor space, that can describe four-dimensional physics? And this problem, at least for on-shell fields, has been solved by Roger and Mike Eastwood and a lot of their students in the 80s. So this is called the Penrose transform. The basic idea is simple. Start with R4 with some metric of your choice of signature, but it's convenient to start with just arbitrary C4. I'm just not going to stop for too long on that. Then you construct R4 times S2, which is the space of all the x's and the space of all the lambdas. And then there are two maps. One map into space-time, which is just the projection from R4 times S2 to R4. And the other map is given by, there's another natural map from R4 times S2 into CP3, which is given precisely by the twistor construction, the construction of mu. And this is the incidence relations map. And this tells us, okay, so one way you take x lambda, you go to x. The other way you take x lambda and you contract, you write x dot lambda, comma lambda. So this is my mu and this is my lambda. That's my twistor. The Penrose transform sort of reverses this. It gives you a means to start with data on CP3, some holomorphic function or some holomorphic one form or things like that, some complex structure type data, pull it back by the incidence relation to R4 times S2, which is usually called a Spinor bundle in literature. And then what's the natural thing you can do on R4 times S2, some field on R4 times S2 to get a field on R4? You can compactify, or you can take its zero mode in compactification, which is literally just integrate along the S2 fibers. So here's the sort of flow chart. We'll start with some holomorphic data on CP3. The idea is to pull back by the incidence relations. And it is at this stage where I will forget about the angular momentum interpretation and just start treating this as abstract, some abstract correspondence. So you pull back by this map, you get some data on R4 times S2, and you integrate it along the S2 to get something that you can prove solves the wave equation on R4. So you can actually generate a classification, at least, of solutions of the wave equation in terms of some holomorphic data on complex projective 3 space. And the kind of characteristic example that at least Tim will use tomorrow is what is called a Dolbeault-Twistor representative, which is defined as an anti-holomorphic one form with holomorphic coefficients. So I'm going to stay in the simplest category of such one forms. I'm going to take a one form, which is an anti-holomorphic one form along the celestial sphere direction of Twistor space. So d lambda bar is in homogeneous coordinates, the standard anti-holomorphic measure on CP1. But if you're confused by that, just think of putting some z bar coordinates on the celestial sphere and just think of this as dz bar, d little z bar. So, and we're going to require that the coefficients of this one form are holomorphic in the capital Z's, my Twistor coordinates. And any such data, you can pull back by the incidence relations by setting mu equals x dot lambda in these coefficients, and you can integrate it along the celestial sphere. So you integrate it along the constant one form, d lambda, along the celestial sphere. This is again a measure which in affine coordinates, it just reads dz. It's a measure on CP1. The only requirement is that this holomorphic coefficient, the holomorphic form omega, have the correct homogeneity for this integral to be well defined. So in this case, d lambda is lambda d lambda. So under a scaling of lambda, under little group scaling, lambda scales up. So lambda d lambda scales as t squared. You simply demand that omega, this one form, scale by t to the minus 2. So that this actually gives you a well-defined conformal integral on the celestial sphere.
Okay, can I ask one question? In your statement where you're uplifting and going back down, is there any natural sense in which the object that's a function of R4 cross S2 is like a conformal primary wave function that like, right, is covariant on the sphere and in the bulk it satisfies the wave equation, or there's no?
I will give you an example of this, and I chose to give the boost eigenstate example in a bit, yeah. Because of its relevance, yeah. Okay, so, but just the general thing, you can show that such an integral formula gives you a solution of the wave equation. You just compute box of phi of x, where phi is defined as this integral formula, and this gives you d lambda. Okay, now that's a bit of a computation. So I've just extracted d lambda bar out. F was the coefficient of this one form, the coefficient of d lambda bar. So I act with these operators on f of x dot lambda lambda, but the only dependence of x is in the first entry x dot lambda. So the derivatives turn into, so d alpha alpha dot turns into lambda alpha d by d mu acting on f. This is just chain rule, nothing deep happening. And now, because box is defined, so, okay, sorry, I didn't mention this earlier, but the metric in the spinor coordinates looks like Levi-Civita symbols, a product of two Levi-Civita symbols. So the box is naturally defined in the spinor coordinates as two Levi-Civita symbols contracting two position derivatives. And it's because of these Levi-Civita symbols that these pair of lambdas that come out on doing this differentiation contract into each other and die because of antisymmetry. Because of the symmetry of lambda alpha lambda beta. Is that somewhat clear? The moral of the story being that you can construct such integral formulae that give you solutions of the wave equation, and they also give you solutions for the spin 1 linearized field equation, spin 2, spin 3, and all of them. 3 halves, 1 half. You can also do it on curved manifolds, at least curved self-dual backgrounds. Lionel's making his PhD, another one of his PhD students do that. So, okay, so similar tricks also have spin linearized field equations. So just to give you a concrete example, which I guess Tim will use to some extent, we can write down the Dolbeault-Twistor representative omega for a boost eigenstate. Yes, Sabrina.
Oh, sorry, a very dumb question again. Like, you didn't need that integral to still, like, you could have defined an object that's still dependent on lambda, but was, I'm sorry, I'm curious if it's the antisymmetry in that epsilon that's giving you the solutions to the equation of motion, or can you still just for the sake of trying to do these CPW things, can I have an object that doesn't integrate over the d lambda bar that satisfies the equations of motion as a function of x, but like is still a function of the celestial sphere? If I wanted to.
Oh, you're starting with something
exactly.
that's a function of x dot lambda lambda. If say you take a constant lambda and then say that this f is only a function of a particular x contracted into some particular lambda, then that's just a standard solution of the wave equation. It's a function of x plus t and x minus t.
Sure, but I guess the question I would have is like, is there like I'm just trying to basically go instead of from the particular Mellon representatives, which I think is easier to see the vertex operators in your construction, like how I would try to go back and reconstruct like conformal primary wave functions where there's this like auxiliary dependence on that S2. So I know I'm like, I don't want to sidetrack a bit.
So the nice thing about the conformal basis states is that they don't depend on any reference spinors.
No, they do. Sorry, I'm sorry. The states don't in the end, but I'm saying that there's something nice about looking at wave functions that do have like a kind of a bilocal dependence, like one foot on the celestial sphere and one in the bulk, right?
Yeah, solutions of the wave equation in the bulk, which are parameterized by points on the celestial sphere.
Yeah.
So I'll show you. Yeah, I'll just write down the representative of this kind exactly. But here, at least, you wanted to get rid of lambda, and the most natural thing is to integrate over lambda. That's why I did the integral. Sort of average over all lambdas. Okay, so what happens for boost eigenstates? I'm going to use some simple spinor notation. If it's too heavy, feel free to stop me and ask. So you want phi delta of x to look like 1 over q dot x to the delta. Yeah, Sabrina. Are you muted or am I not hearing you?
I think my hand was still up from before and I like scratched my hair.
Weird. I saw a tiny message, so okay, never mind. This phi delta can become, well, this is the state that we want. I have dropped the gamma of delta factor as usual. So what is the Twistor representative of this state? The natural Twistor representative of this state is going to be, let me just say that this Q is going to be my normalized null vector, which contains the information of Z and Z bar. So it's basically X alpha alpha dot contracted into 1Z and 1Z bar. Okay, so the Twistor representative is given by one form omega, which takes such a form. You want to arrange for two things. The coefficients should be holomorphic or meromorphic, so to speak. That's also fine. So strictly speaking, this is only defined for integer delta, but since we actually live in R22, we can sort of work with arbitrary delta. So don't worry about that too much. But you want something whose coefficient, some differential form whose coefficients are meromorphic in lambdas and mu's. I think earlier I said holomorphic, but meromorphic is fine. And which is an anti-holomorphic one form along the celestial sphere direction. So here I have and it should have homogeneity of -2 overall. That's the more important thing. So here we have just arranged for such a thing. So one easy thing to guess is that you can try to replace q dot x by firstly x dot zeta zeta tilde, and then those incidence relations x dot lambdas. You can try to replace x dot zeta by mu. That's the most natural guess you can make. So just replace the factor of q dot x to the delta with a square brackets mu zeta tilde. So this is just mu alpha dot contracted into zeta tilde alpha dot whole to the power delta. Then I want something that localizes me to lambda equals zeta, because when I use my incidence relations mu equals x dot lambda, I want a delta function that sets lambda to zeta, which will give me mu equals x dot zeta, and that will give me q dot x here. So I just append this with the delta function. This delta function, the notation, just to say, because you'll probably see this notation in Tim's talk tomorrow, this notation that it has a bar in it, it just means that I have a secret dz bar or d lambda bar type one form hidden in the delta function. I think this notation was introduced by Witten in some 2005 as well. But forget about the d lambda bar. The point is there's a delta function which imposes that lambda is along zeta. And then to ensure that the thing has a correct homogeneity of -2, you simply use a reference spinor. The nicest reference spinor is just 0, 1, because the contraction of this reference spinor into zeta will give you just 1. So, and you simply multiply this with a polynomial in lambda to cancel the weight. So the overall weight in Z, so you can check, you scale mu and lambda up by the same thing, say t. So you'll scale the denominator by t to the delta. And the numerator here is a polynomial of order delta -1, so it'll scale as t to the delta -1. So the overall scaling is t to the -1, but this delta function scales like -1 in lambda. So the overall thing scales like t to the -2, and then this integral formula will be well defined. So plug this into the integral formula, you made all your guesses, you pull back mu by the incidence relations. So in standard notation that you'll see a lot in amplitude literature, you just write x alpha alpha dot lambda alpha zeta tilde alpha dot in terms of this concatenation of brackets, where this just means x, the alpha index of x contracted into lambda, the alpha dot into zeta tilde. And integrate over the celestial sphere. This delta function is defined so that it exactly sets lambda to zeta when the whole integrand has zero homogeneity. You don't need to sort of dwell on the details. I don't want to annoy you with the details. It's just that it gives you the nice answer that you want. And basically what did I do? Why is there a red sort of lines in front of my screen? What have I done? Did someone try to annotate it or something?
No.
I can't remove it, so I don't know.
Oh,
so yeah, as I was saying, this sets lambda to zeta. So the new denominator you get exactly to be q dot x over delta. And the numerator you get the contraction of iota with 1z. And in my conventions of angle bracket contractions, the contraction of 0, 1 with zeta is the determinant, 0, 1, 1z. So it just gives you 1 or -1, whatever. So sorry, I didn't mean to sort of annoy you with the details, but I just wanted to sort of give you a flavor for how these Penrose transform calculations are carried out. Laura, do you have a question?
Yeah, Atul. It's just, yeah, it's a question about somehow, can you explain a little bit what you have gained there, right? There's a simple expression to start with. Now you have expressed it into Twistor space. I'm not asking these questions to embarrass you, just so that you can make your point about why somehow, if I'm a student now, I should kind of care about the fact that I'm able to do that. Is there, or do I have to wait? You know?
No, so there are two reasons. One that I can mention now. The point is on Twistor, on space-time, okay, I took a very simple example here. But on Twistor space, you can construct solutions of the field equations by just giving any metamorphic data. So as I said, you take any arbitrary such one differential form on Twistor space on CP3, and that generates a non-trivial solution for the wave equation on space-time. And this freedom is sort of what you gain when going to Twistor space. Of course, I gave you a specific example where you didn't computationally gain very much by working with the Twistor expression versus the space-time expression. But in general, you work with more complicated states, and then you see this as giving you some sort of way to classify all solutions of wave equations in terms of simple holomorphic data. Like you might be familiar with this simple cohomology data on Twistor space, which you can compute by other topological or geometric means more easily, maybe. Of course, the real power lies in the self-dual nonlinear field equation solutions, but I'm not going to go to that. And the other thing was that it'll be useful for Tim tomorrow.
Okay, so there's more questions. Andy is next.
Yeah.
Could you just how the boosts, how do they act on Twistor space again? It's just rescaling of.
The little group scaling acts by rescaling mu and lambda both up.
Both up.
Yes, that's
So-
why you can think of this as a single 4-component object. Yeah.
But that's a boost in which direction?
Probably towards Q.
No, the final thing, this thing doesn't scale. This is completely well-defined. It's a redundancy of the Twistor description which drops out.
But somehow
Then-
it comes back in when you're looking at like the single particle states corresponding to these guys in the end, right?
No, it should boost under a boost. Phi delta scales by lambda to the delta, right?
Under scaling of little x, you mean? Of the space-time coordinate, you mean?
So the funny, I think
Oh,
there's
no,
something-
L naught plus L naught bar. It's a
Right, the full dilation. Yeah.
delta is the eigenvalue of the boost. So how did the boost act? I think you said it on the last.
Ah, okay. Yeah, so the boost acts on the external data zeta tilde here. I think it doesn't. Oh, wait, sorry. What should I? Okay. Yeah, sorry. So there is a way to take the Lorentz symmetry of space-time and lift it to some sort of symmetry action on Twistor space. And in that way of, and that is exactly derived using the incidence relations. So mu goes like x dot lambda. And if you scale x up under such a dilation, then mu will scale the same way. That's the kind of, and similarly, you can get translations and rotations as acting on Twistor space more generally by simply changing x and then seeing what transformation of mu and lambda will compensate for that transformation of x. So in short, it scales mu up, but doesn't scale lambda because it only scales x. And mu is x dot lambda. So it scales x.
It's a boost in the along Q, right?
Right. So what are you gonna act the boost on, x or q? I mean, which way are you thinking about?
Delta is defined as the eigenvalue of the function under boosts.
Right. So you sort of act on x and you act on q with some rescaling. So the Lorentz transformation of q and x get canceled, but q also has some rescaling. So it generates some non-trivial transformation of the wave function. So yeah, the same way you'll act on mu. Mu takes the role of x here. Lorentz transformations act on mu now as SU2 transformations. And zeta tilde takes the role of q here. So Lorentz transformations again act as SU2 transformations up to the overall rescaling, which comes out.
Okay.
Oh, no. Sorry. Yeah.
Oh, no, exactly. I was just saying.
Sorry, my question is going to be really silly. I'm following all the steps, but I missed why you need to have the I lambda to the delta minus 1 in the numerator. It seems like everything goes through without that factor. I feel you briefly mentioned that like that's not so important, but you need
The
to mind.
integral is only well-defined if it has the correct homogeneity. It's just that.
Oh.
Because the denominator is a polynomial of homogeneity delta. Well, polynomial.
But it like literally gives one in your reference example. Right?
It gives one at the end of the day. That's why it's the correct Twistor representative. If you took another reference paper, that would not give one. It would give some, Sorry.
Thanks. Laurent now.
Yeah.
Yeah, maybe just a question of clarification about that. So if you change the representative, that I into something, do you just get a closed form that integrates to 0? Is that the idea? That this representative is, because this representative looks like you're breaking the Lorentz symmetry by picking a preferred guy, but somehow that preferred, axis must disappear in the integral. Right? So if I to I prime
So you can actually write this expression as a, what happens is this expression is actually independent. I lied a bit. You can choose any other reference spinner here. It gives the same answer because this I lambda to the delta minus 1 is actually independent of I on the support of this delta function. This is because on the support of this delta function, lambda is proportional to zeta and I acting on zeta always gives you 1, so it always drops out. So it's sort of, I don't want to go into the details, but you can actually use any, you can in fact even write this as a manifestly invariant thing under Lorentz transformation, but then it turns into an integral over all possible such reference spinors, which is manifestly independent of the reference spinor, but I didn't want to go into the.
Okay, so it's not true. If you take an omega I minus omega I prime, this object is a closed form.
It doesn't
zero, no?
It's not that the point is it doesn't become that complicated. It just drops out immediately. If you change the reference spinor, the difference between the two reference spinor is just 0 on the support of this delta function. Yeah. In general, you're right. In the Penrose transform is only defined up to closed forms, and because closed forms integrate out to 0 when you do the integral. It's just simpler here. Okay, thanks for the loads of questions. Laura, do you have another question?
No, sure.
Okay, yeah, sorry. So I should speak about twistors in R22, hopefully for Alfredo's benefit, if nothing else. Oh, sorry, of course, for if you want to listen to the bonus part on W infinity at the end, you can stay on for half an hour extra. I did seem to have, gone over. So twistors in R22, I'll just try to go somewhat quickly over this because I want to describe twistor strings as well. So real twistors, as Andy noticed quite quickly, in R22, lambda and mu, lambda tilde and mu tilde are all real. But just to be explicit, in R22, P alpha alpha dot can be written purely in terms of real objects, real 2x2 matrix, by Wick rotating P2 into IP2. This turns into P1 minus P2 and a P1 plus P2. And the nice thing is this simple Wick rotation makes the determinant of P vanish exactly when the momentum is null in a 2-2 signature bilinear form. Now lambda and lambda tilde are real and independent of each other. That dot should be there, but okay. Lambda, lambda tilde are real independent spinors. So you can, this is very nice. And this is a theme that is common to many experimental papers in the amplitudes community where you sort of work in R22 and you sort of access a lot more singularities in R22 that allows you to, I don't know, bootstrap amplitudes or do a lot more things than you can do in R13, where you can access very few of the singularities. But okay, that's just some motivation to study R22. Of course, there's an immediate Celestial CFT motivation because the Celestial OPE based motivation. I'm not sure if somebody talked about Celestial OPE today. I've forgotten.
Yeah, Andrea talked about it enough, I think, for this, but
Okay.
I think the key part you're going to see with the fact that you need to actually be careful about Z versus Z bar was only a little bit emphasized.
Exactly. So the Celestial OPE can be written in somewhat more independent, nice way in R22 signature. X alpha alpha dot is also consists of just a bunch of real coordinates. Now W and W bar become real and independent. So just like lambda was real, mu also becomes completely real. And now if you restrict yourself to real non-zero little group rescalings, then everything stays real. So just the simple restriction acts on mu and lambda as real non-zero rescalings and reduces you down to real projective space. So just to remind you, lambda goes up, X doesn't scale, so X dot lambda goes up, so mu goes up. Mu lambda goes up and you quotient out by these scalings because you want to quotient out the little group scalings. That reduces you from R4 minus 0 to real projective space. And you can think of mu and lambda as homogeneous coordinates on this real projective space. So this is very nice because now you can do stuff like half Fourier transforms that you might have heard in fancy talks. So that's what I want to set up quickly. Firstly, we want to find an interpretation of mu in momentum space. Okay, so the thing is, the main question is we want to develop an analog of the Penrose transform for RP3, which allows us to take data on RP3, not CP3. We don't want complex. We are real and nice people. So we want to take data on RP3, and we want just that much data to give us non-trivial solutions of the wave equation or R4. And that can be done. I think it was developed by Tia and friends again. It's also called the X-ray transform, John Fritz's X-ray transform, radon transform, stuff like that. And you can develop it fairly quickly by going to momentum space. So firstly, you start with a solution of the wave equation, and you want to represent it through some Penrose integral formula. How do you do it? You start with its momentum space description. So this is just a Fourier transform phi of x, but since phi solves the wave equation, it's supported in Fourier space only along the light cone. So only along the Lorentz invariant phase space measure, I don't know, d pi ellipse or whatever Srednicki calls it. And P is my momentum, which I can decompose into lambda, lambda tilde. So my Fourier representative is just a function of the spinors. Now, it's a standard calculation. I don't have time to do this, so I just want to mention it. In passing, you can show that m tilde alpha dot beta dot as an operator x mu d by dp mu minus x nu d by dp mu as that operate, sorry, p mu d by dp nu minus the other way around acts. It also splits into spinorial components. So the self-dual part of the angular momentum operator acts like this. And you might have seen this when computing soft theorems, for example, like the Chazo-Strominger paper in which they compute the soft theorems, and this angular momentum generator pops up, and then you sum over stuff and it kills the amplitude. So this is just as complicated as it gets. It's fairly simple, just a linear generator. And now we want to identify the twistor mu, or the mu bit of the twistor in momentum space, how it acts. And the identification can be done easily by just noticing that it has to give the angular momentum. It has to give an operator. So now the natural identification is to identify mu with d by d lambda tilde. So this tells you, this is what really tells you that mu is to be the Fourier conjugate of lambda tilde in 2-2 signature when everything is real and Fourier transforms are defined. Witten probably also starts something like this in its paper. If you read his 2003 paper, he motivates it using symmetries and stuff, why you should use this Fourier transform. Now, let me define for once the half Fourier transform of the Fourier transform. So the Fourier transform f hat was a function of lambda and lambda tilde. You Fourier transfer it further in lambda tilde. And as I said, the Fourier conjugate of lambda tilde is my angular momentum bit mu. So it becomes a function of mu and lambda. What is this good for? You simply plug this expression. Oh, sorry. You invert this. So you write f hat as the inverse Fourier transform of f of mu lambda and plug this into the Fourier expansion of phi of x. Then you do the lambda tilde integral and the mu integral, and out pops a completely real analog of the Penrose transform. So I didn't want to go through the calculation. This calculation, I should have cited. This is a nice calculation. It's given in It's given in a paper by Lionel Mason, my supervisor, and David Skinner from 2007 or 8 or something. It's in an appendix, so it'll be very hard for you to find. But now that I've told you, you can. Otherwise, you'd end up reading a TS papers, and you don't want to get into group extensions, believe me. This is easy. So, but the basic idea is very easy. Just write f hat as a half Fourier transform of f of mu lambda by inverting this. Sorry, I wrote it this way. I should just written it the other way around. And then plug it in here. F hat of lambda lambda tilde as integral d2 mu e to the minus I mu lambda tilde f of mu lambda. And then just see what expansion of phi you get for phi of x in terms of these wave function f of mu lambda. This is, you guys are very familiar with this. This is just a basis change. I'm just changing my basis to f of mu lambda. And you get out pops the nice Penrose transform when you plug okay, let me just say it. When you plug this e to the minus I mu lambda tilde here, the lambda tilde integral, well, you can write this integral as a d lambda tilde integral. That becomes extremely easy to do. And it's just e to the I mu lambda tilde minus I x dot lambda tilde. You integrate over lambda tilde, you get a delta function. That's the Fourier representation of a delta function. And that just tells you that mu equals x dot lambda. And thus, you're only left with an integral over lambda. The mu integral gets done using the delta function and just sets mu to equal x dot lambda. So that's the real Penrose transform. Andy has a question.
Yeah, I'm still having trouble counting up to 4 here. So mu and lambda now we're in 2-2 signature. Isn't f a function of 4 real variables?
Yeah, but it has some homogeneity now. So
but if we have a function of 4 real variables and we integrate it over something, how phi is a function of 4, x is 4 variables, right?
Yes.
So I guess the weird thing is that you basically, all these transforms are just doing weird things in this 3 manifold that's at the boundary up to some weird signature choice. And then eventually you're going into the bulk with this one.
The point is you're integrating over RP1 rather than R2. So you can fix the scaling of lambda. Lambda is homogeneous coordinates on RP1, but you can fix lambda.
Phi is only really a function of 3 variables because it's subject to the wave equation.
It's like the estimate, yeah.
Oh yeah, exactly. Exactly.
Oh, okay.
Lambda, just like lambda tilde have only 3 degrees of freedom.
Right. Okay.
Mu lambda also, yeah. And here it's particularly clear because this is just a Fourier transform. Thanks, Sabrina. Okay. This solves the wave equation, but that calculation is identical. So I'm not going to repeat it. In fact, it's easier here because you don't have a d lambda bar wedged against it. Yeah. So that's my real Penrose transform. Does anyone have any further questions on this section before I go to Twistor strings and sort of have a change of tack? Right, okay. All right, let's move on. So hopefully that will set up some things in Alfredo's talk. Let me try to set up some things in Tim's talk as well, because I promised him I will. So Twistor strings are something that sort of you can experimentally discover by starting in R22 and doing Penrose transforms and, doing all these half Fourier transforms to mu lambda basis of states. And I'll give you an example if I have time. But once you sort of discover it, and that's what Witten did, sort of started with the Park-Taylor formula, and he half Fourier transformed everything, and he saw that, the half Fourier transform, the amplitude in mu lambda variables, amplitude on Twistor space has a very nice, easy to guess world sheet representation. And then he half Fourier transformed back to get a world sheet representation of amplitudes on space-time in momentum space.
Can you do the same thing with RP3 instead of CP3 in this context, or no?
You can experiment with RP3 and then generalize it to some string theory in CP3, which works on all signatures.
And then a dumb question, like in the end, would that be like the world sheet, the target space is null infinity in some weird sense? I mean, in this weird, like we're taking the S matrix, which is a function of lambda and lambda tilde, which basically is a function of an energy variable and the sphere. We could Fourier transform, so it's a function of U in the sphere. So we have basically null infinity, and then inverse all these transforms to eventually get back to the Twistor space, I guess.
Yeah. And unfortunately, it doesn't. One would have loved for that to happen.
Yeah.
But the topological B model requires complex Calabi-Yau threefolds. So
So where does it go wrong? If you just tried to very naively, like if the last thing that you ended on, it looked like I could take the S matrix, which is my f of lambda tilde, and I could do whatever transforms I need to turn it into this f of.
Nothing goes wrong. You get the answer.
Yeah.
You get a beautiful world sheet formula, but you can't prove that it comes from a world sheet model, a string theory.
Okay.
It only comes from a string theory that lives on CP3 rather than RP3. That's the problem. The
like,
formula exists because you can restrict it to any external data you like.
But if you wanted to, is there some sense in which you could think of this worldsheet model, like the target space as being a complexification of null infinity then, or isomorphic to it up to these weird integral transforms that we're doing, or no?
Yeah, something like that. Okay. It's based, well, the complexified Twistor space, so slightly more extension of general relative of Scri, slightly bigger than Scri, but yeah, the idea is exactly that. You complexify Scri, and then you add these angular. You complexify the celestials.
Yeah. No, because maybe we're saying that in the case that you were doing with this real example, it doesn't look like it's bigger than Scri. So something, I guess this is the same thing Andy's asking about, like what happens in these, like, I mean, obviously like the dimension.
Oh yeah. In the real example, RP3 is 3-dimensional. So you do seem to have some sort of a holographic correspondence, but there's no theory. There's no dynamical theory that you can put on RP3 that generates the worldsheet formulae.
And so
that's the problem.
So the issue.
String theory doesn't work. Yeah.
Okay, cool.
You might have a RP3 version of BMS field theory. I don't know. Yeah. Which might be dual to some celestial CFT on the celestial torus on which the RP3 fibers or something. I don't know.
So is there any sense in which you think that you can just like do some sort of weird analytic continuation of this to land on some like some image of this working out into the CP3 case, and then you try to pull back the Witten story, or I don't know.
Well, you can't pull it back because CP3 and RP3 have different dimensions. So
it's like, I'm saying you take the RP3 and then you complexify it or something like that, because we're saying that we're taking the 2-2 scattering.
Yeah,
maybe, like
exactly.
And then we're complexifying it, and then we want to.
That's exactly what we do. We start with RP3. We write the formula. We guess the worldsheet formula on RP3, and we complexify. Then the complexified formula lives on CP3, and that can be written as worldsheet correlated of an actual topological string.
Is that what Kevin's basically doing? I'm sorry if I'm like asking a basic.
Well, I haven't written notes on it, but I'll talk about what Kevin's doing just in words at the end.
Awesome, thanks.
Yeah. So just to tell you about Twistor strings, the worldsheet model is a worldsheet model with a complexified Twistors with the fully complex gadget CP3 as target space. You can use homogeneous coordinates as your target space coordinates. It's up to some rescaling constraints that you can impose as some gauge symmetry of the model. So we use Z and W as Twistor and the sort of dual Twistor coordinates. So Z will be the coordinates. Sigma is worldsheet coordinate. ZA of sigma is my map that takes me from the worldsheet to my target space CP3. There will be a constraint that will gauge various scalings of Z that I'll mention in a bit. W's are going to be the momentum variables associated to Z in some sense. You can think of W's as not being some extra dimensions of the target space, but just as the momentum in a first order formulation of string theory. The action, I won't write all the ghosts and stuff. I'll just say the basic bosonic bit of the action. I haven't written the current algebra that generates color factors as well, but just the basic bosonic twistorial part of the action is very simple. You take d bar, which is partial sigma bar, the standard anti-holomorphic derivative on the Riemann sphere, and you write the theory in a first order formulation as some momentum contracted into some sort of time derivative of the position, W d bar C. You have to sort of, since W and Z have 4 and 4 complex degrees of freedom, you have to impose invariance under little group scaling. So you want to impose invariance under scaling Z up and W down. This is imposed by a specific constraint, which is basically a very simple U1 gauging. So E is a gauge field, and you couple it to a current that generates the U1 scalings, or the scalings of W down and Z up. This is just W dot Z. If you write the Hamiltonian formulation of this model, then W dot Z is the generator of rescalings of Z up and W down. And so you impose this, but then this imposes a constraint that W dot Z is 0 as well. But that is also something you wanted, because if you recall the incidence relations, then mu and mu tilde weren't actually independent quantities. They were related, and they were related precisely by the fact that W contracted into Z which is basically just 4-component notation for mu contracted into lambda tilde plus mu tilde contracted into lambda. If these mu's and mu tildes come from some angular momentum data, then they can be written as x dot lambda and x dot lambda tilde. These sum to 0. So this constraint is indeed something you would have expected from your incidence relation constraint. But at the level of the sigma model, this also generates rescaling. So this is a very nice thing. I do not know why I explained this, actually. I'm not going to talk about this. Sorry.
You want to know, thank you.
Might have been about time. Since I just wrote it down, I just said this in words. The actual thing of importance is the application that worldsheet correlators of this model compute scattering amplitudes. And you can, since you're living in CP3, you're free to compute it with any external data you like, real, complex. Yeah, Andy, do you have a question?
Yeah, so this is related to what Laurent was saying. So you've been talking about the Twistor construction, and it looks like, to sort of put it in the worst way, I mean, Laplace solved the free wave equation 300 years ago, and it looks like an awful lot of work to do to solve the free wave equation.
Yeah.
And I think the thing that's, so it doesn't seem very impressive that you, at this point, what you said so far, it doesn't seem very impressive that you do this and you solve the free wave equation. However, I guess at the classical level, and I don't really understand very well why this works, but the amazing thing about Twistors is that then once you've solved the free, then you can add the nonlinear interactions and you can solve the interacting full self-dual gravity sort of without sort of, losing a breath. It's sort of, once you've done this, why you get to add the interactions for free once you're in Twistors, boys, I've never understood that. I mean, it seems there are many ways to complexify Minkowski space and have Fourier transform, and I don't understand, I don't have the intuition what's special about this one. And here you're doing it like, if you just write down some random complexification according to Minkowski space and you make a string theory, you could certainly get out the free, wouldn't be hard to give something that gives the free, gives back the free theory. But now all of a sudden you write down this string theory, and now all of a sudden you get the scattering, the interacting scattering amplitudes. So it seems to be obvious to everybody in the field why this works, but I'm still mystified by it.
Oh, it's not. It's it's not obvious to everybody. It is somewhat mystical.
No, may I?
Yeah.
Is it because there's a bunch of shells though, and they're like weird?
No, this is something we know as relative locality written in Twistor variables. And the reason why it works is that local interactions in this kind of language are the consequence of positing conservation of energy and momentum.
Well, so then you said something which confuses me even more, which is you did a half Fourier transform, and then you have local interactions. So why you would get anything back that's local in space-time when you're working in a half Fourier transform space? That's also mysterious, right? But you seem to understand why it's true.
Well, not as well as I'm pretending, but I think somewhere in there, as long as energy and momentum conservation are written in with the rules, it has to come out that way.
So then, would you say you don't expect locality? I mean, you expect only locality at the boundary of the bulk or something like that in the end? Is that what the, because somehow—
No, this is just, well, maybe let's postpone this to more reflective discussions, because that's just my first impression.
I don't know about this, so I'd be curious to listen.
Yeah.
Yeah, but I don't want to hijack. There's a whole thing called relative locality and why local physics emerges from conservation laws rather than reverse.
Sorry. Could you just? I think I misunderstood between the two. You're saying it should be local in Twistor space. It should be local in space time.
In space time.
Okay.
That's very similar to some stuff that Kevin's doing, that this theory on Twistor space has some anomalies. And if those anomalies in certain symmetries, if those anomalies cancel and the symmetries are preserved, then exactly those local theories on Twistor space descend to local theories on spacetime.
Yes,
It might be related.
I think it's got to happen. It's like an inverse Nether theorem.
Oh.
Wait, why would the locality be okay? Okay.
So stuff that is local on spacetime is non-local on Twistor space because it's sort of smeared over the sphere direction.
Yeah.
But what is relative locality?
This is your talk. Let's not.
Sorry, I'm very bad at this. I sort of end up distracting myself.
We're trying to get you to visit for a minute.
we will, don't worry.
I guess I'm with Andy there. The question he's asking is, can you give us a sense of why, now that you have these twistors, somehow interactions, like, adding the gravitational interaction is kind of more natural. How you couple G Newton is supposed to be more natural, right? That's the hope, or that's the expectation.
Or at least half the theory for the self-dual part.
Well,
expansion around the self-dual.
Even for the self-dual, I know there's this wild mathematical magic, but
it's not magic. It's just that you have.
It is to me, maybe to Andy too. I'm saying there's anyway. Why suddenly adding G Newton? There's a natural way to add G Newton. That's what you have in mind, Atul.
Yes.
Right? But it's not.
Is my Wi-Fi breaking?
I think this is really important too for celestial conformal field theory. I mean, if you had done a full Fourier transform instead of a half Fourier transform, and then did this, you wouldn't reproduce the scattering amplitudes. And in celestial conformal field theory, we're struggling with: do we want the original fields? Do we want the light transform fields? Do we want the shadow? We don't quite know what the good set of variables are, and somehow in the Twistor world it's known, but I don't.
But it seems like we know how to go between them, though, and that's I think that was the best part of Atul's solo paper on, beside the basis stuff, because once you can go between them, I feel like somehow they're all equivalent at some level, and the subtlety is in how you're complexifying.
Wait, they're talking about the free level, but not that. The question is about the interaction.
Like literally every talk has ended on a technical. At least not started. I feel like there's a little gremlin here. We'll give him a little bit of time to come back on. If it was a power issue, it should be fine.
There are various kinds of power issues.
If it's a local power issue, sorry.
Sorry, I don't know what's happening. Maybe it's after 7, the Wi-Fi starts breaking. Maybe the department's shutting down. I have no idea. Let me try to reshare. Can you make me?
If I needed for the gong show, I didn't need a gong. I could just like drain the battery of someone after 7 minutes.
Make me a co-host again.
Oh, yep. Sorry for this. 1 second. Make a co-host.
Awesome. What are you saying? Okay, let's continue. Let me try to wrap up. The main application of this Twistor string technology that also is useful for computing, say, celestial OPE, collinear soft limits that Tim will talk about tomorrow, is that Twistor strings somehow encode interactions, at least at a perturbative level. And so they compute amplitudes. The vertex operators in these strings will be discussed by Tim explicitly, but I just want to tell you their generic structure. The general structure is that vertex operator will be an integrated vertex operator on the, so like just in a usual string theory, you have an integrated vertex operator that comes with the wave function. And in heterotic string, you have a current that generates the color factors. So you can forget about this current algebra bit. It's just a heterotic string type object. But the main bit is this wave function, which you have pulled back to the world sheet This is our Twistor representative now. So this gives you an anti-holomorphic differential form. It's along d sigma bar after pulling it back to the worldsheet. So the integral is well defined. And now this is why I sort of explained all that Dolbeault-Twistor representative, because tomorrow Tim will sort of use the fact that those Dolbeault-Twistor representatives are exactly the objects that enter vertex operators of such, in his case, ambitwistor string, where W's and Z's will both become variables of the target space. Awesome. So this will be repeated by Tim in more detail tomorrow. But I just wanted to show you how you can actually use the half Fourier transform to motivate the Twistor string formula, say at the MHV level. So this is again for people who know a little bit about amplitudes. For people who don't know about, actually, if you're tired, feel free to sleep, take a nap now, regardless. So here you have your Park-Taylor formula. Suppose you work in R22 and you want to figure out whether it has a worldsheet representation. This is something that only Witten can guess. To get the worldsheet representation, you have Fourier transform and everything. I do not see how you can start with this and guess that, but if you're Witten, apparently you can. So you start and have Fourier transform in all the lambda tildes. If you Fourier transform in the lambdas, then you have to deal with this complicated Park-Taylor factor, which depends on the lambdas. But if you want to rescale, Fourier transform the lambda tildes, then all you need to deal with is the momentum conserving delta function. So what do? You write the momentum conserving delta function in its exponential representation as integral over some R22 times a product of e to the I k dot x's. So this is just e to the I k I dot ipi dot x. X is the same, of course, so that's a nice bit. And you have these varying momenta, so that now you have Fourier transform along the lambda tilde directions. The Fourier transforms in lambda tilde only act on these exponentials. And you immediately see that they just generate delta 2 of mu I minus x alpha alpha dot lambda I alpha. I was a bit fast there, but hopefully that's clear. That just gives back the Fourier. That was just the Fourier representation of this delta 2 function. So the Twistor amplitude, as it is called, localizes all the Twistor external data of my Twistor eigenstates, which depend on mu lambda, onto the incidence relations. And these actually generate lines in Twistor space. So again, I don't want to be too explicit about this, but if you read the literature, these you usually think of these things as giving you lines in Twistor space. To make this fully explicit, what you can do is complex lines in CP3 in general. But here we are working in RP3, so they give you copies of RP1 that are parameterized by these lambda i's. Okay, so we can make this fact that they live on the same line more explicit by simply defining a pair of curly twistors. These are just constants, whose first, okay, so it has a undotted Spinor index and a Twistor index. So it breaks apart into beta. So A breaks apart into alpha dot and alpha. And you just construct this 2x4 matrix. If you know a little bit about the Grassmannian formulation of amplitudes, then this is just a G24 matrix of some sort. This is just delta beta alpha. You just construct it like this, and the first four components you put as x beta alpha. Now this relation mu equals x dot lambda can be written as a relation, or as expressing a curve in Twistor space like this. So basically mu satisfies x beta alpha dot sigma, and lambda satisfies delta alpha beta sigma, where I just introduce a new sigma, an extra variable sigma in my game, which will parameterize this curve. And then I can sort of rewrite this compactly in terms of my 2x4 matrix curly Z, as ZA lives on this big curve. And now it's obvious that this is a copy of RP1 in RP3, because sigma is homogeneous coordinates on, say, the worldsheet or the celestial sphere, whatever you prefer. And then this is just a map of degree 1, so you can call it a line that gives you all the points that lie on this line to being of this form. So they're all collinear in this sense. So now you can rewrite the delta functions trivially like this. You can just introduce an extra delta function that says that delta 2 of lambda. So that says lambda equals sigma. And then when you integrate these delta functions out using some extra integrals over sigma that you introduce, you get back delta 2 of mu minus x dot lambda I. So I just introduced some extra worldsheet looking parameters. This is completely trivial. Initially, I didn't have these worldsheet parameters, but I just just added some trivial delta functions and then wrote delta 2 of lambda I minus sigma I, which you can immediately integrate out using these d2 sigma I. The nice thing is I can also turn the Park-Taylor factor into a Park-Taylor factor on the worldsheet now. So the factor of 1, 2, 2, 3, 3, 4, and all that becomes on the support of these delta functions, sigma I plus 1, and so on. And similarly, the negative helicity part. And now this looks like a worldsheet formula. It's a super beautiful worldsheet formula. If you're confused, sorry, I probably went too fast over this, but just to give you a gist, this is the kind of worldsheet formula you get. You get your twistor. In the MHV case, all these Z's, the data for all the twistor eigenstates in whose basis you're computing the amplitude, all these Z's lie on the same line at the point sigma I. So that's what this is saying. Zi equals the value of the line, the point on the line at the parameter sigma I. And then you integrate over all the sigma i's, and these d2 sigma i's become worldsheet integrals. You can complexify everything and make this rigorous. At the moment, this is somewhat hand-wavy, but you can generalize this. And again, if you want to generalize this, you have to be written because it's not obvious. So it wasn't obvious for the last, well, before written, so it wasn't obvious for the last 30 years before 2003 that more general curves other than the incidence relations are actually useful for anything. Witten noticed that you can generalize the degree 1 line, the linear map from the worldsheet variable sigma into twistor space into higher degree polynomials in sigma. And as soon as you do that, you put some higher degree curves Z of sigma here, you generate the n MHV amplitude. You generate the n squared MHV amplitude, and you suddenly start getting googly interactions out of higher degree curves. So at least perturbatively, we can solve the googly problem through twistors at the level of scattering amplitudes by simply replacing the degree 1 incidence relations by these higher degree polynomial curves. Again, neither me nor Tim is going to go into too much detail about this, but I just wanted to give you a gist of this. So all the twistor points now lie on higher degree curves. And now that you have worldsheet formulae for your twistor amplitudes, you're very happy. You have Fourier transform back, and you get worldsheet formulae for your space-time amplitude, and you're super happy. And in fact, there's a similar thing that works out for the Grassmannian integral formulae that Nima and Freddie and friends discovered. You can also study, this actually is where the ambidextrous half Fourier transform comes from that I used to motivate the light transform prescription in my paper. You can have Fourier transform the positive helicity gluons into dual twistor space and all the negative helicity gluons onto twistor space. And then you notice that that takes the form of a Grassmannian integral if you're very, very clever again. But then these people are cleverer than me. So that's why I'm giving this lecture. Okay, so you get this beautiful, well, you get worldsheet formulae that go by the name of Roybans, Proudlin, Bolovich, and Venn, so the Brown group. And then you have a gravitational version that goes by Cacciazzo and Skinner, and the worldsheet theory for that was found by Dave Skinner. And you can see Tim's talk for the ambitwistorial take on this. I realize that I'm over time now, so let me just finish on some hopeful notes.
Can I ask one quick question before that? Like, how does this generalize to higher dimensions? Because in this case, like the base of the twistor space, like projection is isomorphic to like both is the worldsheet and also like the celestial sphere, versus normally like the worldsheet for like a string theory wouldn't be.
So it doesn't. Okay. Twistor space don't. Twistor space itself doesn't generalize to arbitrary dimensions. There's something, but ambit Twistor space does. It turns
Wait, I'm
out.
confused about why, like, out of curiosity, could we try to reverse engineer some of these constructions from like the fact that Celestial CFT and all these things were, okay, there's no hope.
I mean, that's why the light transform rigmarole that we are trying to do is pretty.
Yeah. No, okay, so that definitely generalizes. So, okay, that's, no, so that's cute. Okay, that's the take on it is you want to, I like this. Okay, let you go.
Okay. Any other questions? Again, hopefully Tim will do a better job at explaining Twistor strings than me. He'll have an entire lecture to it. So if you didn't follow something, ask him, and I'll go back quickly to the conclusions. Yeah, do you have another question?
No, I don't. I just think there is something about the light transfer hierarchy. So it's, yeah.
Cool. Yeah. We can talk in private as secretly find a theory and yeah, but we can't beat Witten anyway. In the end, it'll have to be Witten who comes up with the theory. Okay, so applications to Celestial CFT. The Twistor strings, as I said, the immediate application is that they generate amplitudes. They can be used to compute all the soft limits, the subleading soft limits, the W infinity soft limits, the collinear limits. All of this is still from the bulk perspective because in some sense, the Twistor strings are dual to four-dimensional physics in the bulk. So I haven't done holography yet, but you can compute them. And you can see Tim's talk about how efficient these calculations can be, how you can think of Celestial OPE as coming from the OPE of well-sheet vertex operators. Actually that is one way to convince yourself that Celestial OPE has to exist, at least at MHV degree, because there are actual operators and actual vertex algebras that you can write in terms of the vertex operators of ambit Twistor strings that give you a representation of the Celestial operator algebra. Of course, they're not the holographic operators, but it's nice to have a concrete thing. Okay, the Celestial holography, then I wanted to just mention that this is from the bulk perspective, but now you have a string formulation on Twistor space, on a Calabia, well, on super Twistor space to be perfectly precise. But you have a topological B model plus some instant-on contributions that give you Twistor strings. You have a string theory description that gives you these amplitudes. So you could think maybe we can do holography for this string theory. And indeed, Kevin and Natalie have developed, Kevin and Davide Gaetto and, Kevin's acolytes have developed this program for for topological B model holography on Calabia threefolds. And recently, in their recent paper, they showed that Celestial holography has the correct characteristics to be the dual theory of something that might be coming from holography for Twistor strings. They haven't found the dual, but they've shown that it has the correct characteristics. So it's super exciting. I think this is the only, other than the 4D equals to strings, at the moment, this is the only actual possibility in my mind for having a stringy holographic duality. Because there are these soft constructions that you guys have, Sabrina, and all this SYK model, and I would be very interested to see how they fit all that R22 story that you have into Twistor strings, or at least a subdual sector. Twistor eigenstates in R22 enter CFT spectrum through light transformed operators. And if you want to see more about this, you could refer, I'm happy to refer back to my Corfu and Edinburgh talks. I have a slightly new, maybe I should mention this. I have a slightly newish version of the light transform that I've been playing with that will hopefully make this somewhat more useful in practice at the moment. Okay, and the Penrose transform is a close cousin of the Kirchhoff-Dademar integral formulae. Sorry if I butchered that name. That will maybe, that Alfredo will probably discuss because I read the paper and they had some interesting integral formulae by taking asymptotic radiative data, the shear and all that stuff, and constructing black holes and stuff. So I would be very interested. I would be looking forward to Alfredo's talk tomorrow. Let me not show you what's below, Peter. That's the end of my talk, the formal part.
Thank you.
If anyone has any questions, you can ask. Or leave, of course, yeah, probably too late. Yeah.
They had to leave, but Andy has a question.
Could there be any sense in which the Twistor string, the 2D theory on this Twistor string world sheet is the CCFT?
I mean,
but that would be the bulk theory. Yeah. Sorry, go ahead.
No, it's a two-dimensional conformal field theory.
Yeah, but that's the string theory. That's the world sheet theory of some 6D dynamics. I'm just thinking of standard ADS CFT type holography where strings in ADS5 are dual to some boundary CFT. The strings themselves are not the boundary CFT. Yeah.
So the suggestion, so there is a 2D conformal field theory in your story, the one that lives on the Twistor string world sheet.
Yeah.
And the space-time S matrix is some kind of correlation functions in that two-dimensional field theory, which is what celestial conformal field theory posits.
No, you're forgetting that there are world sheet integrals, so you actually integrate over the world sheet, while celestial CFT
that's the annoying part. You have to integrate the vertex operators over the positions, but maybe something could localize. Gopalkumar and Gabriel had a similar.
That's my hope too. Yeah, I know what you're referring to.
They had a similar problem, and they showed that. I guess they showed that the string explicitly. They got the right. They in their low level. Their small ADS3 CFT duals, and they had a there it happened that the string world sheet CFT became the thing on the boundary of ADS3, and there was a puzzle about integrating over all the points, but somehow the integral localized. There was a lot of magic that happened. Okay, that's a very special thing, but
I can
that ruled out here, right? Or there could be some relation.
Relation with that, I don't know, but I can tell you the closest thing that actually is a holographic duality. So there's an example in Kevin's work with Davide Gaiotto. You might be familiar with this geometric transition between the resolved conifold and the deformed conifold. You might be in fact, you might be one of the, sorry if I don't know the history too well. So on the deformed, okay, I might be mixing names again. So on one side you have SL2C, and on the other side you have the O-1 plus O-1 vector bundle over the sphere. There is a sphere in that story. You wrap D1 branes on the sphere, and you let open strings travel in the O1 plus O-1 plus O-1 sort of resolved conifold part of the duality. And then once you put D branes on the base sphere, that deforms the space, the resolved conifold, into the deformed conifold, which is SL2C. So it actually turns it in, the branes dissolve away and just becomes closed strings in a curved background of SL2C. So it becomes like an ADS3. The SL2C becomes an ADS3 times S3, curved background strings, closed topological strings traveling in ADS3 times S3. And on the open string side, you have the resolved conifold. But it so happens that when you don't need to take the limit, what is it called? The near horizon limit, since the theory is topological B model that you're studying. So on the open side, on the resolved conifold side of the duality, it just reduces to the two-dimensional theory, somewhat as you're saying. The open string theory is just all the degrees of freedom are just live on the brane. So on the D1 branes wrapping the sphere. And that theory is simply a beta gamma system, a gauged beta gamma system that is dual to a complicated closed topological B model on ADS3 times S3. So one would hope that, so Twistor space is not O minus 1 plus O minus 1 over CP1. It's O1 plus O1 over CP1, if I'm actually if I'm being completely precise. So one might hope that there might be a very similar open-closed duality, that you wrap a brane on a sphere in O1 plus O1 on Twistor space. Maybe it deforms Twistor space by some large n corrections, depending on how many branes you wrap, and it will give you some sort of concrete stringy open-closed duality relating, one side of which might be the Celestial CFT and the other side might be the closed Twistor string theory that generates gravity. And this paper doesn't actually find the theory, but it sort of says that the closed string perspective is consistent for the existence of such a theory. So sort of computes Witten diagrams essentially and shows that it has the correct collinear limits on Twistor space. You think of Twistor space as some analog of ADS3 and you compute Witten diagrams on Twistor space and it works. It's fairly cool, yeah. We're sort of on the verge of finding something cool, maybe.
Is there a poor man's intuition for the ADS3 cross S3 from the perspective of like, if you try to look at things at null infinity or like how like this incidence relation in Twistor space maps?
Yeah, I don't know. And I'm being honest, I have sort of scoured the literature and I think this has not been worked out. So it would be really interesting to find it.
Yeah. ADS3 to be the massive case states or something.
Oh, no, I'm not even, yeah, I'm still saying massless.
I'm just throwing shit out of like.
Okay.
Right.
Yeah. I have a few more sort of slides on the relation to W1 plus infinity, depicting a back of the envelope calculation that I did to prepare for the talk, but I don't want to make people stay. So this is not any published work or something. I just wanted to give you an appreciation for how Twistors linearize the action of W1 plus infinity. Do you want me to, if people want to stay, it's fine.
It's up to you. Now there's been some requests for your stuff, like the follow-up or the like post-talk stuff to be recorded. So, but that's your call. So do you want this to be recorded or you want it to not? Okay.
That's fine. That's fine. Okay. But I was just worried that you might want to leave some.
Oh no, that's okay. No.
Yeah, okay.
I mean, I want to gauge the audience, but I think that normally like more content is better if people can leave whenever they want to. Like,
yeah. Basically, I'm done with what's required for tomorrow's talks. Mm-hmm. The extra stuff is just some appreciation for Twistor theory and how it can be applied to celestial holography. So let me just go through it maybe in the next 10 to 15. It should be quick, actually.
Yeah, if it's like 10 minutes, it's perfect, I think, or like whatever, like something.
Because you guys have already talked about W infinity a lot, so I don't need to repeat that. So how would a celestial holographer discover Twistor space? You would start doing all these light transforms and you would discover it. But okay, let's, the celestial holographer would discover it through celestial OPE. And that's indeed where we all sort of first started noticing that the Twistor technology is really saying something about celestial CFT. So, okay, I guess I don't need to remind you by now, but you have your collinear limits for graviton-graviton scattering, which factorize in the bulk, and on the boundary, they map to some OPE of two operators coming close together. So I just represented the boundary as a line. You can think of it as the celestial sphere in Minkowski space or as the celestial torus in R22. So basically what happens is you bring these gravitons in the bulk close together, and on the boundary, this coincides with bringing the dual operators close together. And this OPE factorizes into some OPE. This OPE simplifies into some OPE coefficient times an effective graviton. This was discovered by Stiebergen Taylor. Graviton or gluon. I use G, so it can be anything. And now, the idea of a symmetry of the OPE is that there exists a charge Q. If you act with the charge Q after taking the OPE, it gives the same answers as if you act with the charge Q before taking the OPE. And the previous talks listed a bunch of symmetries, Poincaré, BMS, Virasoro, and all these higher towers of soft gluon, soft graviton symmetries. So let's just see what these soft symmetries look like in Twistor space. they do look very complicated in the original expressions for celestial OP. My point being that in Twistor space, they simplify drastically. So, right. So they look like a tower. They arrange in some sort of a tower. You have super translations, super rotations. Do these have a name? Subleading soft graviton symmetries.
I guess Anna and Laurent could coin it if they want to. It's a bit. I think it's a multiple connection or something later. Like, but I don't know if it. Yeah.
Yeah.
Like
higher moments of symmetries. I don't know.
It'll be like multiple moments.
And the nice thing is that these generators are Kac-Moody generators, then they all come from taking soft limits of graviton, conformal primary gravitons. So for instance, the super translation generators come from taking a soft limit of the leading, come from considering the leading soft graviton, and they naturally decompose into polynomials in the variable z bar into 2 signature. So these sort of act as, these W generators act as generating functions of all these Kac-Moody generators, the parameter being z bar. And now these have an extremely complicated looking expression when their action on the celestial OPE has a complicated expression. So you take the OPE of such a generating Kac-Moody current WK at level K. It's OPE with a hard graviton. Looks like some differential operator acting on the hard graviton. Where this differential operator is a super complicated order K-1 differential operator, which I have written in a factorized form, sort of spoiling some results in Timstor, but forget about that. There's a complicated order K-1 differential operator. Z bars are coordinates of this thing.
But it should
WW
come from like the orders in R recursion probably of the equations of motion. Right, like in the same way that the higher dimensional like memory.
This differential operator you can derive at the level of the celestial, at the level of the amplitude using BCFW. This is what Monica and
sure. No, sure. I think. I mean, yeah. The question. Never mind. I think I was just.
Oh, I think Anna's talk would be a better place to look for that. Yeah. Yeah. Okay, so how do we actually make sense of this differential operator? It's an order K-1 differential operator. Can you actually go to a space in which it simplifies? All of these differential operators like of or increasing differential order. So the super translations are not differential operators, the super rotations are order 1, the super rotation, the subleading soft gravitons are order 2, and they all increase. Can you go to a new basis, a conformal primary basis preferably, but in the first instance, any new basis in which all these differential operators become linear differential operators? And let me show you how this is exactly what's accomplished by Twistor space. So first, go back to momentum space by doing so the operator in the Mellin representation is related to the operator from momentum space by doing a Mellin transform. So you can get some sort of operator in momentum space, which is not conformal primary any longer, but it transforms as a primary under the bulk Lorentz group, you can think, by doing an inverse Mellin transform. So now you can take this action of W1 plus infinity and pull it back through the transform to momentum space. It's still a complicated differential operator. By now, I hope you're all accustomed to all these Spinor variables. These are just variables and components. There's still a K-1 order differential operator, but it's somewhat nicer because it's just a simple differential operator to some power. But now you know what to do. You can Fourier transform in lambda, tilde, and you can get a differential operator which turns all of these into numbers, and this single thing that is a number into a differential operator. So as I said, I've only done a back of the envelope calculations. Maybe you have to sort of be careful about operator ordering and stuff. But if you just quickly do a back of the envelope calculation and ask, can we find 4D states or 2D operators on which these W infinity charges act linearly? And yes, you do a half Fourier transform to Twistor space, and you define an operator that you believe is dual to Twistor eigenstates in the bulk by taking the operators dual to momentum eigenstates and half Fourier transforming. This turns the derivatives into numbers. This is sort of this is a basis that is an eigenbasis of these differential operators. And this turns this complicated looking representation of W1 plus infinity into an extremely simple representation, which acts as linear differential operators acting through some canonical transformations on the mu alpha dot planes. So the two planes of mu alpha dots have a natural symplectic structure, which you can just think of as this Poisson structure, d by d mu naught dot, dg by d mu 1 dot, this natural Poisson bracket. And now if you have Fourier transform this complicated W infinity action on momentum eigenstates, it turns into this beautifully simple linear action on Twistor eigenstates. And this acts as, yeah, so this is one of the this actually sort of shows that this is W infinity. So it's very nice. If you did not know if you did not know already that this was W infinity by actual hard work that Monica and Peter and others have put into it, then this sort of quick back of the envelope transforming will show you that this is a W infinity algebra, and it acts most nicely on Twistor space, on Twistor eigenstates. Now, I did not write notes on this, but if you go to light transform, so what is the natural conformal primary operators that you can construct out of Twistor eigenstates? These happen to be these light transformed operators. And again, I would refer back to my talk in Edinburgh for this, or my paper from July. And so if you act with the W infinity generators on light transformed hard gluons, they act in a linear way. So you have to simply do a further Mellin transform on this action to get a linear differential operator acting on the light transformed boost eigenstate. So it's very beautiful. Maybe a possible application would be to, well, now that the action is linear, you could hope that bootstrapping the OP by imposing symmetry constraints would be much easier than it would have been if you had to use hardcore nonlinear differential operators and act with them on the OPE. So that would be one application. There might be other interesting applications pointing to the fact that the theory might actually live on some brain in Twistor space, and that's why all this is working out so nicely. Who knows? Okay, yeah, that's the end of my talk. Thank you for listening.
Thank you, yeah.